it's doing. Hello. So hopefully you guys can hear. If you just say something in the chat.
Oh, there it is. Okay,
cool. So I hope you guys can hear us. If somebody's watching, could you text in the chat? Maybe send a message in there saying, "Hello, we can hear you." This is the first time ever doing a stream, so I want to make sure I'm doing this correctly.
All right, sweet. So we got one person that says it's happening.
Cool. All right. So good morning. My name is Dylan Romig, and this is.
My name is Zach Muckler.
And we're two. Right now, we're two engineering students. I'm from Pennsylvania. Zach's from Texas. We're working at a space company in California, but we decided that it'd be really fun to do a project, a Bi-Prop project, and do it as cheap as possible and as fast as possible. We're going to try to do this over 2 weekends, and it's going to be intense. We're going to have. There's a lot of work to be done, but I think it's going to be a lot of fun. So, like I said, welcome, and I think we can pretty much get right into it. So the first thing that we're going to really talk about and do is we're going to, first off, the actual part of the problem, what we're trying to solve here is we're trying to build an engine for as cheap as possible and as fast as possible. And we want to do a Bi-Prop. So Bi-Prop is fun, it's a good time, and it'll be quite a challenge. So to kind of fit within the budget, we did a little bit of preliminary work on this to make sure that it was financially possible to actually do this. And for $500, we've kind of narrowed in on you're really going to get an engine probably about 10 pounds of thrust, maybe a chamber pressure 120 psi, somewhere in that that frame. Excuse me. Yeah. So first off, we're going to talk about propellants and actually bounding the problem properly. So, like I said, our problem was how do we do this for this budget, and how do we actually achieve basically a rocket engine, which is like choked flow through a nozzle. So we kind of looked at what kind of fuels would be available to us, easily accessible, also affordable, and that's kind of mostly gases. We're not going to be doing any liquid fuels. It's going to be like a gas injector for the Bi-Prop. So we'll have a gaseous oxygen as the oxidizer, and we have yet to figure out what the fuel is exactly because we're having some challenges talking to Airgas about purchasing and procuring fuel. So that fuel might be gaseous hydrogen, it might be methane, and it might possibly be propane. We're not sure yet, but we're going to kind of do an engine design here of maybe 2 or 3 of those fuels. So the first thing we're going to really start off with is a NASA CEA calculation. So that essentially, if you go to this website, actually, yeah, well, it'll bring me here and it'll say that, because I had this tab open before. So we're going to be using the NASA CEA run to figure out some of the basic parameters of our engine. It's also important to note that in order to make this as achievable as possible and for the lowest cost, we are going with a commercial nozzle that's available. So this engine's going to be, there's no cooling in it. It's going to be glass phenolic. There's going to be a phenolic liner and a glass phenolic nozzle. So right here, this is the nozzle we'll be using. And this is a really, really good starting point for this project because it bounds the problem really well. We have a throat diameter that is known, we have an exit diameter that is known, and we have other dimensions on this geometry that bound how big we can make the engine and like the maximum size, and we can find like L star, C star, all sorts of performance parameters for the rocket engine. So we're kind of starting with this nozzle. Like I said, this is really important because we have this diameter here, this 0.291, and that is basically the holy grail, the holy parameter, I would like to call it, for this project. Is everything we're going to do is based off of this nozzle because this is really, really cheap and easy to do. This nozzle particularly is $3.65 from this company, Rocket Motor Components, RCS. So, like I said, super cheap, easy, and it shouldn't be an issue. So when we go, so I guess we're going to kind of go right into it. Maybe we'll jump over to the whiteboard to kind of explain what's going on and what we're trying to do, but let me see. I might be able to just do this, just start going into it. So, like I said, we have this nozzle. We're going to have a exit ratio, or sorry, a throat to exit ratio, and also there is a diameter here for the nozzle inlet. So we can kind of estimate that this will be the chamber diameter, but our chamber is going to be a little bit bigger than that, just because like we did a little bit of preliminary things, and we're trying to figure out exactly how achievable this was. So we can go into the NASA CEA stuff, and this is completely everything we're going to do is completely open to the public. We're not going to be using any proprietary software. We're not going to be using anything that costs money in terms of design stuff. It's all going to be things that you can, like CAD software that you can probably, if you have an educational license, or rather you're a college student, the CAD software we'll be using, you'll be able to get with an educational license, but you can also get Fusion 360 for private home use, and that's completely free. So the CAD software we use today doesn't bound your ability to do any of this stuff. But everything else is completely available to the public in like this NASA CEA software. So first off, we're going to kind of start with we're most likely going to be able to get hydrogen. So we're going to kind of start with a hydrogen ox engine, or actually, what do you think? Should it do methane first?
I think hydrogen probably.
Okay, we'll do the hydrogen first. So you have this main page here, and you're kind of going to select rocket, because obviously we're doing a rocket problem. Hit submit. So now we kind of have to find you have to figure a chamber pressure value. If you don't know a chamber pressure, you don't know where that's going to be, because obviously you haven't figured anything out yet. You can either randomly select a value, or you can choose interval values from 24 data points for a low value, high value, and the interval between each of those values. So I'm thinking we're probably going to be in and around like 100 PSI, just because some of our other fluid system components, again, to keep this cost under $500, a lot of the fluid system components are cheap and only can withstand so much pressure. Not that they're going to burst, but that their rated pressure for operation is only maximum like 150 to 200 PSI. So we're kind of bound by that capability. So knowing that, I'm going to kind of just choose maybe I'm going to choose like the low value of 90, maybe a high value of 150, maybe actually probably do even smaller, 125, and then we can make the interval like 5 PSI, and then we want to do it in PSIA. So actually this would be, what was that, would be, if we're doing it in PSIA, it would be I can't math, 104.7. So PSIA is atmospheric pressure. So there's PSIG, PSIA. PSIA is based off of like 0 is like complete vacuum, and atmospheric pressure is 14.7 PSI, and then you add on your whatever pressure you're achieving on top of that. PSIG is gauge, and that'll be 0 is the atmospheric pressure, and then anything above that is just tacked on. So you already like it just shifts it by 14.7 PSI, whatever the atmospheric pressure is. So that kind of changes these a little bit. So this will be 139.7 if I did that correctly. And the interval will be 5 PSIA. Accept and continue. So now here we're going to choose, since we're doing hydrogen the first time around here, we might run this calc again with methane right here. So since we're doing hydrogen, we're going to choose H2. And we're not going to be doing liquids, no cryogenic stuff here. And then that should all be good. I don't want to hit reset. And then we're going to be choosing gaseous oxygen, again, not liquids, because we're not in the cryogenic, we're not doing cryogenic stuff. And then we can hit accept and continue. And then here's where we don't know the OF ratio. So what we're trying to achieve with this calculation is we're trying to essentially generate a plot. We're going to be doing it in a brute force method, where I'm going to just be grabbing values and putting it into an Excel sheet. Again, so demonstrating to you that you can do analysis. You can do this, get the information you want out, and make graphs from it, make plots from it, and actually extract useful information from all these data points. And so that's what I'm going to be demonstrating. Is it's going to essentially, I'm choosing an OF ratio over this crazy range because I have no idea where the OF should be. So we're going to choose like a low value of 1 and maybe a high value of 8. And then we'll make the interval like 0.5. If that should work. I don't think it should. Maybe, actually, I'll make it a little bit tighter. We'll do 0.25. Hopefully it'll work. Sometimes they only let you, 30 data points, so I can't do math in my head, so let's see if that works. It works, okay. And so this is the other important thing. So we don't know the chamber pressure. We're guessing what the chamber pressure will be. The exit pressure would be 14.7 psi or atmospheric pressure, but we don't know that ratio because, like I said, we don't know the chamber pressure, so we can't really use this column. We also, I forget, okay, yeah, so we could use both the subsonic and supersonic area ratios because, like we outlined before, we have this. So these are our area ratios. So subsonic will be the converging to throat section, and then our supersonic, I think that's what I said, right? Yeah, our supersonic area ratios would be the throat and out to the exit. So, like how the nozzle works is you have on this side of the nozzle, you have high pressure, relatively low velocity flow, and the nozzle essentially accelerates that flow at the expense of the pressure. So the pressure is converted to velocity energy, and then at the throat, you should achieve Mach 1, which is choke flow. You cannot push any more mass through that orifice. You hit that. Mach 1 is as high as you can get flow, or sorry, the highest velocity you can get flow through. And then as you expand that flow, it can accelerate further, and you can achieve, depending on your pressure ratios and all sorts of other variables, you can achieve really, really fast gas flow on the exit side. You can get really fast nozzles, or really fast flow. So, we don't, actually, let me grab my calculator. Forgot to grab that. So we're gonna do, actually, you know what? We probably should show this on the screen so we can do it in the budget by prop tab. So we have this guy here. This is kind of our Excel sheet that we created that is essentially just for this design. We're going to have the engine design here, the test stand design. We're going to throw in the NASA CEA values that we're going to get from this calculation, and we'll put it in here and we'll create some plots. Then we also have some other ones here. We have a regulator characterization. So we did some flow calcs to figure out the regulators that would be able to achieve the flow we're looking for, and that was done last week. We have some other tabs in here. This is preliminary budget stuff, and yeah, I forgot we named it real cheese. So we'll kind of do a little bit of stuff here. So we're going to choose, so we'll reorganize this as it goes along, but right now it's kind of just maybe actually, you know what, we'll make a new tab that'll just be number crunching so that we don't compromise the engine design tab. So we'll add a new sheet and we'll call it just go down here. We'll just call it number crunching. And here's so like I said, we're trying to find the area ratio. So we'll do the throat area, and then we'll do the probably just the exit ratio. We'll just go the supersonic way. Exit area. All right. So we have actually, this would probably be a good whiteboard little thing here before I put it into the Excel sheet. So let me go back here. Oh, sorry, back here. So we have, like I said, we have this known value. So we're going to jump over to the whiteboard cam. So over here, we just have some stuff going on right now with characterizing the problem, making sure that we're correct. But so if we're getting right into it, we are essentially, oh boy, I'm dropping stuff. So we're going to try to find that ratio. So we have, I think it was, can you tell me the...
You want to switch?
Yeah, that's probably a good idea. Yeah. We got 0.68, so we'll do this. We'll just draw a little image here of the throat, or of the nozzle rather. So this will be the exit over here. 0.688. Diameter, and then our throat was 291.
And obviously this is kind of like an amateur. We're not like perfect at all this stuff. So I'm going to make a ton of math mistakes today, and it's going to be pretty embarrassing. But we'll try to fix them as we go along. And if you see me doing something dumb, please just put it in the chat, and we'll take a look. So we have your exit diameter, you throw diameter, and we want to get areas out of that. So we know that area equals pi r squared, and because like I can't do math properly, we know we're trying to find the areas, but we have. Zach, could you do these guys divided by 2? Because I cannot do it in my head. So we're going to do the area of the exit first. So A sub E, so you could do
So that's 0.344.
0.344. I should have been able to do that in my head. Squared, could you
And
crunch,
then
crunch those?
0.1455 for the other one.
Okay, what was it? 0. What? 1.5?
1455.
Okay. So hopefully I'm not blocking anything. I probably am. So we'll erase some of this. So yeah, this is just our characterizing the problem. We wrote a couple things down. Just to reiterate, we wanted to make sure the problem was simple, affordable, and actually be able to manufacture this engine. So yeah, you can do some numbers over there. So I'll do the area of the throat.
That is a fancy looking 3 right there.
So area of the throat will be pi 0.1455 squared. And can you tell me what the area of the throat was?
So that's going to be 0.0665.
65. And then we're doing this all in inches. I know a lot of people are going to cry and complain, but a lot of all the design notebook we're kind of going off of. It was published in like 1960, and it's all in English units. So unfortunately, that's the reality of today's today's little stream.
And some context for those resources as well. We're going off of a book Rocket Lab came up with a couple years ago. That'll also be shared with some of the post-live stream resources, so you guys can get into a little bit more detail about that as well.
Yeah. Okay, so the supersonic area ratio, if I remember correctly, should be the area of the exit over the area of the throat. So you have the exit area, got 3.3716 divided by the throat, 0.0665, and these units will cancel out. So you're just, a ratio is unitless, it's dimensionless. So could you do that for me?
All right, so that's going to be 5.673.
All right, so right there, that's our ratio, supersonic area ratio. So that's the number, 5.673, that we're going to put into the little calculator, the NASA CEA calculator, and that should give us some good...
Actually, I take that back. It's 5.58.
5.58.
Yeah. That's yeah.
Now you're tripping me up. So. All right, so that's the number. 5.58, we're going to put that into the NASA CEA. So
Hop back over to here. So we got this guy open. And find the exit conditions. So now we know this. So we got 5.58 as our supersonic area ratio. I think I'm doing that correctly. I'm almost positive it's not a... oh, I think is our video freezing a little bit?
Let's see. It looks like we are temporarily frozen.
Let's see. There we go. For some reason that froze there. I don't know if anybody...
Let's see.
If anybody notices like the video froze, just send me, shoot me, or put something in the chat. That was weird. All right,
Yeah.
so okay, we know our supersonic area ratio. We know our oxidizer fuel ratio. Or sorry, we don't know that. We know the number, like the different values we're putting into it. So accept and continue to the next form. So okay, we're at the end. This is just where you kind of choose what you want. So we're going to want to tabulate the results and put them into a spreadsheet so we can copy and paste things in. And this is going to be very cringy and brute force, but it works, and that's how I've done it before. There's probably a way to properly automate this, but so we're going to be using Google Sheets because Google Sheets is free for everyone to use. So not everybody has the Microsoft Office package. Alrighty, so it'll ask us to select output parameters, so we can kind of just choose things. So we can kind of do the cross-sectional area. We can do this guy or whatever. So I think we're going to choose. Maybe if I click in the box, it'd be fun. So we're going to choose gamma. We're going to choose, and the reason I'm choosing some of these values is they're going to be very important for certain engine calculations. Like gamma is the ratio of specific heats, and that is very, very important for a lot of calculations. So we're also going to choose the molecular weight of the products, choose the pressure, we'll choose the specific heat, that might be useful. We'll choose the temperature. Temperature is extremely useful. The adiabatic flame temperature, I think that's what that one is. We'll choose the Mach number. We'll choose PC to PE, because now this thing will backtrack out the chamber pressure for us, because we chose, hey, do it over these different values. So we'll do PIP, and then we'll do ISP, because everybody wants to know the efficiency. That's important too. So we could also do the coefficient of thrust, but we can actually, maybe we should do that. I don't know if we'll need the specific heat, because we have the specific heat ratio, so the ratio of specific heats rather. We probably do the CF instead. Maybe not that one either. I'll do this. All right. So I would like to explain that more in depth, why I was choosing certain parameters and why they're useful. But it's hard to explain it in a quick sentence. But it's kind of I've done not a ton of engine designs, but as you do them, you figure out based on the problem you're trying to solve and where you're starting at, what things you need, what parameters you need. At least in this case for the NASA CEA, which things you need to get pulled out and which things you can use for calculating other variables. So we'll hit submit, and here is the actual results. So this is going to be long because we had multiple inputs, and we had also little chunks of stuff. So we had different pressures, and we also had different OF ratios. So it's trying to boop, 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 and put those all together. So yeah, it'll be a little bit long process. So we're gonna click on the output. It'll open up here in a new tab, and as you can see, yeah, it's long. It's going on for a while. So I might I'll show you the beginning of doing this part of it, and maybe then we'll skip to something else, and then maybe Zach, you can input those numbers into the thing, because it'll take a decent chunk of time. Yeah. Probably about like 20 minutes to make sure that you get them all correctly. So we'll kind of start the plot and kind of see it, but we can also show you. So if we go back to the budget prop, so we did do a NASA CEA for methane before we started. We kind of just wanted to figure out how everything was working. So these are kind of the plots you'd be looking to get out of it. So these outputs, so here's your varying OF ratio. Then it gave you a chamber temperature, and then I just changed that to Fahrenheit so that it would, again, it's because even though it's in Kelvin, and that's a very useful unit, Fahrenheit and degrees Rankine are more useful in terms of our design sheet. So, and then it also gave the ISP and meters per second, and I just converted that to seconds. So you just divide this number by 9.81 meters per second, 9.81. So you can see just for these are the plots, like I said, that you'll be looking for. We'll go briefly over this now before we go back to all this data. So essentially what you're looking at here is you have different OF ratios. So your oxidizer to fuel ratio is varying over time, or you're just increasing it. And then you're looking at your ISP, or basically the efficiency of how much propellant that you're, the way to, I forget exactly. So it's, oh man, is it this is why I can't remember equations in my head. This is always the embarrassing part. But it's essentially it's like thrust over the total propellant flow rate, I think, is the equation. So ISP equals thrust over the total propellant flow rate, and that's like a performance parameter. So the more thrust you can create from a certain amount of propellant means that your ISP is higher. So this is what you can see right here. Your chart, your little plot here is going up, and then it peaks right at around 2.5, 2.4 for your OF, and then tapers off. So if you're looking at this plot, you're like, hey, I want to be right there. I want to maximize my ISP. I want to be as efficient as possible. And then now that you know this, you can come over here to the OF ratio. Hey, I want to be, so I know I'm at 2.4. I can go up and say, hey, my chamber temperature is going to be probably about 5,700, right in there, 5,700 degrees Fahrenheit. And that's really useful then for the further calculations we'll get into with the Rocket Lab, the PDF that we have here that has all of the engine design. So, and then at the bottom here, this is kind of doing another calc. We changed some variables here, so we dropped the chamber pressure down to 100 psi, and here's our chamber pressure to exit ratio. Like I said, these were just test parameters. This is us just throwing some information in there and figure out what was happening. But you can see the massive ISP hit when you drop the chamber pressure. So when you're at like a high chamber pressure, you're being efficient. It's kind of hard to explain this. It's not necessarily intuitive, but you're being efficient in terms of your combustion. You're extracting and using as much energy as possible to produce thrust. So that's why you have like a higher ISP. You can see it kind of peaks here at 283, but down here our peak is only at 244.89, and that's because we have a lower chamber pressure and our pressure ratio is 10, almost 10, or more than 10 less. So this also made it a little bit nicer. I kind of narrowed in the OF plot, so it's only from 1 to 3.5, but it has a little bit nicer of a plot here, not this weird bump right here. And then you can, like, same process. Hey, right here's the peak, and that 244.89 is at 2.25. So at 2.25, which is basically right in the middle, that's our OF ratio in this case. So we come over here and go 2.25. You come up and you're like, hey, my temperature is again a little bit under 5,500. So probably about 5,000, I would say 375 in this case. Probably could just look over here to 5,491. So, but if you had only plots, that's kind of the process you go. You use the plots to get the information you need. In this case, we do have obviously these nice values in this table over here that we can just grab things from. But so that's what we're going to essentially do here with the NASA CEA, and this is all that data. So the actual plots for it are going to be a little bit more complicated because we're going to have varying OF, varying chamber pressure, and we'll have to have like a chamber pressure versus OF plot, and hopefully that will look nice, that you can actually get information from it. But yeah, so we'll do that. And then we'll probably talk a little bit about the, what else should we talk about with this?
Well, I think one important thing to note is a little bit of context on how we kind of came to the conclusion that hydrogen was our best fuel.
Oh yeah, that's probably important too.
But yeah, so I guess one of the trickiest things with building a rocket engine, especially for amateurs starting out, is actually obtaining the proper propellants, or getting your oxidizer, stuff like that. So one of the easiest ways we determined to do that was using a company like Airgas. They have facilities in just about, well, I don't want to say everywhere, but
a lot.
They're pretty much everywhere. For starters, oxygen, well, I guess Airgas is a company that is really good at supplying gases for like welding processes, and of course that includes oxyacetylene torches. So a company like Airgas is going to have pretty much all kinds of sizes of oxygen cylinders, and so gaseous oxygen is going to be really cheap to obtain, and you're going to have it in all kinds of different sizes from a company like Airgas. The tricky part came with actually deciding what kind of fuel we would use. So like initially we had thought we would go with something like methane. One, because it kind of simplified our CEA calculations, and another thing as well is that kind of wanted to spice things up with methane.
Yeah.
But initially we had thought you needed to have like a facility you stored it at, and that facility needed to be inspected. And that kind of complicated our process. Okay, well, all right, so we need to get this inspected, and of course, you guys know we're kind of trying to do this as fast as possible, so we were worried it would take a week. So, we called Airgas, we talked with them, and we found out, well, we don't need an inspection, but methane, once we priced out a little bit in more detail, what kind of methane we would need and how much of it we would need, we realized it was a little bit too expensive for exactly what we were looking for, especially if you want to build a bi-prop under $500. So then we kind of looked into alternative fuels, like propane was one candidate we were looking at. The problem with propane is there's a lot of use for it in say cooking applications. So it's Airgas doesn't typically sell high pressure propane cylinders. I think the max pressure, it was somewhere between 100 or 200 psi for the bottle pressure. So that kind of ruled that choice out. And so then the next logical decision would be, okay, well, what about acetylene? Oxyacetylene torches, they have plenty of acetylene, so why not that? Well, the way that they actually have acetylene inside of these bottles is they dissolve it in, I believe it's acetone. And this kind of presents a couple of unique challenges with storing it. It can actually be a pretty dangerous gas. If the bottle tips over, you have that acetone kind of mixing up into the regulator, and then you can actually have acetone basically spitting out of the regulator, and that's obviously not a good thing. So to kind of make this a little bit safer, we actually went with hydrogen. And I know hydrogen, a lot of people kind of start thinking, well, there's the Hindenburg and all these disasters with hydrogen, and it's actually pretty dangerous. But we actually found upon some research that we were doing on hydrogen, it's actually a lot safer than most people think. When hydrogen, it doesn't combust as easily as one might think when it comes in contact with air. Obviously, it mixes with the oxygen and it becomes a lot more dangerous, but there's we found that actually when hydrogen actually does combust, it doesn't release as dangerous of a shock wave as one might think, and the combustion actually dissipates quickly or more quickly than other gas clouds that would mix with ambient oxygen in the air if, say, a leak did occur. But so keeping that in mind, and just kind of hydrogen actually ended up being a little bit more affordable than some of the fuel alternatives as well. So a little bit of, I guess, kind of looking to the future there. We'll be calling Airgas on Monday and kind of pricing out and getting everything together for, let's see, kind of actually getting the hydrogen later in the week. But yeah, it looks like we have a question. How do you plan to deal with the inevitable hydrogen leaks? All right, so that's a good question. So I guess for starters, the whole idea being a budget bi-propellant engine, we're using kind of cheaper nitrogen regulators and putting adapters onto the end of them to kind of save money on the more expensive stainless, fancy regulators.
And there's a massive risk with doing that.
Right.
It is not a good idea. But in order to stay within the budgetary bounds, we kind of have to use off-the-shelf nitrogen regulators, and they do sell adapters to go from hydrogen and oxygen to nitrogen. So nitrogen is CGA 580 on the regulator. That's the configuration for the threads, and the hydrogen is CGA 350, and oxygen is, I forget what oxygen was. Oxygen was I don't remember off the top of my head,
yeah.
But it's so they make adapters for them, which is kind of scary because should you be able to adapt a hydrogen bottle to nitrogen service? But it's kind of all we really have, because if you went to get I purchased oxygen regulators before for other projects that are good for oxygen service, and those ended up costing $400, which is whole budget's gone at this point
Yeah.
for regulators. So we're gonna do nitrogen regulators. Still doesn't address the hydrogen leaking issue.
Right.
Uh,
And I think kind of the way that we're planning on minimizing that is just a really, really short like hot fire time, very short prep time, very short hot fire.
Yeah.
We're doing all of this very quickly.
Yeah.
Because, like Dylan was mentioning, those nice regulators that kind of contain all of those leaks, it's a lot.
There's a lot of money. So
Yeah.
we're gonna kind of set up, pressurize the entire system, and get back and kind of run and just go for it.
Mhm.
There's gonna be check valves inside in the system to prevent anything if there was any sort of any sort, not necessarily explosion, but essentially propagation of pressure or combustion products back up the lines, that the check valves would prevent that from continuing past up to the valves, the main valves. So our biggest plan to deal with dehydrogen is to just keep the bottles open as like short as possible. No just sitting there all day with hydrogen sitting there. It's going to just be turn on, or essentially turn the bottle on, pressurize,
Yeah.
set the regulator, pressurize the system, get away. I'll have my computer set up to do the actual hot fire part of it, which will just be kind of, I'm thinking a MATLAB program for just something simple with a little GUI that just hits, like you hit a button and it just goes run, and it'll have pre-programmed the timing for the solenoids and the shutoff. So, and then it'll just record pressure and report the chamber pressure back to us. So that's kind of basically what's happening with that. So it's not a good way to address a hydrogen issue. I would have much more liked to have methane or another gas that is a little bit less small, a little bit larger, because that's the issue with hydrogen. It's so small,
Yeah.
kind of just leaks through everything. It just goes. Those little molecules are very, very small.
Yeah.
So that's kind of how we're addressing that issue. Not a very elegant solution, and we're going to try to make sure that we're taking care, make sure we're doing this not in an enclosed space, right? Because if you're leaking hydrogen into an enclosed room and then you light the engine off, well, you just made like a room bomb.
Yeah.
It's just, you fill this room with gas, combustible gas, in a nice air to fuel ratio, and light it off, and it's gonna go bang.
Yeah.
So we're gonna try to not do that. We're gonna have it in an open air environment to keep hydrogen from, at least whisking hydrogen away from just airflows. So that's basically how we're doing that.
Yeah, and I think this would be like a good time to kind of segue into some of the testing we did with those regulators as well, kind of characterizing the flow rate and how exactly we did that, which I believe is on one of the pages of our spreadsheet. Let's see. Yes. All right. So the principle behind this was we have now, I guess in the spirit of the budget bi-propellant engine sort of thing, this isn't a sort of necessary step. You don't need to have these resources. This isn't, I guess, part of the budget, if you will. But since we did have the stuff already on hand, we took the liberty. We did it for you, I guess, is a good way of saying it. But anyway, the idea behind it was we have an argon cylinder, and we essentially pressurize the line up to a fixed pressure, and then we open a valve. And we have a pressure transducer that records how long it takes to fill a fixed volume. Once we have that data, we can take basically how long it took to fix that volume, and
So
we have our flow rate out of our regulator.
So we had a sampling cylinder from Swagelok that we had a known internal volume, and the pressure transducer was measuring the pressure basically inside the tank. So we have this known volume, and we had a choke point at the regulator. So the regulator's little exit orifice was the choke point, so that was going to be the limiting factor in the system. And we had a little ball valve downstream of the regulator. So we'd pressurize the ball valve upstream to whatever, in this case, one of the set points was 300 psi and the other one was 400 psi, roughly. This is all in PSIA, so it was like 314, somewhere in there. And then we open the valve, dump it into that cylinder. The cylinder is closed on the other end, so it's a closed volume, fixed closed volume, and we allow that pressure to build. So since we have a restricted flow, it doesn't just boom and just go right up to pressure. As you can see from this plot, it takes a few seconds, and essentially you could do some like calculus and some other fun things to find your actual flow rates. But essentially what we took was we took the start point minus roughly about here where it starts to taper off or level off, and you kind of just measure that time. So you know the fixed volume, and you know the time it took to fill that fixed volume, and there you go. There's your volumetric flow rate. And using that number, we can make sure that our fluid system components can keep up with the demand for the engine. Even though the engine doesn't really have a demand, it's not pulling these things. It's in order to run the engine at the desired parameters, we need to make sure that all of our fluid system components can actually supply enough fuel and oxygen to the engine. So we had to do a couple little calcs here and some actual some tests, and we did a similar test the other night with we bought a solenoid to make sure the solenoids are rated, I think, for 145 psi. But with where the chamber pressure is going to probably be and the expected pressure drop across the injector, we're looking at probably closer to 200 psi line pressure going into the engine. So we ran some tests to make sure those little solenoids could actually handle 200 psi. Their maximum operating pressure is 145, but there's always a factor of safety built into these things, and that's why we tested it and not wait until the day of the hot fire, because we wanted to make sure those valves can actually handle it. And that little $9.49 solenoid had no issue reaching 200 psi, and it didn't leak. But that was with argon, so that's not hydrogen.
Yeah.
But
now that doesn't mean go out and buy a super cheap solenoid for all of your rocketry projects. It's just given our very, I guess, restrictive design constraints, this was one of the decisions we had to make, and we were able to test in a very safe and just a very safe environment with experienced people who've worked with this stuff before. So
and having the tools available to
right,
us.
yeah. So word of caution, this isn't something we're encouraging, but just be careful. Yeah.
Cool. Alrighty, so let's see here. So
yeah. So I guess as we're transitioning, if anybody watching has any additional questions, throw them in the chat, and we'd be happy to answer.
I saw that somebody said that our area ratios are wrong, and that is entirely possible. We already started. If that is the case, then we already are starting off on the wrong foot.
Let's see. I believe there was one note that said instead of actually calculating the areas, you can just take the diameter ratio and then just square it.
Oh, okay.
Yeah.
See, I'm not good. I'm not great at math. I kind of just want to. I'm kind of doing a process where how my brain thinks about it. So, but thank you for pointing that out. That's actually probably very useful.
Yeah.
But I hope it got to the same answer. I hope our method got to the same answer.
I might as well run that real quick.
Yeah. So, do you? I'll ask a question to the chat. Do you want me to go through extracting all these numbers properly, or do you want to show a couple things and maybe we'll transition to something else? Like I can have Zach input some of the stuff, or I can input some of it and we can switch to something he's doing. Is that what you guys, anybody have anything in particular they want, or would they like to see it in its entirety? Give it a second.
Yeah, so the result is pretty close, 5.58. I believe it was 7, so.
Oh, wow, yeah.
Yeah.
So.
Nice little
Alright.
shortcut there.
All right, I don't see anything in the chat.
Yep.
Yeah, nothing in the chat. So, all right, I'll make a decision then. I'll show a couple of the first steps, and then hopefully Zach can do.
You might want to email that to me as well.
Oh yeah. So what we've been doing is like essentially I don't know. Okay, cool. We'll show this. So yeah, the stream software I'm using, I was afraid it wasn't going to show if I took off the window. So this is 159 pages. Oh my goodness. 159 pages of stuff. So maybe we don't put this all in somewhere. Let me think, because that's a lot of information.
That's for hydrogen, right?
Yeah, this is for hydrogen because we didn't know the. So, all right, hold on. I'm gonna change something here because we're gonna make an assumption here because that's insane. So we're gonna go back to the pressure, and we're gonna choose. We're just gonna get rid of all these, and we're gonna get rid of the interval. We're going to just choose like 114, so 100 psi chamber pressure. We're going to just make that assumption because it's, like I said, with our fluid system components, that is probably accurate. So we'll just make that assumption. Oh crap, I forgot to hit save.
And some of you guys that are new to kind of performing these calculations, and it's like, oh well, why is he just throwing numbers in there or making assumptions? Well, the way that all of these equations and I guess physical relationships between the different properties of rocket engines, sometimes you have to make a leap of, okay, well, I think this is going to look like this, or our chamber pressure is going to be 114, to kind of, I don't know, give yourself a focus so that you can kind of build off of your calculations. And the way that the things work, you have, say, 2 unknowns here, 1 unknown over here. If you can kind of guess what one unknown might be, you can back solve into kind of figure out what the rest of your engine is going to look like, and still have pretty accurate results.
All right, so this one, changing it to just 1 pressure, and that's it. We have only 21 pages of information, which is still a little hefty, but it's a lot more doable.
Yeah.
So what we'll be doing is we've been saving these PDFs so that we have note of them later. So it didn't bring up the save location, which is kind of good because you don't need to see all my stuff. So we're gonna call this, I'm gonna call it just like first order GOX, gaseous oxygen, H2 output. And then we kind of been saving it into our budget by prop page here, our little drive folder. So just upload a file, go to find it. So again, you can't see where I'm finding it, which is fine, but just believe me that I didn't already do this already. So where is it? There we go. All right, so it's uploading, and there it is. So this is just for our sake of putting things in there to make sure that we have it correct. So let me see if it's going to, okay, it's going to break. Things are breaking. We're going to go over here, and yeah, so that's going to break. We'll do that instead. You might just have to flip between tabs.
Yeah.
Actually, wait. You can, never mind. So I keep looking. I'm new to streaming, so I'm like all over the place. I'm looking down here while the camera's up there. So he's going to start inputting those values. So essentially, I will show it first. I'll just flip between the tabs. So what we're going to kind of go, and then he'll take over, because I was trying to figure out a way to do it so that you can, but we'll just flip between the tabs. So I will pull this guy over to here. I think, yes. So, okay. So we are going, yeah, okay, cool. Did a copy, make a copy of the NASA CEA stuff.
We'll do that for hydrogen.
All right, so this is going to be called the NASA CA H2. And then essentially I'm going to just get rid of all this information right here. No data, and then we might do a second order calc if we like narrow in the problem a little bit, if we want to get a little bit more fine-tuned information. So he's just putting in right now, Zach's going to be putting in the OF numbers that we've got. So here it was all of these values here, just broken up in quarters. So
yep. I feel like there's an Excel hack.
There was definitely what I did is I typed in the first one and did equals plus or equals the first cell plus 0.25.
Yep.
So
not well versed in all those hacks.
All right. So I'll show this part. I think it's coming up right. Okay. So starting off, we have here is our NASA CEA output. And so at the beginning, it gives you all the inputs that you put into the system. So here's the OF ratios that we wanted. We chose our selected fuel and oxidizer. So we have 100% weight of H2. So it's not like, this program allows you to do different percents of fuel and oxidizer, and we're not doing that. That gets fancy. We're not really concerned with that. So 100% H2, 100% O2. And then we start here. So our pressure is 114 psia, and we have an OF ratio of 1. So there is 1 mole of fuel for every mole of oxidizer. And then it starts outputting our pressures. Or sorry, yes. Or, well, everything, just data in general. So we have the chamber, throat, and exit columns, and we have all this really, really nice data. So, for example, we have the pressure in bar. We have the temperature in Kelvin for both the chamber, throat, and exit. We have rho. We have H, or is that's enthalpy, and I think that's internal energy. Yes. See, I wish they would maybe give me give me a little bit more information than just the letter, but then we have down here some useful things. We have gammas, so that's very important. We have the sonic velocity in meters per second, and then we have the Mach number in the chamber and the Mach number at the throat. Like I said before, 1.0 is the number. That means we have choked flow. And then the exit Mach. And then you have mass fractions for the byproducts. So yeah, and then that's essentially that column. So what we're going to do is we're going to basically, he's kind of doing it right now. We're going to take, we're concerned for the chamber. In this case, we're like looking at the chamber temperature, because the chamber temperature is going to be used for a different calculation later. Oh boy, what is going on? That was the, hold on, it's the ISP. Oh, hold on. Oh wait, yeah. So hold on. So here you take this number.
Right.
Yeah. Sorry about that. I was like, whoa. I was like, that's a massive. I was like, that's not right. So then we do this divided by 9.81. Enter. Oh my goodness. Why is that still so high? Hold on. Wrong thing. What is going on here? Why is that like insanely high? I bet you we did something wrong. Something went wrong, because that's an absurd ISP.
Well, isn't hydrogen known to have a very high ISP?
I know, but
Isn't that high?
It seems like 368 seconds is. I mean, hydrogen can get pretty good, but I mean we aren't doing
What
well.
does Rocket Lab say?
Yeah, so this is how the stream is going to be. I hope none of you were expecting this amazing professional stream where literally some engineering students kind of just throwing stuff together.
Yeah.
So there's going to be some issues. If you guys see us doing some things blatantly wrong, please say something because this is going to be rough. Yeah, so somehow our ISP is insane.
With LOX and hydrogen, it's 363.
It should be a little bit more with gas. I think that's how it works, because you have liquid fuels that need to go from the liquid phase to gas to burn, but we're just injecting gas, so it might be correct. I find it very hard to believe.
If there's more experienced people watching this live stream, please say something in the chat.
I think I might have accidentally. There might be an input that was incorrect.
Yeah.
So you should. Okay, we're still good. So the pressure value 114. We have fuel, oxidizer, our random OF ratios, exit conditions 5.58. Yeah, I'm not sure what's going on here. Oh, you know what? So the other thing we can do. Let's go back to. Oops, no. Exit conditions. So now, so that we made an estimate based on the chamber pressure, which is 114. Mm-hmm. So we can populate the PCPE, this guy. So we can just say 114, like 114 divided by 14.7. So 7.8 is our pressure ratio. 7.8027. This should maybe change some stuff a little bit.
Yeah.
I think. Like I said, as I had done this. I did this before, and now I'm doing it wrong. Interesting.
doing that? There's an extra column. All right, now I'm just botching it. All right, give us a moment here. Somebody's gonna probably dump in the chat and be like, yo, what's going on?
You can save the CEA as a text file, import to Excel with space delimiters, which will put all values in cells. You can then use filter to select only what you want, like all ISP values. Okay, let's see. Wanna try that?
I've done that before, and it works, but for some reason my computer skills are poop. So, so if you want to try that, we can.
Yeah, let's
export as. Go back here.
All right. We're gonna try the suggestion we just got in the chat. See if we can simplify this process a little bit more.
Yeah, so here, this is, I've looked at this before, and so, what did he say?
Text file.
Okay, that's what.
Space delimiters.
Save as, why does it do this? It's like, always says, like, save as a web page.
Copy and paste it into, like, a sticky note.
That's literally what I'm going to do. Notepad.
Yeah.
All right, sorry you can't see this, but I'm saving this as a text file to drop into our thing, our Excel sheet. Man, for some reason I'm like stressing out right now.
It's only rocket engine design, no pressure.
I know. It makes me cringe. All right, so we're gonna upload a file. We have this. Oh well, can you?
I use the output link.
I already have that open, don't I? Oh, I'm an idiot. Wait, why is it still HTML single file web page? Okay. I think either one kind of works, but all right. All right. Well, just because, you know, I've done this, I did this before, and it took like a while to get it to work right because my computer skills are probably really bad with Excel. I think we're going to brute force it, and I know a lot of people are, no, don't do that, but this is the whole point. We're kind of, even though we're like super amateurs, we're kind of also demonstrating that if you just brute force it hard enough, you can make a rocket engine. That's kind of the end goal of this, is just absolute brute force, and it'll work eventually.
That ISP versus OF ratio graph looks like it's having too much fun there.
It's just vertical. Yeah, I don't know why this happened. I had it on really good with here, right? Because I had this guy going, and that made sense. That I don't know why it broke.
Let's see.
That's very interesting. All right, I think I maybe can figure this out. I would hope so. Exit conditions. We're going to get rid of the supersonic error ratio. I wanted to address your other thing that you probably have to trim down the nozzle to avoid flow separation. Yes, you are 100% correct. But I don't know if that's what we're going to do. We might just wing it. I mean, we could always just sand the nozzle down.
Yeah.
It's just like, it'll work. It'll be fine. We'll figure it out. We'll play around with some of the numbers and.
Yeah, let's see.
So. All right, that looks like a lot better. 2009, 02. I think I fixed it.
Okay.
2009, 02. Do you want to do this over again?
What do I need to change?
I'm just gonna like type 2009, 02.
Do it.
All right, 295. All right, things are fixing themselves. Okay. All right. So we'll change this guy. PC is 100, and this guy is 7.8027. 7.8027. Yes. All right. So can you go back and get the chamber temperatures again for this? Oh, my bad. You don't know what I'm doing because I don't have anything. Save as.
So do you update only the chamber chamber temperature?
No, you're gonna have to update everything.
Okay.
Sorry. I'll just overwrite this first order thing.
Here's the output link. We're gonna have to learn exactly how he's doing that because.
All right, so the new file in there. Your storage is full.
All right. Let's see. Did you just delete the old H2?
Yes, that should be the new one.
Nice.
Let's see, scroll. Yeah, that's a new one.
Yeah.
All right.
All right.
So
I guess while I'm doing you want to dive into maybe some of the component study?
The component study. Yeah.
All right.
Oh yeah. So
what do we got?
Oh, like for the engine itself, like the particular engine. Okay, yeah. I'll jump over to some of the basic stuff. We'll go over to the whiteboard, and I'll try to draw some things.
The whiteboard came first for a second there. Okay. All right. Hopefully, yes, you can see me. So. Get rid of all this stuff. Do you have a better black marker? Yes. Okay. So, in order to get this thing to work, the biprop to, what's the right word? To be feasible, we had to make some really, not necessarily gross, but really simplification of the engine itself. So essentially what we thought we could do is, this is almost entirely a McMaster car engine. McMaster and some Amazon stuff. So what we were kind of thinking of for the basics of the engine design is we're going to do an ablative engine. So ablatively cooled is just going to have a chamber liner that burns away, and the throat, or the nozzle itself, is going to be made out of a glass phenolic, which will probably burn away. And the engine's not planned to be run for a while, literally probably about 2 seconds, to hopefully get some data, get some values, get some pictures, videos, and demonstrate that you can do this for roughly $500. So the engine itself is going to kind of look like this. We're going to have a really thick. This is all cross-section view, so this is going to be a cross-section. We're going to have a really, really, really thick chamber. And this is all going to be aluminum because aluminum is very easy to machine with like a drill press, to drill with a drill press, to machine if you needed to do machining. It's a very easy material to work with. So this is our chamber. None of this is to scale or to anything else, and it's also crooked a little bit, but that's fine. So the next thing I'll highlight here is, so this is going to be our liner. So we're going to have a liner in there. And this is what's actually going to absorb most of that energy. It's going to burn away and hopefully keep the metal of the chamber, these here, intact. And, oh, okay, you know what, I screwed up a little bit. We're going to move this back. So the next thing is we're going to have also a little plate on the front that retains the entirety of this assembly. And then there is the nice Probably, you know what, I'll make it orange for the opposite ablative. Like, this is another ablative. So the nozzle is going to kind of look like this. Yeah. Yep. So that's kind of what the nozzle is going to look like. There's going to be an O-ring like that to keep hot combustion gases going in fun places we don't want it to go. The injector is going to sit on top of all this like that. And since this is a cross-section, we'll do some oversized impinging screen injector orifices. So, and then there's going to be one more plate on top of these, and we'll just make this estimation that essentially, not an estimation, but we'll just do this. So you're going to have, get some more colors here. You're going to have oxidizer, do blue for oxidizer, and unfortunately we'll do a little bit of red for the fuel. That is pink. That's a pink color. We'll do red. So right there is going to be the fun zone. This is where we'll have combustion happening. So it's just going to be an impinging string injector. And this is just all going to be aluminum. We're going to have cap screws that go and bolt this all together, coming from the ends. And we're going to have some graphoil gaskets for right here. It'll be a ring. And then we'll have another one there, and then this will just be the O-ring. And we're going to use RTV sealant to fill in some of these just cracks and crevices to add a little bit more of a barrier to all that excessive heat. So essentially that's kind of the design we're looking at. These are all parts that you can buy kind of on McMaster. So these will be discs, aluminum discs, about 1/2 inch thick. And then this thing's, I think, what is it, 3 inches? Or what's the diameter, 2 inches? 2-ish. I think it's about 2.
You're talking about
Just the whole OD.
Oh, 2, yeah, you're right.
Yeah, okay. So this will be, you can get 2-inch diameter discs that are like 1/2 inch thick on McMaster. And then this is just we're going to get a 1 foot length of 1/2 inch wall thickness, 2-inch OD aluminum tube. And then you can buy, and then the Garolite is that ablative material that'll be on the chamber liner. That is also a McMaster part. And we're going to get that, I think, in 1/8 of an inch thick, possibly. I think it's an 1/8 of an inch thick. So this will be 1 inch OD, 1 inch inner diameter of chamber, 1 inch OD of the Garolite, and then a ID on the chamber here. This will probably be 0.75. That'll probably be the chamber diameter, and then we'll have some length. And then here's the commercial nozzle that we'll be buying for the engine. So that is basically what's going to be happening. Kind of basically design. Like I said, we did some preliminary design work and figured this is what's going to be happening. Oh, I think we froze. Did we freeze? Oh man. Oh man, that's not good. I don't know why this keeps freezing. So I'm sorry about that. I think we missed a ton of information there. let me.
Let's see, anybody watching, if we're on Frozen or if you missed any important information,
Okay.
just let us know.
Yeah, I'm not sure about what happened there. Interesting. Okay. Well, so that's I don't know why this thing keeps freezing up. There's I happened to look down and it
You
didn't
said
look.
audio is working.
Audio's working?
Yeah.
There's no video?
No video. So it sounds like they heard everything you said, but the diagram's there now, so I think we're good.
Okay.
Yeah.
Yeah, I'm sorry about that. I don't know why the video keeps freezing. It's probably because we have a bunch of junky webcams that we're using, Amazon webcams. But so I'm sorry. So hopefully you saw maybe the beginning part, but here's kind of what's going on with the engine. We have fuel and oxidizer coming through an impinging stream injector. An unlike doublet is what it's called. This will be at some angle, maybe 45 degrees, somewhere in 30 to 45 degrees, impinging with each other. And then that'll combust, and then you'll have the actual rocket engine part of it, where it's combusting. We're going to have Starlight liner for the chamber, and this will be, the chamber diameter will probably be about roughly 0.75, because this is material, these are all diameters and materials and dimensions from already existing things on McMaster, things that you can buy and you don't need to machine. There's none of this engine you need to make on a lathe, absolutely none of it. These are all parts that you can buy from McMaster, and as long as you have a drill press, which you can get from Harbor Freight for $100-ish, $150, you can make this engine. And that was the whole goal with it, is we don't want to have to do any machining work. We want to do this as cheap and as easy as possible. There is one part where we have this, so where we're at right now, we have access to this little tiny micro mill. It's probably literally about that big. It's a little tiny thing, and I think it's $350 for that little micro mill, and neither one of us bought it, but we're going to probably be using that to make one channel in the engine, which you can file. If you have files, you could work a file and actually create this notch that we're going to make. But we're going to just use the mill just because it'll be a little bit easier. And but everything we're doing here, we're trying to do with the concept and the idea that you can do it for really, really cheap, or at least relatively cheap. Rocketry and engines and bi-prop stuff is not a cheap endeavor, but we're trying to make it as cheap as we possibly can, because that's the goal. So this is the engine concept as of now, and we're going to get a little bit more in depth with it with the CAD that we're going to be working on. And so, but we got to do the actual engine design part first. So eventually, once we'll have some of these. Zach's almost done with the values here, and we will be able to bring you back over to the ISP versus OF versus temperature graph, and then we can start extracting data, and we can go look at things like gamma and all these other values that are associated with that specific calculation that the NASA CEA did, and we can use that information to get more of these dimensions here and narrow in on the design. So are you ready? You're good? All right, we're going to flip back over to again.
So, wow, we're having some serious problems now. This is really frustrating. Why it keeps freezing. So we're back over here, and we have some data now.
We do.
So
Probably. Actually, no, that's fine.
Interesting.
Yeah, so it looks like our.
I mean, this is good. This is
Yeah.
like
I think that gives us what we.
this is like, this makes sense. Like before, it wasn't really making sense. So, so here's, based off of our estimates. I gotta change the date on this too. Based on our estimates from the NASA CEA stuff, this guy right here, this is roughly what we'll be looking at in terms of ISP over different OF ratios. So we're probably going to be maxing out right about here, right? 314, 2.5.
Yeah.
So because we're running at a really low chamber pressure, according to our one source, it says like liquid hydrogen, liquid oxygen the ideal OF is somewhere at around 3.5, which is like not our case because we're kind of not as good of an engine, not good at all. So a pretty bad engine, but bad engine in terms of performance and all these other things, but fun and good for our purposes, I guess. So we're looking at an OF ratio of 2.5 is about our max value. So now we have a number. We have 2.5. We can come over here and we look at 2.5 and we can go on this plot and say, hey, we're going to be at roughly 3,000. I would say 3,750. Why do I keep doing that? 3,838 is the number.
Yeah.
I keep doing that. I keep looking at plots and trying to estimate things. Yeah, so degrees Fahrenheit. And to convert that, so our calculator thing is going to use Rankine, and Rankine is just degrees Fahrenheit plus 460. So we maybe make another tab there or something that does like, oh, wait, more.
Oh.
Okay. Oh my goodness. Oh my goodness. Okay. I'll do this. We'll insert one to the left. Oops. Oh my gosh. I can't type. R. And we'll do this guy plus 460. And oh my gosh, autofills too. So
Nice.
there we go. There is all of our chamber temperatures in degrees Rankine. And yeah,
Cool.
cool. So could you send me that PDF?
This.
Or sorry, not the PDF. The Rocket Lab PDF.
Oh,
Like,
yeah.
could you just could you just dump it into the OG budget by prop? Okay, so we're gonna probably soon here get into, now that we did a little bit of NASA CEA analysis, we're gonna get into doing some of the actual calculations and trying to figure things out. This is where it's going to probably get really spicy, and a lot of mistakes are going to be made at first, and then hopefully we'll figure it out. Hopefully things will get unscrewed and done correctly. And if you see anything that is blatantly wrong, please send something into the chat. Like I said, we're pretty much amateurs at doing this, and not just that, it's also, I don't know, I've never done a live stream before, so I'm a little bit anxious and nervous and probably more likely to make mistakes and embarrass myself.
It's the process of learning.
But we're here, this isn't meant to be a professional broadcast on how to do a rocket engine. It's meant to just be fun and show that you can do these kind of things if you have the determination and a little bit of money. And yeah,
Cool.
that's kind of the whole process here. So, alrighty, did you drop it in here?
I emailed it to you.
Oh,
it
you
wasn't.
emailed it to me.
It was being not fun.
Alrighty.
Yeah.
Yeah, there it is. Nice. All right, so we're also thinking about making this whole drive, and maybe not this guy. I'll move this. That's something else. Making this and some of the data we get from here, from these calcs, and also data from the test, hopefully.
Yeah.
We're going to probably all put it in this drive and just make it that anybody can view that information if they would like, and kind of see how things are done, or try to organize it a little bit better. Hopefully that it's useful. All right, so I'm gonna drop that in there. We're going to go back over here. All right, so what I'm uploading right now is the PDF for the how to design, build, and test small liquid fuel rocket engines. And you're going to say, well, liquid fuel, that's not what we're doing. But everything in here is very applicable to what we are going to be doing. So we're going to open with, we're not going to open with. So yeah. There it is. I'm just going to drop it in here just so that we know it's there, but I might open it up in the other link because this is a little bit better to look at, I think.
Yeah.
There we go. Boom. So this is the PDF. This is how we're going to design the engine. So this is a book that was published in a long time ago, 1967. And some guy took the book, and essentially made this nice PDF that is up to date with text that looks nice, and scanned in some of the plots and information. But it's very satisfying to look at. It's a lot easier to look at than the original. The other one is a HTML website or whatever. That's kind of gross, but useful still. But this is literally everything we're going to need, and it even goes into some of the fluid system stuff. So this is all liquid. A lot of stuff they talk about here, so it's liquid fuels. This is actually a gas pressurized system for gaseous oxygen and a liquid fuel. So this is a really useful tool, at least for amateurs and starting doing your own stuff. Okay. So we're gonna so it goes into some of the theory behind a typical rocket motor and a de Laval nozzle, the schnoz. Yeah. Okay. So what we kind of did, and what we're kind of following this. It's a logical process in terms of designing the engine. We kind of have this niche that we want to fill. We want to do this specific task. Now we kind of are into the propellant choice, which we kind of looked at hydrogen because we can get it. There's other books and resources that I have that goes a lot more in depth into the design process and those figuring out what you're trying to achieve, what mission you're trying to achieve. In the case of like a full-size launch vehicle, it's like you want to achieve this delta V, you want to do this type of mission. Here is like these engines, this kind of process. So we're a little bit looser than that. It's kind of how cheap can we make this, and what is available to us. So, but we're kind of doing the same process here as this book. So we went through kind of a little bit of the basics here, and then we chose a propellant. Here they have a nice table of different propellants, combustion pressures, mixture ratios, flame temperatures, and expected ISP. And I would have liked to have done a liquid, a liquid bi-prop. That would have been fun, but I don't know if it's really achievable for under $500. Maybe one that's really, really bad in terms of performance, but you want to get that rocket feel, then it's going to be a little bit of money. So I already did a gas liquid bi-prop before, and it ended up being a few $1,000s because I kept buying more things. So this is meant to not do that. But yeah, so here you have the same kind of plots, right? We didn't do this plot, but we have this guy down here, mixture ratio and flame temperature. So we are not using oxygen alcohol or oxygen gasoline, but our plots kind of mimic what this is supposed to do. So we are, so like literally the first thing we're going to be going after is, if we go back to the budget bi-prop tab, we have an ISP versus OF. And so you have this guy right here, which is the holy grail. That is super important. And we can, right now we don't know the thrust because we could assume, we could say, hey, we want to make an engine with 10 pounds of thrust, and then boom, you got the ISP, you got the thrust, and you can find the total propellant flow rate. I think this is where it's going to probably all fall apart, but I think we're going to try to find the total propellant flow rate based off of this, because we know this diameter, which is so we know that nozzle, we know how much flow we can get through there. So I think if we do it that way, it'll work, and that way we can then find the total propellant flow rate from the nozzle, and then backtrack out what the thrust will be. I think that will work.
Yeah.
It probably
see
won't. And if it doesn't, then we'll just make some estimates and say, hey, we'll maybe do
Yeah.
10 pounds of thrust or whatever. But like the one guy noted in the chat, it could get a little bit interesting because we're going to have flow separation on the nozzle, and which is I think is entirely possible. But you can only have so many things. You can only have
Right.
so many things without blowing the budget. So I think we'll try to see if we can do it with this. We'll see. Yeah, I'm thinking it'll work, but I have to like pull up some equations and think of things. Maybe some NASA information. Man, this is stressing me out. I don't know why. Okay. Yeah. Okay. All right, so actually we'll go here. So we know this is the column, right? We want this guy. We're interested in this column because that is our, as of right now, our highest ISP, and then that way we can find the OF ratio. And we know temperatures and we know some other things. And now I can go back to this. So we know what, 2.25? Yeah, or 2.5. So we scroll down and we get to 2.5. So 2.5, this whole thing right here, this is this is the information we want. So some of the values that we can grab. So we'll go here, and this is where the engine design tab will start being populated. So we have from the NASA, oh gosh, no, not NSA, NASA CEA. They're not, oh my gosh, I can't type. I can't type at all. Okay, from the NASA CEA, we got parameter, we have value, and we have units, just so we can keep track of stuff. Even though I would like to do this in Python, because Python you can use libraries, but I am not good at programming, and it will take multiple days to get anywhere with this if I do it that way. So this will work. Actually, I like making everything look nice, and it doesn't really matter, but if I don't do it this way, then things go bad. If I don't, I just feel like I need to make it look nice. Okay. So now this is where we'll make, this is like our input tab, or input box of information. So we know a bunch of stuff because of the NASA CEA. If we go to here for H2, we know a bunch of stuff here, but then we can also go to here and grab a bunch of information. So information that I will put in here. So we have the O to F. We have I just lost my train of thought. Wow. We have the O to F. We have pressure, the chamber pressure. So we'll call it PC, and that is, we'll do it in PSI. We'll label it as PSIG here. It'll be 100 PSI. Our OF is 2.5. No units with that. Our chamber temp is going to be in, not G, not that either, R. Sorry, my keyboard is over here and I'm looking at this screen, so it's kind of hard. We know that guy is this. Well, actually, do this. We'll do this. Oh man. Oh god. Okay, no. All right, I'll do that later. Try to make it look all nice. Okay, so we have chamber temperature values. Oh, ISP, that's the other thing. Oh, man. I'll put it here. ISP is going to be, what was it, 3? I don't remember, and I can't remember anything. 314.37. And that'll just be in seconds, S. Okay, and now we will do other things. Gamma. Other useful things. So we come to this guy, and we have all this stuff. We have gammas. So we're kind of interested, I think, in the chamber. So we're looking at the chamber because, like, the ISP, or sorry, the ISP, the gamma is changing over the course of the chamber, throw, and exit. I think we're going to work with this guy. We're going to work with 1.229 as our gamma. Even though it's changing, we're going to make the assumption that it's not changing. I think we're going to assume that is the gamma. And that's just the ratio of specific heats. The Mach number. Wow. Is it really going to be going Mach 3 at the exit? Holy crap. Okay. That's going to be spicy.
Yep.
All right, so then we have all of these fun numbers. We got all these nice things. Coefficient of thrust, AE, 8. Yep. Okay. I don't even know if we're going to really... Well, we're going to need the 8. No, yeah, we are. We're going to need the AE to AT. But we're not going to need... I don't know if we're going to need C star. Because we're doing like this this guy here. I don't know actually if it goes into some of those... I think there's L star, but I don't know if this thing ever goes into C star related information. There's L star. I don't think so. No.
Yeah, I didn't see it.
So this is literally as basic as you can get it. This is going to be, yeah, so yeah, that's actually a good idea. Could you make like the chamber design stuff? So I'll make another one here that's from NASA CEA. Okay, never mind. I'll just do, nope, I won't do that. AEAT. Let's see. Which is interesting. It was the same. Excuse me. Then just pull out the speaker or the mic.
Yeah, so for basically everybody watching, just kind of a little idea, just to kind of solidify what exactly we're doing. We're basically just going through this Rocket Lab PDF. I'm looking over there. And just kind of basically taking some of these equations that it gives us, and we have these characteristics from our NASA CEA, and we're basically finding out exactly, okay, how much volume would we want in the chamber, how long should it be, what's the diameter of the chamber should be, stuff like that. And this is important because it determines basically how long your propellants are in there mixing. And as Dylan was kind of mentioning earlier, when those propellants collide, they atomize, turn into like an even finer like mixture of oxidizer and propellant. So this is really important in terms of like, you know, whether you're actually getting choked flow or not, and how much thrust you produce out of the engine. So it's not exactly the most exciting thing to watch, but it's an essential part of the engine design. And what a lot of engineers will do usually is they'll make this into like some kind of Python calculator, or put it into Jupyter Notebook or something like that. But for the sake of simplicity and for all the amateurs out there,
I think we're just special. The company we work at does a lot of programming. Like all of the mechanical engineers are kind of almost expected to be able to do some amount of programming.
Yeah.
We're interns, so it's not like we're not like I do some programming, but in the real world, if you work at more traditional companies, I feel like I don't know what Aerojet Rocketdyne does, and I don't know what ULA and SpaceX and all these other places do. But at least in other experiences I've had, a lot of the this is going to sound awful, old timers, Excel is the go-to thing. So, yeah.
Which it gets the job done.
It
Not
works.
bad.
Yeah, it works. So, yeah, but okay, let's keep grinding away here. There's going to be mistakes made left and right, but we'll be fine. So I'm going to try to figure out how I want to do this calculation. I'm going to look this.
Our chamber diameter is, so I guess some of the way that we're pulling some of these values as well is, as Dylan was mentioning earlier, this is basically a McMaster engine, or like Amazon, stuff like that. And our engine, in terms, or I guess as far as cooling goes, is going to be ablative. So we're basically going to have like a cylinder of, like a hollow cylinder or tube of garlite inside of this aluminum cylinder, and as the engine burns, all of that stuff is going to burn away with it to basically get rid of all of that heat. So our diameter of our chamber is basically going to be whatever the inner diameter of that garlite tube is.
Well, actually, here, can you move? I want to have the NASA CEA stuff that we grabbed from CA. So
right.
yeah, could you bump that down? I'll make this look a little bit better in a second, or not in a second, probably at the end of this. I'm going to just add this little buffer here so it's easier to look at. Yeah, that's better. Okay. Oh, no. No. Come on. There we go. That looks better. So, this is like our NASA CA values. Oh no, please don't do that. Make this like box like light gray or something. I don't know. That kind of looks nice to me. Looks a little bit easier to differentiate the text from that. So this is all of our essentially inputs, or at least the kind of a critical information that the CEA gave us. The AE to AT is probably not going to be important because, or not important from them, but I think it's identical, right? Is that the value that we calculated? 5.58?
Yeah.
Is it really?
Actually,
I don't remember.
Yeah.
Whatever the value that we
I know the gamma is like spot on for what they tell us to assume.
Oh, almost. Yeah, 1.2 is pretty close. So, but yeah, I don't know. Sorry, I'm like all over the place. My train of thought is kind of going, and I'm not really articulating it well.
Let's see.
So, I'm going to kind of talk about what I think is the method I want to do, which is this guy, the mass flow choking. So I was going to kind of grab some of those parameters that they gave us and make some assumptions and throw it into this guy. So this m dot. So once we find the absolute maximum flow rate, so that m dot from this value, right, from this right here, this calculation, that equation, I mean, once we find that m dot, that is our mass flow rate. Whatever because the rocket engine isn't a rocket engine unless you achieve choked flow through the nozzle. And once because that's what we're shooting for. We're shooting for choked flow, m equals 1, Mach equals 1. And this equation can be simplified now into this. And we have, from the NASA CEA, things such as the area, the total pressure in the chamber. Well, this is where I'm like not entirely sure what I want to do here yet. I don't know if this is going to be. This is probably going to be the total pressure at the throat. I'm not sure. We have that value, but I'm not entirely sure the total temperature at the throat. And then we have gamma, which we can find also at the throat. I think I might have to change that as well. And then R is the gas constant, but that's going to be the specific gas constant, I think, right? Because remember we were talking about, yeah, I think it is.
That's true.
That's R. This R is the specific gas. It's not the universal gas constant. It's the specific gas constant. But like I said before, luckily we have the. Oh, do we not have it? Yeah, screw it. I'll figure it out. We'll have somewhere in here, or maybe not in here, but we need to find the molecular weight of the product. So you can divide the. Is it R equals? Yeah. So okay, yeah. This is where it gets really stupid. The universal gas constant is in SI units is 8.3145. But for our purposes, we're going to have to use 1544, and it's actually in here. So here's, where is it? Oh gosh, I lost it again. I thought I just saw it. Here we go. Wow, I was almost on the page exactly. R is the gas constant given. This is the most confusing thing ever, but whatever. R is the gas constant given by R equals R divided by M, but then R is also the universal gas constant. So this should be like RS for specific gas constant, and that should just be RU for universal or something. I think that would make sense, but whatever. I didn't make this document. So we got to find our own gas constant, which is given by the molecular weight of the hot gaseous products. So this guy, they just said, is about 24, which is also not useful, but we're gonna put that number. So that's why I said it was bad. Like, look at these units: 1545.32 foot-pounds per pounds Rankine, and that is not fun. That is not fun at all. I think that's even simplified. I think it's foot-pound force over pound mass Rankine, if I remember correctly, or yeah. It's not good. It is a not good unit, and it makes you want to cry a little bit. But this was really awful to get working with Python, because you can do the AstroPy units library with Python, and you can input all these units, and it goes ballistic because it's no idea what's going on. And if you enter one thing wrong, it can't simplify it, and it took me an hour or so to figure out what I did wrong. But Excel does it for us without units. So we just, but that's the problem with Excel, is you don't have this unit tracking, I guess you can call it unit tracking, where you just are going and going and going, you're making mistakes, and you don't know where you made the mistakes, because unless you're writing it on a piece of paper doing the dimensional analysis to make sure that everything you're doing actually reaches the units that you're looking for, you run into, and that's what we're probably going to run into a couple times here, because we're going to do a couple things wrong, and it's not going to make any sense. And the only reason it doesn't make sense is because I have done this before, and I know what doesn't look right. And that's the hard part about a lot of this. Is the first engine I ever designed, it took me literally a few weeks of what we're doing now to get it to work right. Because I think I was in 12th grade, so I had no college educational experience at all with fluid mechanics and dynamics and all this other stuff. So I was using this document, and I still, like, things like this were just confusing me. So it's don't be frustrated if you do this and it's confusing, and if you've never done it before. It's just, that's the overcoming all of that confusion and all of those issues is the best part of it. It's the feeling once I got it to finally work and things made sense was like the best feeling ever. So, and then especially when I got to a hot fire. The hot fire was, it was awesome. It was great. The engine was kind of in terms of performance, but it was really great to have all that work. It took me about 5 months to go to a hot fire, because I made fuel tanks from scratch, high pressure fuel tanks from scratch, and hydro tested them and welded everything. And yeah, that was a lot of work and a lot of money. This is not going to be that. It's going to be a lot simpler. I'm really good with machining and fabrication and those kind of things. The math side of things always ends up screwing me over. I always end up making easy mistakes. Oops, kick the table. So, yeah, I'm gonna get back to this. I'm gonna make some universal. So from the NASA CEA, under here, I'm gonna make a constants tab. Constants. Oh. Is there any comments there in the chat about anything? I don't know why I just did this.
I don't have anything yet. Those of you watching, if there's any questions, don't be afraid to put something in the chat, or any suggestions you might have for an improvement on how we're doing something, we're open to anything. Let's see here.
And like I said, this is all going to be scary units. You have feet per second squared. We have gravitational acceleration in feet per second squared. Everyone's going to freak out and be upset, but this is America. No, it's just unfortunately that's the case. We have this document, and we want to follow this document, and everything in here. It was written in 1967. Everything in here is going to be an imperial. So we're going to do the universal R, Uni-R, 1545, point something, 32 foot pounds divided by pounds R. That's awful. That is awful. Those are terrible units.
Okay.
What other constants? We have R, universal gas constant. What other constants are we going to need? I guess it doesn't matter. We'll figure it out. We'll plot it in there. So he's got some things going on over here. So this is, right now we don't know the L star. We're trying to figure that out. He's calculating based off of our already known already known nozzle information. That's what Zach's working on. Zach's kind of, here's the knowns from it. Oh yes, okay. Do you wanna talk a little bit? We'll have you talk for a second about what you have in there, the knowns. Why you wrote these knowns? Because if we keep going, we'll forget.
Yeah. All right. So then, to kind of touch on what I'm doing over here with this chamber design sort of thing, kind of like how I was saying earlier, we're trying to find the volume of the chamber, how long the chamber should be, and essentially what our characteristic length is going to be. So what exactly is characteristic length? Well, it's basically a measure of how well your propellants mix before they actually enter the nozzle, or I guess how well your propellants mix and then combust and then enter the nozzle. Now, ideally,
it's hard to explain. I don't know if that's the right explanation. It's
Yeah.
kind of correct, but
yeah,
like I said, we're amateurs. We're not really good.
Right.
At what we're doing. But you want a certain length of chamber to make sure that all of that burns to its full capacity. You do not want byproducts. You don't want to overdo it, because if you have a too long, let's say you have a chamber this long with like a diameter of that much, a chamber diameter like a half an inch and then 2 feet long. Well, now you've burned all your propellant up here. And as you get down, now the gas is cooling. Your gas is cooling, and now your performance, your efficiency, everything just craters.
Yeah.
But if you're too short, then the exhaust still has unburnt fuel and oxidizer in it.
Right.
So what we're trying to do is the L star is get it into, there's a range. It's like, I think it's between 50 to 100 inches. L star, it's not an actual inch value. It's a, what's the right word? I don't know what the right word is. It makes no sense if you look at that. You're like, wow, the chamber's 50 to 100 inches long. That makes no sense.
Right.
But L star is
you can think of it as a measure of how well the propellants mix.
Yeah, kind of.
Yeah.
That's not the, I know.
Yeah, it's not exactly a good way of explaining it, but to kind of simplify, to oversimplify, we'll go with that rough definition for now.
Sure. So I think for us, we're going to try to shoot for 50, because we have, it's going to be probably under, I think, a little bit, but we have, we're now, this is another constraint of the design. We're going to be buying material, and the material we're buying only comes in the chamber is thick, like the chamber, the chamber is 2 inches in diameter with a ½ inch wall thickness. That's a lot of material. So it's expensive. So an aluminum, it's essentially a giant aluminum pipe with a really thick wall thickness.
You kind of have to think, like, in order to make this like a very cheap engine, you kind of have to work with what you already have. So that means like going on to McMaster, looking at like basically what kind of pipe sizes they have, and going like, all right, well that's pretty close to what like our chamber volume is, or our chamber length should be. So that's
So in our case,
something like that.
Where he put down 6 inches for the LC, which is the length of the chamber in his knowns, and 6 inches is given because we're buying a 12 foot, oh my gosh, a 1 foot length of aluminum stock from McMaster, and we can split it in half in case we make a mistake and have to scrap a chamber. We can make another one and still have material. So
Yeah.
and unfortunately, that 1 foot length of aluminum is $52, which is an astronomical portion of our budget.
Now,
It was 10.8% of the budget or something crazy like that.
And the main reason why it has to have such a thick wall, or the wall thickness is the way that it is because kind of, some of the preliminary design work that we had done with this was, designing that upper manifold for the injector can be really tricky if you don't want to machine anything, especially if you want to minimize basically leak paths where your combustion gases can go and basically blow up your engine. So
It's basically an over-designed engine in terms of factor of safety with over-pressurization.
Right.
Unless we have the most epic of hard starts ever, the chamber is not going to split open.
Yeah.
That's such a massive amount of material. We'll do the calculation. There's in our I keep pointing like you guys are seeing what I'm doing. In here they have a wall thickness calculation. It's down here. Chamber wall thickness, and we will do this calculation and show you how absurd our chamber wall thickness is. The working stress is going to be just stupid. It's going to be like a couple hundred psi, if that, when the material can withstand thousands and thousands of psi. I think I'm just throwing random numbers out there. I don't know these numbers off the top of my head, but what's going to fail first is that glass phenolic nozzle. If we have a hard start, that is going to fracture and blow out like crazy.
Yeah.
It's going to just break. But we shouldn't have any bad things happen with the metal, because that's the core of the engine. The metals, not necessarily the core. That's the exoskeleton of the engine, right? That's containing the ablatives and all these other things, and those aren't going to blow up. The ablatives will. The ablatives will burn away, possibly fracture. The glass phenolic nozzle might just break in half and chunk out. But that's fine.
They're designed to be expendable.
They're designed to be expendable, and even though it might be really hard to get the old burnt out insides of the engine apart and out of the engine, because we're going to put like RTV sealant in there, all this other fun stuff. This technically could be a reusable engine in terms of replacing the nozzle and the chamber liner. You should be able to reuse the engine again as long as the injector doesn't melt.
Yeah.
But we're going to be actually at a pretty cool temperature. I think that one calculated temperature was only 4,000 degrees. 4,000. Yeah, look at that. 3,830 degrees. The other one was at 5,000. Wasn't it 5,500 or something? Yeah. So we're actually pretty cool. Well, it's not really that cold, but the aluminum still melt at this temperature. But it'll give us a little bit of a margin in terms of length. It's not length. Oh my gosh, time. Give us margin in terms of its lifetime. Its operational lifetime. Maybe get an extra half a second out of the firing.
Yeah.
Before we could, I've debated doing an ANSYS simulation for the temperature, just to see how long it would take before things start getting bad.
Yeah.
Because this is almost like a mix of an ablative and a heat sink engine. We have a lot of material there to absorb this heat, and we probably can get a good 2-second run out of it. I think a good 2 or 3 second run, which will give us the data we're looking for.
Yeah.
To make sure that we actually designed this properly. That's the whole. That's again. That's a good part. That is a big part of it. So the last engine I built, I put no instrumentation on it, and it ran, and I have no idea how well it ran. It looked like it went okay. It didn't sound like it was okay, but it didn't melt. Nothing burned up. There is, from some of the videos, tiny little mock diamonds I think are visible at the exit of the nozzle, but it's unknown. This time around, even with this little guy, we're going to put a pressure transducer on the chamber and hopefully get a chamber pressure reading. And making other assumptions such as temperature or pressure, or not pressures. We get a pressure reading, and if we make other assumptions, we should be able to backtrack out of thrust. If we're running at the right OF, we're assuming we're running at this OF, we have this gamma, we have this, that, and whatever, and we have a tested, or not tested, but from the test, from the hot fire, we have a pressure value from the chamber. We should be able to say, hey, this was the theoretical thrust. We really wanted to add a load cell to it, but I don't think it's going to fit in the budget. And also we have to add some to get a clean value out of that, we'd probably need to also do flex lines on all of the lines coming into the engine, which means that gets a little scary because they're also a little expensive if you get the right flex lines. But then if you don't, you're using like polyethylene tubing or whatever it is. which could withstand the pressure we're running at, but
The concern
melt
is the temperature.
The
yeah.
temperature, it'll just melt. So, and then we'll have oxygen and fuel spraying all over the place. So we're probably not going to get a thrust measurement. We might, in the future, maybe make something. Maybe we'll modify it or something and make a video separate, like sometime way in the future. I'm not sure.
Yeah.
Trying to say, hey, we did get a thrust measurement from it. I don't know. So.
Yeah, an important thing to consider when you're designing all of this stuff is the testing infrastructure too. I mean, the plumbing, some of those fittings and stuff can get extremely expensive. So, you know, it's something you definitely want to keep in mind. And when we kind of get into more detail for the testing infrastructure later down, I guess later today, well, you'll see. I think the plan right now is most of it will be made out of something like wood, which, yeah, I mean, it's not exactly the best type of material, but
not ideal, but
it's the idea of the project is it's under $500, including the testing infrastructure.
Yeah, and it's gonna, at the end of the day, I'm not gonna lie to you, it's going to be more than 500 in terms of the total cost of the project. All of the hardware is going to be under $500. The only thing that's going to be more is the shipping to get it to your house. Probably, depending on your area, renting the bottles, the oxygen and the fuel bottle, high pressure bottles, and that's basically it. Everything else, we designing everything apart. Even there's like an Arduino we're using an Arduino to control it with a relay board for the solenoids, and also the Arduino will take in pressure data and will do some sort of function and scaling. But we'll get into that later. Even that's accounted for in this budget. And we'll go through the budget. Yeah. We did make it already. We kind of went through. That's the real cheese. We should have renamed that. Yeah, but we already kind of did that because we had an idea. We needed to kind of almost do this project without the design part. We did the material stuff. We did all the making sure that this is physically possible, financially possible. Now we're just kind of fitting the engine to the budget. Is I think the right way to say that.
Yeah.
We already have a budget bomb, bill of materials, a budget bill of materials with a budget bomb.
Yes.
That this is the old one. This is the new one. So we probably should just merge these. But as of right now, we'll show you that later once we make sure that this is good and correct. But yeah, so we'll get back into this, and yeah. What'd you do? You break it already?
I think I got some funky things going on because our L star is
19.
Extremely low. Yeah.
That's entirely possible.
Let me.
So the L star calculation that he's doing there is up here somewhere. Did I lose it? I probably lost it. Oh boy. Oh no. Oh, there it is. So it's the volume of the chamber divided by the area of the throat. Did you add the volume of the convergent section to the throat, to the total chamber volume?
Yeah, let's see. I think I might have messed that up. I'm looking for...
Yeah, so essentially what he's doing right now is we're trying to find just the L star. He's doing a little bit of a separate piece, and then I'm going to keep going with some of the flow rate stuff to find what our thrust is going to be. Excuse me. So what he's doing is trying to find L star, which is the volume of the chamber divided by the area of the throat. So he's got to find the area of the chamber, and that goes into the length of the chamber plus the convergent volume. In this little thing here, they tell you that for small combustion chambers, which is kind of us, the volume of the cylindrical portion of the chamber, the convergent section of the nozzle is 1/10 of the volume of the cylindrical portion of the chamber, which is an estimate you can make. He brought up the cone estimator,
yeah,
not even estimator, calculator, to find the volume of the convergent section, which is going to get us pretty close. So the this works for levels less than 75 pounds. So if it doesn't end up working, you can just say 1.1 times all of this and get the volume of the chamber. But it's kind of nice to do it in other ways. So he's doing a right circular cone calculation, and you can just the area of a cone you can just put into, or the volume of the cone you can just put into words into Google. Google has like calculators. You look up area of a cone or volume of a cone, and boom, it just gives it to you right there, and you can. So everything we're doing is like, again, not special. We're not doing weird things. We are using all of the public resources we can possibly come up with.
Yeah.
Yep. All right. Let me get back into it. That was a big tangent there. That was probably a 20-minute tangent.
Yeah. Let's see.
Got a phone was ringing or something. No. Okay. Oh, and then one last thing. I don't know if anyone would realize we have some rockets back here. So yesterday we went and flew our high power flights at Mojave at the Friends of Amateur Rocketry. So we got both of them back. Mine broke a little bit. His was good. He got his L1. I did not get my L1 because I had a fin break down here at the bottom on landing. It was 30 to 40 mile an hour winds yesterday. So, but his was successful because his is just super densely made. There's a lot of material there and a lot of epoxy. Mine has really thin fins, so the fin hit the ground on impact and broke, and that failed my certification. But I got the whole rocket back, and I actually got data. So I have a little circuit thing going on up in there that records data to an SD card. So one day on maybe here, or this channel, or on my blog, which is linked down below, I think, I'll post the data from that and the tests and a flight and doing like a flight report. So, but anyway, we'll get back into this.
Alright, let's see.
Okay, so, all right, I got this now. All right, I think I have a good idea. So we have these constants. We'll just put a little box around them. I think. Okay, we have mass fractions. Yeah, this might get spooky. We might have to do some
Okay.
chemistry here. Maybe.
That's better. Alright, so I was accidentally, the genius that I am, I was using the throat area as the chamber area, which is, I was like, our L-stars, our chamber length is going to have to be like 3 feet. No. So now that I fixed that, we can see that we're like right on the edge of a recommended L-star. So not bad. 50 to 100 L-star isn't too bad, and we're right there on the edge. And if we were to use that entire tube, we would
12-foot long chamber, or 12 feet, 12 inches. I keep saying 12 feet. 12-inch long chamber. That, oh my goodness.
So I think it couldn't hurt to make two.
Yeah, that's the thing, is we're going to budget it for one, but we might buy enough material for 2 engines in
Yeah.
case. We might change some things. I don't know if we're going to change maybe something with the injector design, or maybe try something a
Yeah.
little bit different. But at least just have 2 in case something goes horribly wrong.
Yeah.
Yeah.
So like now that I have this, if I can go on a place like McMaster or Amazon or something, like look up Garlite tubing or something like that, and I don't know, maybe an alternative is I want a thinner Garlite ablative tubing or something like that. So then I can change my, I don't know, something like this, and I can. So if I change the wall thickness of that Garlite tube, now I have a larger diameter or chamber diameter, and then that can change our L-star. But say like, or I guess it would be
Like
let's say
0.875 or
yeah.
something. Yeah, because there's some of the. Oh boy, we're both at the same time.
Yeah.
Yeah, so there's different Garolite diameters that you can choose from. So
Yeah.
You can get like 1/16 of an, not diameters, but wall thicknesses. You can
Yeah.
get like 1/16 of an inch, 1/8 of an inch, 3/16 and a quarter.
Yeah.
So I think we're gonna baseline 1/8 of an inch, but we might pull it back to 1/16 because then therefore we get a little bit better L-star.
The trade-off
and
is
that's
like,
one other thing we could do with the engine, right?
Yeah.
We can, if we build 2 engines, we can buy 2 different Garolite liners. I don't want to do that because the Garolite comes in 40-inch lengths and it's 40 something bucks a piece.
Yeah.
So I'd
it's,
rather just not change that. So maybe we'll change something else.
Yeah.
Maybe another parameter somewhere, or some other physical piece of the design. But
let me. Oh.
I did it. Oh gosh, we both keep editing the same thing.
All right.
Yeah, so I'm gonna keep working on We might have to do some little bit of chemistry here. I'm going to try to pull it over to the whiteboard cam. I don't know what is going on with why the cam for that keeps freezing. But we haven't had an issue here. We haven't had an issue with this camera up here.
Oh, yeah.
So maybe I do a little bit of fixing it and moving some stuff around and changing the camera.
Yeah. So then, I guess for those of you watching, now that we have a pretty good idea of what our engine specs are going to be using NASA CEA, and then now using the Rocket Lab PDF, we have a good idea of what our chamber should look like. Now we're going to kind of use this information to calculate our orifice size, which is essentially just a really small hole that the propellant or the fuel and oxidizer flow through.
Mm-hmm.
And
there'll be 2 orifices, so we'll calculate the orifice for each one based on the propellant flow rate, which is what I need to find. That's my value that I keep beating around the bush and doing other things because I'm not confident that what I'm doing is going to work. But I have to do a couple other things. So I got to get the flow. I got to get the process in my head before I do it. Otherwise, I just do it wrong. So we're going to need to find. I don't know. Should make another thing under here, I guess. We'll just do this. We'll make a nozzle. I'll make a nozzle tab here. We'll organize this a little bit better once we know how the flow is working. We'll move some of these blocks around and make it look a little bit more pleasing. Pleasing. Oh my god. Oh man, I'm falling apart over here. I can't speak anymore. Kels. That's not. I'm typing too fast. I keep doing it. All right, so we got nozzle calculations. So we're going to try to find the specific gas constant, or specific R. I'll just call it specific R. And that is going to be based on something else from here. Okay, you know what? Control X. We're going to have to find. Oh wait, no, that's what wait, what? Oh my goodness. Oh no, I do need to. So this is where I was gonna it was gonna be a little bit spicy.
Yeah.
I don't know. Oh wait a second. Okay, this actually makes sense. So we have mass fractions at the road. We wanted this.
Oh. Okay. Yeah.
I've done this before and it's not fun, but like way more complex than this. Like this gives you the mass fractions already. I had to calculate the mass fractions one time and it was not a good day.
Ooh.
It was actually not a good week because it took me like that long. This was a side project for home, but what is the turn-in process? All right, I'm gonna jump over to the whiteboard.
Oh my goodness, it is still just botched. Let's see. I don't know why this camera freezes. So you can see me. Yeah, it looks like it's. Can you keep just look at the stream a couple times to make sure that the stream doesn't fail. So this is not gonna be any good math. This is gonna just be a brain dump. This is just gonna be me just spitting out things. So we have can just read them. Too late. I'm ready. Cool. Alrighty, so these are the mass fractions. That the NASA CEA gave us. And essentially I gotta say, what's the molecular weight of the products? So this isn't gonna be hard because I actually now just realized what I'm doing. I think I'm doing it right. I'm gonna basically, so our reaction is going to be this, like combustion reaction, just the bare basics of it. We're gonna have H2 plus O2 equals, oh wow, actually, it should just be water, right? The byproduct, right? Isn't the byproducts of hydrogen-oxygen reaction? Yeah, it's just water. I'm used to a hydrocarbon fuel and an oxidizer, and you get CO2 and H2O.
No, that's a good
but
point.
Yeah, so this is just this. All right, that actually makes things awesome. So, but then you're gonna have a dissociation reaction, or not reaction, dissociation of these, and that's where it breaks down. Where you have in the products, you're gonna break down your H2O, and it's gonna form. You're gonna have some H2O in the gas products that are flowing through the nozzle. You're going to have a dissociation of the H2O, and you're going to have some amounts of OH, the hydroxide. You have some amounts of hydrogen gas, because that's our fuel as well, so it's like and some uncompleted reaction, and then you're also going to have like some H. So some just ions, essentially hydronium, I think that's what it is, hydronium or something, ions. So our reaction is this, and we got to do like a little chemical balance here. So we'll have 2H2, yes, right? Yes, that is correct. So the stoichiometric ratio, did I do that right? I did that. No, I did that right. This is where math goes to poop on me. So we're going to have, I'm just kind of just brain dumping here. Let me just, that makes no sense. That means my OF would be a half. What did I do wrong? That should be right. That's the stoichiometric one. But anyway, so like we have a reaction going here. This is like a balanced chemical reaction, right? You have 4 hydrogens, 2 oxygens, 2 times 1 O is 2. So that's a balanced chemical equation. That's our reaction for the engine. There's probably going to be we're looking at the best case scenario that these are the only byproducts in the exhaust, which is completely not going to be the case because we're going to have a blade of burning away. So what we're calculating here is going to be completely wrong in the real world because there's going to be extra things happening, things that we didn't realize are happening. So we have these products. So essentially this can be broken down into these like there's this kind of stuff happening. Like really there could be an O, like there should be an O left. Like O, just O, but in this case there's not. I guess it's too small for it to be a recognizable mass thing. So essentially this is our gas, like this is the products, the mass fractions, that's the word, mass fractions of the gas going through the nozzle throat. So what we want to do is essentially, we want to find, I'll do it right here. We'll find the total molecular weight of those products. So essentially what we're going to do is we have mass fractions, and oh boy, this is where my chemistry goes down the drain really quick. We have, I'll probably look this up in a second, but because I'm going to do it wrong. I forget how this works. I know how it works, I just don't know what the equation is. Because you have things in like grams per mole. So these are mass fractions. I don't know if the mass fractions are in pounds. It probably is. Or are they grams? essentially how I want to do this is I got to find the molecular weight from these products in the gas. And for example, like, I'll just do this. I'll just start going. Like I said, brain dump. This is 1.01, isn't it grams per mole, right? Is that the unit? Grams per mole? That's what I thought. Grams per mole. H2 is 2.02 grams per mole. H2O is equal to 17, 16, 32. Grams per mole, and OH is 17.0. This is just based off the periodic table, right? I believe that's correct. So,
Isn't H2O 18.1? There's only one extra.
oh, you're right. I have my brain flipped them.
Nice.
Yep, you're right. So, all right. So that's
Oh, is that a 7?
where, right here.
Yeah.
Yeah.
Okay, nice.
What do you think I wrote?
It looked like a 9 for a sec.
Oh gosh. Yeah, 17. So so we're trying to find the total molecular weight. We know these. And if the mass fractions are given in grams, or not mass fraction, oh gosh. Like whatever's, so my intuition would say to multiply each one of these, right, by this, and then add them all up, right, because, but mass fractions, it's not like mole fractions. If it was mole fractions, I feel like that would make sense, because then you would do this times this would cancel out the moles, and you would get grams.
Yeah.
And you would have the molecular weight. Let me do a little bit of research before I speak and do things wrong. So I think I'm on the right track here, but we'll flip over.
Flip over to the screen share so I can show you. Can you look at the? Did anyone put a comment in there saying like you stink? No, not books. I just need to do. Okay. Okay, molar mass. The molar mass of it. So, sorry. This is. That might help me a little bit. I'll do that. Total molar mass. So we have the total molar mass. Probably like losing so many people because you're watching. We only probably have 2 people watching because we have a video going up here.
Yeah.
To see that we're doing this correctly, we have Zach's computer running the stream, so we can look at the chat properly, and then we have. That means we only have 2 of us actually, 2 people actually watching. Thank you to those 2 people.
Yeah.
Thank you for watching. It just helps. I mean, we're just kind of recording this for our just documentation purposes in terms of we have a video of us designing an engine, but we wanted people to come and watch. So some people probably left because they're like, "Wow, these guys are gonna die."
No, it's a group learning process. I mean, if there's something that you guys are learning, or any comments you'd like to make, please feel free to put them in the chat or anything like that.
Molar mass. Maybe I should look up what a mass fraction is, because that's obviously. Oh! A mass fraction is the mass divided by the total mass.
It's dimensionless. That's what I was thinking. I was like, wait.
That's what I thought. Like at first, I was like, "There's no way this has a unit with it," but
Yeah. If the goal is to find the mass flow rate at the nozzle, though, I feel like there's another way that we could find that without Well, I guess because what we're
The other way is the other way to find the total. Like so, mass is conserved for this. So if I
Right.
find the flow rate through the nozzle, like this is why I'm saying I'm trying to do this in a fancy way that doesn't really matter. We could just
See.
make an estimate and say, hey, we want 10 pounds of thrust, and it would give us the mass flow rate of propellant into the chamber, which is
Yeah.
also the two of those combined. The total mass flow rate, sorry, the total propellant flow rate is the total mass flow rate through the nozzle because energy is conserved, mass is conserved, and that would make sense. But I'm trying to do it this fancy way with this choked flow stuff over here, trying to get these numbers.
Well, 'cause,
so
like-
I'm trying to find the specific gas constant, which is the. We kind of do need the specific gas constant though. It's used
Yeah.
otherwise, so we kind of do need it. But for some reason, I can't process mass fraction other and times the grams per mole. So I'll jump over.
Thinking about two is m dot oxidizer plus m dot fuel.
Why do you always have a marker that's better than mine? I don't get this.
What's our ratio? 2.5?
Yeah.
Isn't that, cause that's proportional. We want this guy.
Well, actually, wait. I don't know. That's wrong.
Is that, well,
Or like so. So this is what, right? Or maybe you're not right. I don't think you're not right. You're not wrong. I don't think.
because that's in theory, that's what, because
No, you have it the other way around, right? Look at so MO over MF is 2.5.
Oh,
MO
right.
is equal to 2.5 MF.
yeah. So, right? Well, no, because that's MO. Well, look, 'cause total mass for the flow rate for every
No,
one
wait.
fuel we have 2.5.
Wait, remember, like,
Oxidized.
let's do it. Like, let's write that down again.
Yeah.
MO MF equals 2.5. So MO is equal to 2.5 MF, meaning you can substitute MO for 2.5 MF and leave the 1 MF here.
Right. Okay.
So then make that,
Yeah.
or I just totally botched that. So then make that 2 MF. And now you can take the, remember, do the MT, you can take out the MFs and you've got MF times 3.5 equals MT. Remember I was doing that?
That's right. Okay.
Yes, you're right.
Yeah.
Yeah, you're right. Ah!
No.
I'm screwing everything up.
Brackets. All right. So. All right. So then we just need the m dot of. And then this is where we ran into having two unknowns.
Yeah, and that's why I was like, we need to find the M total,
Mm-hmm.
and mass flow rate total, which was related to the nozzle because we have this known
Right.
nozzle that has a throat diameter.
So m dot total was that fancy mass equation.
Yeah,
What was that?
that. Oh my gosh. There's no way.
I'll go take a yeah.
Hold on, wait. Let's just do this.
Wait here.
You just looked it up on your phone and we took a picture of it.
Yeah. All right. So that's area times the pressure at the throat over the square root of the temperature of the throat times ratio of specific heats over that fun gas constant.
Wait, are you in the top one or the bottom one?
What-
Well, okay, never mind. I would say we know the M is Mach equals 1.
Yeah, that's true.
But don't erase it. Like, it's good to go through the whole exercise because
Yeah.
obviously we need it. I'm getting botched
Nice.
here. All right, I think I'm gonna go find another marker because this one's kind of not good.
Just right. There's all these.
I like black though. I wanted to use a black marker.
Yeah, that's not.
There's all these markers down here.
I can't write gamma. All right.
Maybe I'll do blue. Blue's nice. I just want to people to be able to see what I'm writing.
Yeah, the
So I'll go
contrast is-
grab a black marker. All right.
All right. So essentially, what I'm doing here is we need. Alright. So we need an area, we need a density, we need a gas constant, a ratio of specific heats, our velocity, our Mach number, our temperature at our throat, and the pressure at our throat. Yeah. Nice. So, we know our nozzle area should be on that spreadsheet. What is? Well, all right. I guess for starters, we know that the Mach number is going to be 1. It gives us CEA gives us the velocity, correct?
Of the flow through there?
Yeah.
Yeah, it does.
Yeah. Specific heat ratio is 1.22.
So the sonic velocity in meters per second at the throat is 1772.8 meters per second.
Got it.
So we got to convert that to feet per second.
And then our gamma.
Oh, our gamma at the throat. I mean, we have a gamma that is like, if we want to just make, do you want to? I don't know what we want to do. There's different gammas. Like there's gamma changes over the course of the flow. So we can do. It's 1.229. Or sorry, that's the one at the chamber. It's 1.2478.
I mean,
That's probably. Well, that's actually probably more accurate,
Yeah.
right? Because that'll get us. Yeah, never mind.
all right. Our throat temperature.
Our throat temperature is 2,135.46 Kelvin.
2135 point what?
46.
46 Kelvin.
And
Okay.
the total. You're looking for the throat pressure.
Yeah.
It was 4.388 bar.
Nice. Okay.
So I'll have to convert that to. We know the area.
What was that?
That's on the sheet, isn't it? Yeah.
Oops.
Our chamber or throat area is 0.0665 inches squared.
That was right. 0.0665.
Yep.
And then our. Let's see.
What is P?
That is our density.
Oh, that's rho?
Yeah.
Okay.
Yeah. I don't know. It's gonna look the same.
I just do it like this.
Yeah.
In order to make it look a little, I go like this. Oh, nice. Add a little curl to it. That's cute. Oh, you're right. Well, wait. So you want that number, the density?
Yes.
Wait. Hold on. Can I see that?
Yeah.
There's a density in there?
Let me.
Take this back for a second.
Yeah. Not sure.
I don't know where that came from. Oh, R is density.
Wait. Why do we need density? We don't need density, do we?
Because we're literally not in that equation.
Nope. Don't know why.
It's for the mass flow rate. M dot equals RVA, which is something completely different. That's basic. Yes, we don't need it for this calc.
So then.
That's something different.
Yeah. And then R is the gas constant. We better double check what kind of gas constant that is.
Oh, this is the special gas constant I'm trying to figure out. It's not 8.314. See? The constant value for each gas, which we have to calculate. So right here is the universal divided by mass, and you get this specific one for air. You get different. So maybe we should look at the
Wait.
sheet.
So then, does this give us the mass flow for each?
No, it gives us the mass flow for total. So what I'm trying to do is find the specific gas constant for the air, for the mixture of gas at the throat.
Oh, right.
Not for each one. For the total.
Oh,
gas.
so
That's why it's called specific gas constant, because it's
Right.
specific to all of these products of the flow that's at the throat.
So we're dividing that by the mass of both the
Or
oxidizer.
yeah,
and
well,
the-
so we have the specific like the universal R,
Yeah.
which is going to be equal to 1545 point. This is a great marker. 1545.32, and it's like in that feet pound
Yeah.
ranking. And then we need to divide this number by the molecular weight, or the mass, whatever the total molecular weight of the products, and this will give us the specific
Okay,
R,
I see.
which is that R.
Okay. I'll put a sub P there.
For what? Products?
Yeah.
Okay. Okay, yeah, that's a good idea.
And then
This is a fantastic marker.
Yeah.
I'm keeping this forever. All right, our stream is still going. We're not freezing.
just for a second, I'm gonna make that into feet. Oh.
Sorry about this mess. We're all over the place.
No, it's the fun. That's the fun part. It's like, oh well, this doesn't work. This might work, and then you try a bunch of different things, and then you learn stuff. All right,
You learn things.
yeah. 4.388 bar psi. Do we want to turn that? Yeah, we do.
Or is everything in feet? Oh, make it to pounds per
Square
square
inch.
foot.
So I gotta turn that into inches.
No, you don't. No, I wouldn't do inches per second there. I would just change the. It's. Do yeah. Find it in psi. 63.64 psi.
Yeah.
And then pounds per square inch to square feet is
PSI, okay.
divided by 144. So that number divided by 144. Oh, times 144. My bad.
Uh-huh.
Yeah, times 144. Because think about it, you have more pressure over a square foot than you do over a square inch. Wow, I'm so rusty with everything. Yeah, times 144.
All right. Yeah, you're right. All right, 9,164. Pounds per square foot. All right. So then that's in feet per second. That's in that.
Inches squared to feet times 144 again.
Yeah. 44 is 9. Is it?
Or to,
Can we divide that by? I think we do.
I didn't say divide it.
Yeah. All right. Okay, so now we need to find R. How's that looking? Can we read that? All right.
I think so.
Yeah, so this mess is our pressure of throat. This is our chamber temperature, which,
Well, I guess it'll depend.
and
We'll have to make it into Rankine because we're going to be
That's
using
true.
some crazy thing.
so,
Kelvin the Rankine.
yeah. Let's see. Oh man, I'm in a corner. 38 for 3.828.
We're not going to be able to see any of this. We'll go to repeat these numbers.
And you're like,
So I'll erase some of this stuff here.
yeah, alright.
But
So now we need our gas constant. So now we need our molecular weight of our products, which is...
me still being special. I'm still sitting here like,
Well, if there's mass fractions, that means there's a total mass. So what is the total mass of our products? 0.8. So it's just the sum of these numbers, right? Because that's a very small product. That a product is going to be...
is that equal? Oh my god, is that equal?
It should equal 1.
It probably does.
Yeah, so...
I didn't realize that. I'm really not doing too good here. I'm fired. I should be fired. I'm just...
Molecular weight. Let's see.
1.
Yeah.
All right. Who would have thought that's how things work?
Yeah.
All right.
Alright.
So it's okay.
Well, our products, let's assume our product is going to just be water, right? So now we just need the molecular weight of 2 moles of water. If we ignore all this junk, if we ignore the parts of hydrogen that aren't burned, stuff like that.
Oh, I'd rather try to be as close as possible, right?
Yeah.
Oh my gosh. It outputs the molecular weight. That's
Is it
what
really?
the NASA CEA thing does. Oh my gosh. I'm not even looking at the right thing.
Back to screen share. I'm so stupid. If we go to the CEA thing and look at
Alright.
tabulation, because I selected molecular weight,
Right.
please work. Oh no. It's broken.
Two watching. We lost our one viewer. Rip. No, it's fine. We're on lunch break.
People don't want to see us embarrass ourselves. Oh no.
Right.
Please, sir. Did I like lose the internet or something? What's going on here? Don't tell me like NASA CEA is down. That's not good.
What's it gonna do? Is it not? It's in the drive, is it?
Not the output.
Oh. All right. So, let's see. If anybody is watching currently, what we're trying to do. So.
There's 3 watching. Somebody's back.
If so right now we found essentially what our chamber is going to look like, our chamber length, the area of our chamber. We found our L star, ideally between 50 to 100. It currently sits at like 49.6, so we're right there on the border of it. We used NASA CEA to find important stats about our engine, like our specific impulse, our oxidizer to fuel ratio, our chamber pressure, chamber temperature, gamma, and then our ratio of our area exit to the area of the throat. So now what we're trying to do is we're moving even farther back into the engine to our injectors. And with our bi-propellant engine, to keep things simple, we're only planning on having 2 orifices to inject our propellants. So what we're trying to do right now is find the mass flow rate across the nozzle so that we can use our oxidizer to fuel ratio and backtrack to see what flow rate of oxygen we need and what flow rate of hydrogen we need to actually get choked flow through that nozzle. So now Dylan is looking at the CEA data to see if we have our molecular weights for our propellants.
So unfortunately, I think it's in another thing. There's another tabulated data that you could export the molecular weight, and somehow NASA's page has crashed. So we cannot access the CEA thing anymore. Which is a good thing this happened now and not 2 hours ago when we needed to use it.
That was quite not good.
And maybe it's just down for something. I don't know. It's kind of like cranking along here. It's loading, and nothing's happening. So
yeah, let's see.
Yeah, you try to open it. Like click. Oh, did you?
Yeah.
Oh, it's definitely down. Something's not good. All right.
So you might be asking, well, why do we need our molecular weights? So NASA has an equation. I think if you literally just go on Google Images and search like NASA mass flow, you'll find the equation that we're trying to use, or that we are using to basically find our choking mass flow. So with the NASA CEA, we have pretty much all of our givens there, and in order to get that gas constant, now it's not the ideal gas constant, it's the ideal gas constant divided by the molecular weights. So as soon as we have that R value, then we can proceed with our flow rates and go from there.
Yeah, it's just unfortunate right now that the website's down. I don't know why they went down.
Yeah.
They're probably doing a software update or something, and yeah, because we still got internet, so we're good on the internet because we're still on the stream. The stream's still going.
Let's see. Well, maybe there's another way we can do it.
I think you can do it based on this information, but I'm just not having things right now. I don't know what it is. I
Well,
just can't figure it out.
I mean, like. Well, if that's the mass fractions, let's say we have 1 gram of a mixture of propellant. Given those mass fractions, that means we'd have like 0.8 grams of water in our exhaust, right? I guess what's confusing me right now is like
Oh, here we go.
when the exhaust is leaving the chamber, that's not all water. That's
Here,
like
I think that's my answer.
okay.
Like 1 over the molecular weight is equal to the mass fractions divided by the mass of A. So, right, yeah, that's it.
Okay, that's what I was looking for. All right.
It's a YouTube video. Oof.
Mass fractions.
Back to the whiteboard. Right, we're at the bottom one.
Okay.
Or the top one, mole fractions. No, never mind, not mole fractions, we don't know that, we know the mass fraction. So, we're going to do 1 over the molecular weight is equal to XH over the mass of H plus
Let's see.
XH2 over the mass H2 plus this is a gray marker.
Yeah.
Alright, so bang, there it is. So we have all these numbers, right? Boom, there they are. So essentially I'm going to do this. X of H, we got 0.00022 over the mass of H, 1.01 grams per mole, plus XH2, 9551 over 2.02 grams per mole, plus H2O, 0.8043, divided by 18.01 grams per mole, plus 0.024 over 17.01 grams per mole. Nice. 1 over the molecular weight is going to be equal to all of that. And I will get my calculator. Oh, sit for that. 0.022. Oh, wait, yeah, okay. their weight is equal to, so you have 1, 4, 1, 6, 6. I don't know how to do this. What would those be? You have 1 over grams over moles. Would that be mole grams? Maybe like that. And then you do the flip around. Flippy.
Well, that's, oh, yeah, mole grams, I guess.
Right?
Yeah.
Is that right? And then do this.
So it's still grams per mole because you flip it again.
1, yeah. Bam. All right.
Nice.
We're very populated now.
Yeah.
Okay. Stream's still going.
All right, so then we take that number.
Let me just, I mean, basically, I just want to double check. It's not going to be quite clear. I'm going to flip
The
this.
screen share here. It's not going to be quite clear on this because they don't do this well, or he doesn't. So he just says, the molecular weight is 24. Well, what is 24? 24 what?
Yeah.
Right? He has no units. So could that be 24 pounds per mole, which is probably what it is? Because we are in
good point.
grams per mole, but maybe not. I don't know. That doesn't. I just don't know what the units are, which is the frustrating part. That's the frustrating part about using this PDF is things aren't quite clear. So if we go here and look up the universal gas constant, and we go to engineering toolbox because this is awesome. We go right here. Down here is what we're looking for. Bang! Right there. That is not that is the number, but it is so he did a weird units thing, where it's actually so we have the moles, but we want it in pounds. So I think this to me this probably is, I shouldn't even be like looking this up, but it should be pound moles. Oh shoot. 7.059. All right, so apparently that's that. We'll eventually, if the NASA CEA thing comes back online, we'll double check it, and then we can, hopefully it comes back online eventually. So we'll double check. We'll go with this. We'll go with this number first. We'll go with like this number first, and kind of just crank along and see what goes on. So we kind of want it. I think we need it in pounds per mole.
Yeah.
But maybe we don't.
That number up top is Rankin. What is that?
It was foot-pounds per pound Rankin. But then this is where this is why this unit is the worst thing ever. Look at this. This is actually in foot-pound force. Foots. Feet times pound force divided by pound mole degrees Rankin.
Nice.
That hurts. That hurts a lot.
Yeah.
So we have. We want that.
Oh, it's back.
Oh, it's back?
It's back.
It's back. Oh my goodness, thank God. Tabulation, bring it to me. Nice. And I didn't choose it. I didn't choose that one. They must have been just like updating it or something. So that's what I wanted. I had it on there and then I took it off. It's like, oh, we won't need that, and I wasn't paying attention to what I was doing. All right, hold on. I gotta just X all. Oh gosh. Bring it back in here. Now open up a new one. problem though is it gives it to you, but which one is it associated with, right? Imagine it's in groups of 3. Imagine it's ding, ding, ding. Yeah, it is. It's in groups of 3.
Look up, if you look up the ISP at our
That's
oh,
what
for
it is.
each, yeah.
Yeah. I wish you could print the OF. It doesn't let you like choose.
Well, is it not listed there?
No. Sorry, it is. I wish you would print it in the output thing. It didn't.
Well, no, I'm talking about the molecular weight.
It is. It's not in here. It's in here. It's this column. So. Brain. So.
Wait,
Sorry, I'm. This. The ISP. We want this one. I'm just gonna look for this guy. 380. 3851. Sorry, I'm thinking and not doing.
Wait, that's different than.
Is it?
Yeah.
Then what's here?
The one on our current sheet is like 3084.
Oh, sorry. Wait, what?
Yeah. That's why I was like.
Oh, I was looking at the. Is this the wrong thing? I have the wrong thing open. Oh
Is that
God.
methane?
Oh no. I have values from. I will use gammas from here. Is it oopsies? All right, we're gonna have to make this. Oops. Just dabble.
Oh man. Alright, yeah, here let's. So.
Oh, I have it open here. Here it is. 3084. Yeah.
Yeah. Wait, what's the gamma real quick?
Same.
1.22. Okay.
But this one,
Yeah.
it's a little bit different here actually. No, it's not. It is the same. 3084. 3084. That's what I'm looking for.
Okay.
Oh my goodness. 380. 3084.
Oh, wait. It was just like below where your finger was. Oh, okay, there it is.
But we want it, the one above it at the throat.
7.044.
That's it. 7.049. 7.049. Right, look at 7.
Yeah, that's pretty close.
7.05.
All right.
So that's the line we're looking at. It was really close to our calculated value. So what we did was right. We
No.
checked it and it was good.
What units is that must be grams per mole then. Just to
I love how they don't give you units.
yeah, sanity check.
Oops. All right. Do we need this anymore?
Yeah.
Not being used. One over n. Oh wait, molecular weight. Oh, m. In big
Oh.
M. Okay, big M.
All right.
Right, because isn't that
That's just grams per mole, isn't it?
M?
M.
M unit. Oh my goodness! What am I looking up?
Per liter of solution. So it's moles per what?
No.
That's not right.
Oh my. People are probably cringing so hard right now. Check the chat. Is there something going on in the chat?
No.
Some guy, somebody came and left and was like, "Oh boy, they're breaking themselves." Is it molarity? Okay. No.
Study your
I haven't been
chemistry.
in chemistry in a while. Oh god, it's not molarity either. Oh wait. It's moles per kilogram.
Yep, molarity. Yeah. Which that would make sense because it's for liquid fuels. So it's like
No, well, not really. I kind of, but not really. This is where I just. This is why it takes me forever to get anything done. Is I'm looking at there, looking. I'm almost certain we can just divide our number by.
well, liters per mole. That gives you 2 units. We'll give you it. I'm assuming that's liters per mole.
You know what? I think it's safe to make the assumption we can just divide this by the molecular weight, because when you think about it, if we chose 8 and just still divided it by, it's the same,
Actually.
right?
Yeah.
But I just want to know the units just for my own sanity. But I think it's grams per mole, right? Because look, it's grams per mole.
Yeah.
What is grams per mole?
Why does he say 24 though? That.
Well, because he's using. It is okay. It is a mole to grams. I think it's capital M. I think they just said. They used. Look at this. They used M. They just said M. The mole is equal. Wait, what? No, it's not. Oh my gosh. This is what happens after a while of just not paying attention to chemistry class.
Well, I mean, to be fair, the book isn't very clear. Neither is the CEA.
See, look at grams to moles. This guy even screwed it up. Or not, I don't know. Why can't I do, I don't know what is wrong. Molar mass. Oh, it's molar mass, look.
That's grams per mole.
Alright.
So we're right. It's okay. All right.
Because the specific, okay, this is where, when I did this before, the specific gas constant is when you, so, I think the guy just makes this, crazy rings.
So, I go back to the whiteboard. Yeah. I think what was happening was, you have, this is actually, the units for this is, pound times pound force over pound mass mole. And what we want to do is, that's the universal one. By doing this, you get rid of this. And that's when I did the calc, and then you use this, and this is another gas constant. This is the specific gas constant, because now you've gotten rid of this. So I think if we divide, even though this is stupid and it's weird, I think if we just divide this number by this number, we should get the specific gas constant. Because think about it, where did 24 come from? 24 came from they estimated the molecular weight of the products.
Yeah.
And it was probably something along
those lines, if that makes any sense. The molecular weight of the hot gaseous products of the combustion of gaseous oxygen and hydrocarbon fuel is about 24. So it's this divided by this. Or sorry, this divided by this equals this. So that's what we're going to do. If it's wrong, we'll fix it. All right? 7.059. And I believe that is in... Yeah, I think it's grams per mole, which is it's not making sense to me, but at the same time, I don't know of any other way to do this. Oops.
Well, because
That's a huge specific item.
yeah, that's what I was doing. We're gonna have to change that to pounds per mole.
But then it gets even worse. It gets huge, right? Because look at,
Well,
I had it up here.
oh.
See? 7.059 is even smaller. So you divide 1544 by this, and it
Yeah.
becomes huge.
Well, but the units don't work out.
Or
You can't
actually,
divide
or
it
do we
by-
multiply? 1545 and 32 times that number? Still like 240. Yeah, this is just. Yeah, we might have to do a little bit more calculations with this, or more research rather.
Yeah. Kilograms per mole. So that would be like 0.0.
We've been going at this for 3 hours now.
Oh, this is joules per kilogram Kelvin. Why?
Yeah, we should have done more research before doing this live stream. Just kidding. This is part of the fun. This is when you figure things out.
Yeah.
Maybe if anybody's sitting there, or I imagine people are just listening, and doing other work specific. If you have any input, please send it in the chat. The other thing we could do is just convert this all to metric and then flip it back. I'm so dumb. I was paying attention. So like here's this. Right, I mean here's the equation. It's like there it is, like I know I wasn't doing it wrong. S equals R over M, and like there's a molecular weight. Now I want to do like this to our units, right?
Yeah.
Maybe. This is where things get broken.
Alright, so if anybody new is watching, again, we're currently looking for the proper specific gas constant for a mass flow equation. If you just go to Google Images and search like NASA mass flow rate, or I guess choked mass flow rate equation, you'll find kind of the photo that we're using, or the equation that we're using rather. But essentially, we found all of our chamber parameters. Our nozzle parameters are predetermined by something that we're buying off of, let's see, a website called Rocket Motor Components. And now we're trying to size our orifices for our oxidizer and our fuel. And essentially that involves finding the mass flow rate at the throat of the nozzle with the, I guess, that mixture moving at Mach 1. So once we have that mass flow rate, we can use our oxidizer to fuel ratio to find our fuel mass flow, and then we can kind of back up even further and find our fuel orifice size, and then we can find our oxidizer orifice size as well. But if you have any suggestions on, maybe you're a little bit more experienced than we are, and you have suggestions on how we should go about finding our specific gas constant, then please drop a comment, or if you have any questions as well, don't be afraid to chat something, or just, yeah. So, let's see. I'll just do it in metric. Why don't we just do it in metric and then take the mass flow and
convert it?
Yeah. Let's do that. This is taking a lot of time.
Alright, do you want to start converting all those meters? Yes, the imperial system. I do personally love it. Like everything I do is in inches and stuff. But then this happens
Stuff
and
like
it's
this happens
and it's very frustrating. I get picked on by all the other engineers for liking this system, even though.
I mean, I understand now. I understand their where they're coming from. All right.
I might have found a thing. Has he done it? I think 218 might be right.
Actually.
Yeah, look, I found units here: pound force foot per pound degrees Rankine, and I did our calculated thing based off of what this calculator told me in metric, and I put it in here, and it gave me 218 again.
Huh.
Exactly the 218 I have here.
Interesting.
Well, oh, you know why? Think about it for a second. Our products are so light. Our molecular weight of our products are so light, so when you divide it, you have a huge specific gas constant. Hydrocarbons are really heavy.
That's a good point.
I think we're okay. Well, you can still do that. I'll flip you over to the whiteboard.
Yeah, so you can erase some stuff and start and figure things if you want, but and then
Bars.
if you want to work over here, you can.
Okay. Should I turn that into
The R, the specific gas constant.
Gosh, you're right.
haircut.
Sounded right.
Is ear kind of close?
No. That's not right.
The units,
Yeah.
according to this, the units should be, you're like standing right in the way of thing. The units should be joules per gram Kelvin.
Yeah, that's right. Okay.
Oh well, actually no, joules per gram Kelvin.
Gram per Kelvin?
No, joules per gram Kelvin.
Okay. Gram Kelvin.
You do your slashes the wrong way.
I know. I write from the bottom up too. Or sometimes.
Why?
I don't know. And then, where does that pressure dimension go away?
It doesn't. Well, if you're in pascals, which is metric pressure,
Yeah.
metric pressure, that's Newton meters. No, sorry, newtons per meter squared. So, okay. You probably have a meter somewhere, and you probably have newtons somewhere. And newtons are also kilograms times meters squared over seconds squared. That's a newton. Don't worry, they all cancel out. They will
Okay.
all cancel out and give you a mass flow rate in probably kilograms per second. Let's see. Oh, yeah, right here in or grams per second. So you get, joules per gram. Okay. Oh my God, my brain. This is a difficult one. Hey, we have 5 people watching. Nice.
All right.
I'm just glad there's some people here. There's somebody's here to enjoy this.
Yeah.
Even though they might be crying inside due to our porn. Yeah.
That's okay. How else are you gonna learn? How else is anybody gonna learn?
Oh my God, it's almost 12 o'clock already. That's insane. We've gotten like nowhere.
Well, no. I mean, we've.
I'm kidding. We've got somewhere.
I'm not total pickles. Just for fun, I'll put it there. All right. So now, there you go. You're gonna need your calculator.
Yeah.
Thank you.
Let's see. Man, you gained 5 subscribers today.
Did you really?
Yeah. Nice. Ooh. Nice.
All right. Now let's just do things. So, If I mess up, I want to be able to trace it back.
That's a good idea.
Yeah.
Is that grams?
Yeah. I think they're looking grams per second.
Are you positive? Did you convert this pascals to like we might actually have to convert this to joules per kilogram Kelvin because
Joules per kilogram.
because like
Oh, you're right.
possibly
Because I'm just thinking it.
a Newton is equal to using a kilogram times meter squared per second squared, and that's Newton, but then a Pascal is equal to a meter squared. So like there's a kilogram embedded in that
Yeah.
Pascal. So, and then we don't have any way to cancel that. So you might be, well, you just could be off by a factor of 1,000.
That's true.
But I don't think we're not running 2 kilograms per second. That's a lot. 2.5 kilograms per second. I would just check, make sure, like, do a double checko. The other thing is we could just start inputting this into Excel and see what Excel tells us.
Yeah.
But it's nice to do it on the whiteboard first to
Yeah.
figure out what's going on. Let me check the Newton thing, because
Yeah.
I probably did something wrong again. You always assume you did something wrong. Yeah, I did it wrong. It's Newton is equal to 1 is kilogram meters per second squared.
Nice.
Not meters squared. I knew I was doing something wrong. So, alright, I'm going to jump on over here and try to do it in Excel.
Check something.
Let's do this in Excel with English units. I'm going to try to shoot it try to do it with English units. Do we even use this? We didn't use this. We'll keep it. Keep it for now. Nozzle calcs. We got molecular weight, product things, specific gas constant. Chamber. Never mind. I'm gonna do this. My gosh, I cannot type. It's really difficult to type with the computer off to the side and trying to look at the screen. Let's bring it over here. 1.247. So we're going to use this. So we're going to assume Mach is 1. So we're going to do this guy. Area is the throat area. Man, this is gonna break. Doing the Excel for this is gonna hurt. I guess I'll just do it in little bunches. You know what? Do we have? So, I'm gonna grab your notebook.
Yeah.
Just so that I don't have to like flip between things. That I'm gonna do.
0.017 pounds per second.
I said to write it down. We're gonna go. We're gonna do it. We're gonna just go to town. It's gonna be equal to. We'll do the first one here. And we'll do a second little calc. And then a third little calc there. Oh, third little thing. So the first one is going to be the area of that times the total pressure at the throat, which isn't actually calculated yet. And we've hit our first roadblock. Below. Got to grab this.
How fast is that going?
How fast is it going? I'm not sure.
Because we can.
Oh gosh. I'm just gonna try to do it. I'm just gonna. I think it'll be fine. I just had to calculate some new numbers.
Wait, what new numbers do you?
Or not new numbers, but I had to. Did I accidentally break this?
What mass flow are you expecting?
What am I expecting? I'm not sure. What did you get?
So total mass flow is 0.0172 pounds per second.
What was it?
0.0172 pounds per second for total.
That's actually pretty dang close, I think. I think that's going to be, because we did a preliminary calc with another fuel, and it was kind of in that range. So it was like 0.5 or something. So I'm going to just keep going. Let's see if I can. Goodness.
Right. Actually, I'll use it for. I might as well make a calculator.
Square root of. I know it's not going to be one of these, but for now I'm doing that. Alright, that's not m dot, but Okay. We're getting closer.
Almost there.
The whole book fell. So, just to reiterate, I'm kind of just doing this. So I did this first little guy here. I'm going to multiply it by this now.
Okay.
Yeah.
Nice.
How do you do? Oh my gosh. How do you do exponents?
You like the caret and then the...
Oh, is it the caret?
I think.
Somebody's gonna be like, no, don't do that.
Let's see.
How would you?
Oh, not that. That was like 0.01, 0.02.
Excel's not good with the parentheses. I just have to check. Which gamma did you use? Okay, we use the same gamma.
The chamber area is still an inches squared.
Yeah, I didn't do it in metric.
Oh.
I did it just purely off of all the imperial stuff I
I
had.
see, I see. Well,
Actually, I'm not nozzle. Okay. Oh god, that's why my area of the throat is in inches. Were you saying I need to put that in the feet?
do you? Yeah, you do. So it needs to.
It's 144. Uh-oh. Alright, let me think. Where the gamma, so this is total pressure. Oh, and then PSI.
Yeah, pounds per square. Yeah.
Oh god. No, areas divided, but it shouldn't matter. Areas divided. So it's going to be the same. Look it. It's just going to be. It won't matter, because if I do, I have to divide one by 144 and multiply the other by 144, so it just cancels. Who would have thought that's wrong? Oh no. Oh. Your CD isn't PSI. CD is just like a dimensional CD.
Oh.
I think. I'm pretty sure it is. Your pressure drop though. Yeah, you assume like 100 PSI pressure drop.
Oh.
Yeah, you can just make a thing called like P drop, and you can do like a PD P drop.
Alright, let's see.
Here we go. Let's see if I can look at it right. Good. On the dead side. Oh. You assumed. Okay, never mind. This is not going to be. What am I doing? Botching it. It doesn't seem right. But it could be. I'm not sure. I don't think so. Hmm. Thought it was outside here. All right, so we're working the problem. I can't believe we've been almost recording for 4 hours.
Are we really?
Yeah, it's been 3 hours and 40 minutes since the stream started.
Oh man.
This is insane. We gotta like definitely figure this one out as soon as possible because we don't have a lot of time left in the day.
No, we don't.
Hmm. Very interesting. Why does this not? Why is it not working?
That's not right. Bloody hell.
I'm just thinking, like, is this right? Like, could this actually be correct? Interesting.
I don't see. So, all right. Is the problem? Is your Excel equation right?
I think so. What's the correct? What is this? I don't know. To me, it makes sense. I don't know why it's not. I feel like it's not correct.
One check. One check my board. I'll check the Excel sheet.
off of the number you got?
Hmm?
The number you got?
What about it?
Like this number? Is this your number?
Oh yeah, that's.
It's the same.
What do you mean?
Look at the Excel. Look at the number I got, 0.049. You have 0.049. When you compare...
No, this is your m dot at the throat. That's the m dot at the for the fuel. Yeah.
What?
Yeah. Yeah. So I don't.
Wait, I thought this was... You were calculating the m dot at the throat, right? Here?
Right. That's the total mass flow.
That's the... Oh.
Yeah.
Oh, that's in pounds per second.
Yeah.
That seems right.
Hmm. It's supposed to be gauge, or is that supposed to be absolute?
Which one? Oh, absolutely. Because, right, I have PN as a PSIA, so all of these are in PSIA. Or the bar, it's a bar, but then converting that would be PSIA, so.
It's the same number.
Well, yeah, it's. I just changed the units. I didn't change the actual
Oh,
number.
okay, I see. All right.
Hmm. Interesting.
Yes, indeed.
Could that be right though? Do you want to just like keep it and just keep cranking along, and then we can go back and maybe fix things?
Yeah.
Cause like there's a chance that could be right. I've done this like 40 times now. Come on, control.
Wait. Why is this only +1?
Is it not? It's supposed
Well,
to be 2.
It's 1 plus gamma minus 1 over 2.
Can you fix it? Wait, can you explain that?
Like right here.
Mm-hmm.
So it's just gamma plus 1. And then you raise the exponent, so then it should be 1 plus gamma
Oh, I
minus
missed
1 over
something.
2.
Okay.
Maybe that changes it. Let's see. Nice. Oh, did I put it?
Oh, like, did I miss it completely? No. Oh, like I used this thing here, Zach. I'm using this equation because I'm not putting m in. I'm using the bottom one. So I did these.
Wait, hold on. Go back to that. What was the? Yeah, but that's a different equation altogether. Where's the?
It's just.
Yeah, it is. Because 1 plus or minus.
Oh, it's just because you simplified with m. M is equal to 1.
Right.
So.
So where did the 1 plus gamma minus 1 over 2 go? That's just gamma plus 1 over 2.
Hmm. Oh, because look, it's gamma minus 1 over 2. Now it became gamma plus 1 somehow.
Yeah, that's what I don't like. Why is that?
It has, I mean, it's on a massive page.
Well, that's the difference, right? Because,
Mm-hmm.
like, what's the difference between these two? Oh, it's just 2 minus 1. Ha! Funny. Okay. Never mind. I'm dumb. Still should have gotten the same thing though, right?
I think so. I'm just gonna like duplicate things here in ISP and dot total. So then thrust, yes, go back to this. We gotta make sure we're also like saying what's going on. We keep doing this and we're like,
Yeah.
herpader. ISP is equal to thrust divided by total propellant flow rate. So if you want to find thrust, you do ISP times total propellant flow rate.
Right. So for the people watching, we're so we have a mass flow rate, but there's a difference between oh man. There's a difference between both of our calculations, and we're not quite sure where it went wrong, basically. So mine was in metric, his was in imperial, so we're trying to figure out what got lost in translation.
Because that's a terrible thrust. The little engine's only going to produce 1.556 pounds of thrust.
Literally. Well, we've got a really low chamber pressure.
But I know. But I changed some things here. Like this is going to be off screen, but I changed those things here to say like boom, boom, bing, bop.
Nice. Okay.
Like put into this calculator this stuff, right? I change it to hydrogen. And oh, I never changed it. That's why. Let's delete that one. 2. I just feel like there's something going wrong. Maybe we can't do that. Like I thought you could, but to me it makes sense, right? You should be able to say, here's our products, we're having choked flow, here's this, here's that. Like to me that made sense, and I guess maybe it doesn't actually work. We are stalling out in terms of progress here. What is going on? Maybe that is right. It like doesn't make sense, but maybe it is. Hmm.
Get the same stuff.
Oof. I mean, it couldn't be entirely correct because we changed the fuel so drastically.
But why are the calculations different?
We could also just do this. M dot equals density times VA, and then the compressed density. We know it's at 60. We know 63. Okay. Let me do this. We know more. We know more constants. Oof. Broke it. Where's my calculator? Can you grab it? Thank you. Alright, off screen, I'm kind of just doing a quick calc to find the M dot based on the density, total density of the products somehow in the throat times the velocity times the area, because that's the other way to find M dot. Density times velocity times area. So I'm kind of just doing it on a piece of paper right now, just to kind of check it.
Can you tell me a page off of that? Thank you. That's terrible.
Ooh, my arm is like being weird. Actually, I don't know if I can do it. I know the molecular weight of the products, but I have a bunch of random products in there. Do I know the density? Probably not. Yeah, just a little. We're working through this problem. I think we'll figure it out.
So for your universal R, that unit was foot-pounds per pound mole Rankine?
I think so.
Is that from Rocket Lab?
He didn't have moles in the or that paper didn't have moles in the units, but
Where does the number come from? Like, foot-pounds per pound Rankine.
I'm pretty sure what we did is right. Pretty sure that's correct. I think we have a chat question.
Good. I don't know. I think we should, so, because,
You have a different value. You have 171, which kind of makes sense.
so I think the issue is with our imperial specific gas constant. Because our molecular weight is in grams per mole, our specific gas constant is foot-pounds per pound Rankine.
Yeah,
That doesn't, like,
makes sense.
yeah, you can't, that doesn't, like, translate over. So, I don't know. I think we should go with metric as much as,
Oh man.
yeah. Because yeah, it's just like joules per kilogram Kelvin. Yeah.
Huh. We'll have a mixed bag here. We're gonna have metric and imperial. It looks like.
It's like how do you convert joules per kilogram Kelvin into imperial? Like how does oh yeah, but it's 1178 joules per Kelvin. Joules per ampere. Anyway.
Yeah, I don't. Maybe.
It just seems more clear to me with metric.
Understandable.
Like, I mean, did you notice any errors?
I didn't see anything.
Or just
Red.
metric to save time?
Yeah, let's try to watch this.
Alright.
Here, I'll do one to the side. Do it like right here.
Well, we can. Alright, I'll enter this. Do you want to, like, do the orifice calculations then?
Well, unfortunately, the orifice calculations are based on our fuel flow rates.
What do you want to get, like, that? You can set this up all the way.
Oh, okay. Yeah, I guess I can work on that one. Well, yeah, just copy and dump it over there. And make it nozzle calcs metric. Oh, and maybe make a little thing that's like specific gas constant, or do just change the units, but then make a never mind. I'm speaking things that don't make sense. Here, let me. Alright, hit enter in that bad boy, and then.
It's a little sweet. I'll just put. Sorry, what do you want me to do?
Don't do anything. Just let me do something quick. And do 8.3. I just wanted to put it there so that we aren't.
Oh, right.
Yeah. We'll do this. And Kelvin. We'll make this in grams per second. Metric is the way.
Yeah. Oh man. I need this. I like looking at this. Right.
Yeah, so basically just for what's happening there, what Zach's doing is we are figuring that metric is probably, at least in this problem, to make sure we can double check ourselves, because there were a lot of units issues with the metric, or with the imperial system here for specifically the universal gas constant in imperial. So we're going to quickly do it in metric and see if we get the same result or something different. So yeah, so that's kind of what's happening there. We're going to do a little check to get the m dot throat. That's a pretty critical value there, which is going to end up being the m related to the m dot total. Let's do that. Actually, it's blue. Math.
Yeah.
We do math. Yeah, so what I'm doing right now is I'm kind of just setting up the fuel orifice calculator. This will be based off of this guy in here. So we'll scroll down. And that's the combustion chamber, engine cooling, heat transfer, which we're not going to be worried about, injectors. Now we're getting to fun stuff. So here is essentially what we're going to use this equation, and we have all these variables, and we're going to extract the area, because the area is what we can use to find the diameter of the orifice. Yeah. So that's kind of what I was just setting up there. Orifice area. Probably. So here, I'm going to do orifice. Oops.
What's the difference between total pressure and total pressure?
Well, I think it's just for, that's just, oh wait, maybe, oh crap. I looked it up. I don't know. I was thinking just for specific orifices, we're talking about this. Oh no, not this. This guy. The total pressure in there.
Mm-hmm.
Even though they have a nice little picture of a rocket engine here, I don't know if the total pressure is this in the chamber, or is it the pressure at the throat? Because I'm think, like, you're looking at an orifice, like the choked flow through an orifice. A nozzle, throat. The throat can be considered an orifice. It's a circular disc, essentially, circular area.
Yeah.
And that's why I just assumed it was the total pressure was the pressure at the throat.
That would make sense. Okay.
You can also do this. But then here it is again. Right. That same equation is fine. Oh my.
Something's not right. Oh.
Is it the grams thing again?
Well.
Think of, oh wait a second, I think it is. If you times that pound, if you times everything by 1,000, and then like, do this,
Did I do that? I thought maybe I didn't do that already. Yeah, because I changed the specific.
but did you change?
Oh, you're right. No, hold on. Kilograms per second. Hold on. Oh, man. Okay. So, it doesn't even match. It doesn't match any of our numbers.
The units for that thing's kilograms?
Yeah.
But, okay. So it doesn't match the numbers, but ready? So keep that number in mind after you look on your computer.
Okay.
All right, just for some
That's-
context, the little things I keep doing off to the side is like I'm moving my mouse around, but I'm clicking on things and nothing's happening. Oh, we froze again.
Okay. That makes me feel a lot better.
Oh, did I break this? I might have broken this now. All right, we somehow have lost video. Look at this, camera's not even on anymore.
Uh-oh.
That's an oops. We're gonna have to do a little old fixaroo here. Somehow lost the. There we go. I don't know what's going on. I don't know why that happened. I don't know when it froze, but so the little side thing we're doing, I'll bring it into the screen. So a while ago, I had done this a bunch of calculations for my own engine, and I just changed the title for it was useful for us. And I've been kind of just like inputting parameters in here because I think this was I'm pretty confident this was right, and I'm trying to find what we were doing wrong based on this, kind of like assuming, hey, here's our parameters for the engine we are doing right now, and now it's saying the total propellant mass flow rate is 0.025 pounds per second. That was what this told me based off of 8 pounds of thrust. Just random numbers I started throwing in there to test things. And this is kind of close, meaning that we're on the right path. This was not right somehow over here, but this is kind of correct. So it's interesting. Very interesting. So I think we're doing something correct now, but I'll leave this up here so other people can see this double checking thing. So I'm very interested in this. All right, Zach's gonna rearrange this equation. So that we can find the area.
I didn't realize how hungry I was until like 2 seconds ago.
I know, I'm hungry too. We might be taking a break in a few minutes because it's almost 1 o'clock, which is insane. We've been streaming now for literally almost 5 hours.
We surviving.
Yeah, the stream's been going for 4 hours and 25 minutes. We have 2 concurrent viewers. I think 4 watching. I think it's a little bit late. Okay. Yeah, sorry about some of the stream quality stuff. I don't know why it keeps freezing in some cases. It's probably just this computer, I have so many things plugged into it right now. I have a screen here, we have a big monitor we're looking at, and then I have my computer and two or three dongles plugged in that have 3 cameras connected to them, and a keyboard and other fun things. So, computer's really chugging along right now. Alrighty.
Pounds per square. We might want to change that to pounds per square foot.
You can I just always multiplied it by 144 in there. Yeah. It's pretty, yeah, it's gonna be small. Oops, I accidentally changed that to 1%.
that's incredibly small.
Well, it's the area. So
Oh,
let's
right.
do
Haha.
let's do that. So we'll convert area. So you have area equals pi r squared. So I literally can't do these things in my head. I'm not a in my head kind of person. I'm very visual, so I need to like write it out. Okay. So, are you already cranking it out? Or are you 2 times square root?
Oh, it doesn't not. Maybe I need to do that.
Oh, here also. I'm fixing this. You can do pi. You can actually tell.
Oh, you can just.
Yeah, you do
Oh,
pi
okay.
in parentheses. And...
Nice.
All right, so that's wrong. Well, check the orifice area because that doesn't make any sense still. Because that's a 3,000 hole. That's a 3,000th inch hole, and there's no way I'm drilling that hole. So.
Well, that's not too crazy.
Yeah, it's insane. It shouldn't be that much. Look, it should be 40 thou.
Oh. Okay.
About. So there's an error. There is an error. Oh my gosh. Zach, you keep using things that I have variables for already. Like this 32.2, it's over here in the constants area.
Nice.
What else did you do? Alright, I'm gonna write it down too. Let me try it. New page. W equals CD times area and the square root of all that. 2g density, 2g rho, delta p.
Something is not right.
Here, let me fix this. We're gonna do this, so m dot, oh crap, please don't break it. Okay. M dot total, so watch this. I'm gonna do this, enter, m dot fuel, enter. Okay, didn't change it yet. Oh wait. For sure it's like. Did you change it back again to 32.2? Did you not?
No, I don't think it saved it. Because I saw that and I was like, oh, well, he didn't.
Like, are you kidding me? I was like, do you keep undermining me?
Alright, for those of y'all watching, if you have any questions, put them down in the chat. Right now we're working out basically what the orifice size should be based off of the total mass flow rate of the propellants at the nozzle throat. Let's see, yeah, so the issue we're having right now is that a 3,000 orifice, fuel orifice size is a little bit smaller than we were initially expecting, so we're running through our calculations again, making sure everything looks right. But yeah, let's see. looks like after we have the orifice size, we're going to move back over to the whiteboard, kind of.
I'm an idiot.
Well, actually, yeah, we'll take a lunch break, and then
There.
we'll go to the whiteboard, and
I told you to convert it to feet per second, and it was always in inches. Or sorry, feet,
Oh, was it?
PSF, pounds per square foot.
oh wait,
We're in inches. We're working in inches. But oh wait, yeah, the density is in pounds per cubic feet. So wait a second. Oh boyo.
that might have been it actually.
Hold on. I'm gonna return that 144. Yeah, because what is G20? Are you clicking on it too? Here, can you get off it for a second?
Yeah.
It's like it's breaking. I hope it's not right. Alright, well.
Yeah. Units check out.
I think we're just stupid. The units check out? That's not
Well,
good.
hold on, 8 inches or pounds.
That's not good.
Nope.
Hey, but look at our thrust now. 8.89. Which is kind of making sense, but why is that not making sense?
Yeah. The units look fine.
Are you sure? Can do a unit analysis?
Yeah, I looked at it.
Crud. Maybe I've been doing this wrong the entire time. stupid. We're so dumb. I think. Oh no, that's even stupider. Areas. G15. Okay, here it is. Don't touch anything. Yay, that makes more sense.
Well, all right.
Oh my god. I was like doing this and I'm like, what? I was like, look at this unit. And I was foot per pound squared over quartic feet times second squared. I was like, oh no. What is going on here?
So for y'all watching, we've been trying to figure out an issue with our orifice size because our calculator was telling us it would be like 3/1000ths of an inch, which is incredibly small.
It just doesn't make any sense. There's no, well, I was just praying that it wasn't that.
Yeah.
Because if it's a 3/1000th of an inch hole,
oh man,
you don't drill one. You don't drill those with a drill press.
No.
You really don't do that. It's not going to happen. So.
Wow. All right.
I feel okay.
So sweet. We have, and then. Yeah, that's pretty exciting.
So this guy. Okay, so what I'm going to do now is I'm actually going to do this. We're going to remove the 144 from here. Nuke it, and then I'm gonna do this. I'm gonna put it in there.
Yeah.
Oh, made it worse. We're going to town here. There.
Yeah. All right.
So there, now the units make sense.
Nice. we both found it at the same time too. We were both like, wait.
Area. Area is in feet per second.
Yeah.
Or feet per second. Oh my god.
Feet per second. So.
Square feet. Oh man, I'm starting to get. It's
Right.
It's that time. Too much engineering, and the brain starts to break down.
Oh man. All right. Oh boy.
Everyone watching, if there are any people watching, or just 6 people are watching. Wow. Or at least, okay, there's 4 people watching because we're both watching. We have it streaming up here on this computer so we can see what we're doing on the whiteboard, and we have it over here on Zach's computer so we don't make mistakes, and we can see, look at the chat. So if you have anything to post in the chat, post in the chat. He'll read it. He'll read it and respond. But we're working through some issues, some growing pains with amateur rocketry. But we're getting there.
We are getting there.
Yeah. So, like I said, I am not good at math. It always breaks me a little bit. But hey, we're getting things that are working. So we have a thrust value. Our engine with the nozzle that we chose is going to, and the chamber pressure we chose, is going to produce 8.895 pounds of thrust, or just under 9 pounds of thrust.
Not bad.
Little tiny thing, but this is budget bi-prop.
Yeah.
You don't get the luxury of choosing your thrust class.
No.
Okay. So we'll make this look nicer in the future. Right now it's kind of ugly,
gross.
very ugly looking. But
Do we want to?
oh god, we have a divide by 0 error. Oh, because the density is 0. All right. I have the.
Oh, do you have that already?
Look at the constants. Look at the constants tab. Well, okay, it has to be that times the injection pressure because of, like you know how gases work, compressed gases.
Oh, good point.
Like PV1 V1 equals P2 V2.
I see.
The ideal gas law. So yeah, so do that guy times the 200 psi. Did you put in?
Let's see, that is
Do-
19.
Yeah, do the
So it's there.
oxygen density. All right, it's still breaking, which is kind of insane. Oh, because it's like saving. Look, it's saving.
Oh, it's different. Yeah.
Fix it. Have fun with that.
Yeah.
Oof.
And a half.
Big oof.
So delta P.
And then also something that's really, so once we have all this, I'm going to go back and create a flow chart for this specific rocket, a flow chart on how we designed, like what we, like the path we went through. That's why we're kind of recording this whole video. Is it's also, it's kind of a roadmap for us, and then for whoever, if they were like, hey, how do people design rocket engines, right? Or small things, or like whatever. How does an amateur do this? Well, here is a video roadmap of the entire process, and I don't think many people have done this before. And like we're going the full shebang. Like this is design, and then next weekend is manufacturing. Like we're gonna order all the parts probably tomorrow, and we're gonna go do everything's today. This is the engine design, and then we're gonna do the budge bomb. We're going to look over that, show you what parts we're choosing, why we're choosing it. We're going to create a P&ID for the entire system, for the test stand. We're going to design the test stand. We're going to do this all in CAD. So we got a lot of work to do yet with not much time left in the day. Okay, we're on West Coast time, so it's only 1:17 here right now, but we might be here for another easily 6 hours going working on this. But we're gonna grind this out. We're gonna have a really, really good place to be today with this. And we're going to order stuff, and next weekend, next Saturday, probably around 8 to 9 a.m. again, we're going to be doing the entire build. We're going to be manufacturing parts. Yeah, so we got a lot of stuff to do today, actually. We have to make CAD drawings, too. Oh, my God. We have to make drawings. Boop. I didn't think of that. There's a lot to do today.
Yeah.
Yeah, and we're...
well, we can speed run the CAD. That...
Yeah, you can do the CAD part. I can do the drawings. You do the actual physical CAD. I'll start making drawings of everything, and we'll be fine.
That works.
And then I'll do like the P&ID as well. Like I'll start cranking out the P&ID, and then you can like he'll be the CAD master for today.
I am the CAD man.
We're using Onshape for CAD. Onshape is kind of cringe. He's really good at it. I am not good at it because it makes me angry. I am an Autodesk Inventor person, and people are going to also cringe at that. But I used Inventor at one of my co-ops, and it went really well, and I learned a lot, and I can really use it really well. I also like Fusion 360 because of the CAM program you can do. You can program toolpaths for CNC machining, and I've done that before. And easy to use in my mind. At least for me, it's easy to use, but Onshape is free if you can get an educational license for it if you're a student, and you can get it. But what we're showing today isn't specific to a certain CAD program. Everything we're doing today can be done in Fusion 360. It can be done in professional software. We're just assuming that you will probably have access to Fusion 360, since you can get Fusion 360 for home and personal use for free, completely free. No money at all. You can subscribe to it and get the full suite of features with Fusion 360. But what we're going to do today will probably work on the basics of Fusion 360.
Yeah.
You won't need any.
It's fairly simple geometry.
Yeah, it's really simple. So like the CAD models and the drawings, you should be able to do with Fusion 360. We're going to just use Onshape because he likes Onshape, and he didn't want to go to Fusion 360, like I asked. So, yeah.
All right. Yeah, so those of you watching, if you have any questions, put them down in the chat. I think we're going to step away here for a sec to eat some food.
We're going to get a lunch break. We've been grinding for 5 hours straight, almost. So,
but we'll still be watching the chat, looking for your questions. So yeah, feel free.
Yeah, thank you. We'll be back in probably about 10 or 15 minutes.
Yeah.
And we're back. Hello.
Hello.
Oh my god, it's broken. It's broken. Here we go.
Nice. All right.
Alrighty, we're back. Let's keep grinding away here, get some values.
Let's see. All right, yeah, so just as a recap, we went over the NASA CEA, got a couple of values like our O/F ratio. And we're back.
Oh my
god, it's broken. All right.
We had double audio.
You told me not to do that. All right. So now we're going over. Basically, we have our mass flow rates, and we split those into our fuel mass flow and our oxidizer mass flow. And now we just calculated our orifice diameter based off of those two parameters for the fuel and the oxidizer.
Yep. So, just to recap what we have going on over here, we started basically with the NASA CEA values. These are all given either in here, in the output of the program, or in, there's some values that came from right here. So we went down here and grabbed this molecular weight somewhere in here. Yeah, this one. Yeah, and then which was already we already had calculated before, but this is nice to check. And then we started going. We started doing things in the imperial system. Realized that things were not working out. That we were getting, this is the M dot that we were achieving, and once we flipped over to metric and did it, we were getting a proper M dot, at least compared to previously known values from an old calc sheet. But we wanted to do it from scratch so that we can demonstrate how this works. So then we calculated other things. From there, we got the M dot, and then this populates over to here, and then this is just for the M dot. So you can find the M dot in the fuel and the M dot in the oxidizer. And once you know these guys, then you can come over here and find the fuel orifices. And earlier in the day, we had already done this stuff, so we'll make that look a little bit pretty. Maybe you can fix that. But so this is we'll go over that a little bit again, just to recap. This piece here, we already had knowns. So our knowns from way at the beginning. So we, like I said, at the beginning of the stream, we had a couple of preliminary design things we had done. And we kind of determined that we wanted to use garlite tube. It's basically a garlite tube, and it's known dimensions. It was 3/4 of an inch ID, 1 inch OD, and that is now a bounding parameter of this problem. So now our chamber diameter cannot change. Like, it is 0.75, and that's it. And also we had another bounding variable, which was the chamber length. The aluminum chamber, yes. So, yeah. So we're doing some. I just lost my train of thought, but it's fine. Yeah. So we were doing some calculation, or we were trying to figure out. We had this amount of material that we wanted to buy, and we wanted to make sure that we were using it evenly. I just realized that we won't be using it evenly because, think about that, if we cut it to 6-inch lengths, the nozzle is already in on that 6 inches. Remember how
That's true.
fits? So it's not quite, so we might have to change a couple things there, we might have to modify a few things, but if we do make the chamber 6 inches long, we would be achieving an L star of 49.608, which is pretty close to the kind of rule of thumb numbers that are from our book here, our little PDF. The author in here recommends an L star between 50 to 100 inches. So okay, there we go. It's a substitute for determining the chamber residence time of the reactant propellants. So we wanted to be kind of between 50 to 100 as a rule of thumb. We are at 49.608. So we're right there. We're almost right at the bottom of that value. So this is just kind of how it'll be.
Yeah, and one of the hardest parts about this as well is the fact that because it's a budget bi-propellant engine, you kind of have to design it around like chamber parameters that already exist. So like, for example, like the garlite chamber, that's got like we can't really. I mean, those come in standard sizes on a website like McMaster Car, so we can't exactly. We don't have full freedom over what our our chamber diameter is, or what our wall thickness is, stuff like that. So now that we have our orifice diameter for our fuel and oxidizer, the next thing we're going to kind of launch into is actually putting the whole thing together, like what the geometry is going to look like, the upper manifold, and kind of how we're going to ignite this thing and manage all of the propellants flowing through it. So
Yeah, so we're gonna do in a few minutes here. We're probably gonna start transitioning into CAD. I'm still mulling over in my head how we want to do this, because we want to show the CAD, but then we also want to be time efficient. I don't want to just sit here and watch Zach do CAD. I want to do something else. So something else that's important. So I want to try to do some of like the P&ID stuff, but I'm trying to figure out a way we can't to do that. I guess I can. I don't know.
I was thinking what we could do is do like every 30 minutes we switch to just kind of check up on the progress I've made, and then we go back to you working on the P&ID.
The other thing I can try to do is I can try to make it a weird split screen thing. You can work on my computer in CAD so that you can see the CAD going on, but then I can. That's just not gonna. It'll be too hard to see it, I think.
Yeah, it's gonna be a small window.
Yeah, because like I'm gonna modify. I was like, oh, I'll put one like this.
Yeah,
but that's not gonna work too well.
Yeah.
Yeah,
we can just flip flop.
Yeah, I guess so.
But
I wish you could. Dang it! I wish we could set up something, but.
All right. Do you want to jump to the whiteboard and let's spec out or draw out an engine?
Draw an engine.
All right. Oh my God! Let me just. Yeah, I would take a picture of that.
It's probably important.
Here, you can come over here and take a picture.
Yeah.
So there's no glare. Nice. There we go. All right. All right, we're gonna erase all this. Cringe. Big scary.
Yeah, that was fun. One of these roads was really good.
Yeah, it's fine. Oh no.
Looks like it's frozen again.
Ta-da! We've done it.
Nice. All right.
It froze, but now we have things. What book PDF are you using?
Ooh. Nice.
Here, you can start. You can start.
All right. Sounds good.
Because you know what we want to do.
All right. So. thing to keep in mind with this bi-propellant engine is, well, we're calling it the McMaster engine for a reason, in that we're kind of putting together a bunch of parts that already exist.
It keeps freezing.
Oh, all right. So, kind of to go off of that, let's say we have like our chamber. This is going to be some kind of aluminum tube that we get off of McMaster. So. Those parameters are pretty set. We have, so inside of that we have, let me go ahead and draw the walls for those. So inside of that we have our, let's see here, we have our Garlight ablative. So this is the part that's going as the engine is combusting or doing its thing. It's going to, essentially, this wall is going to break down and leave the engine, essentially taking all of that heat with it and cooling it down. Alright, so then the next thing we have is we have our nozzle, which is going to look something along the lines of this. Let me go ahead and... So that's where the nozzle is going to be, and then we have some kind of the injector that we just calculated the orifices. that's going to be over here, and then we're going to have some kind of igniter, and let's just say for now we'll put it like right here. So this is where part of the design gets a little bit tricky, because you need to design some kind of way of moving the oxidizer and the fuel into like a certain position that you want it to. And with the budget Bi-Propellant project, we don't want to do a lot of heavy machining. So this means like literally just taking aluminum discs and stuff and stacking them in a way that's going to manage these propellants properly. So let's just go ahead and put one of those discs on there. We'll get rid of these. So, alright, so we have an aluminum disc up top. We have our orifices there, and then we have some kind of opening for our injector or something like that.
Injector pressure.
Alright. That's actually for our igniter, but then Tom brought up a good point. We have to consider also our port for our pressure transducer. Now, this isn't an essential part of the engine's operation, but it's pretty vital to our data collection.
Yeah.
So, so yeah, let's see. So one of the biggest issues that, I guess one of the first things that we noticed is that this engine is really small. So you have to keep in mind that this is only 2 inches in diameter, and a lot of like flow management parts, like your and fittings and stuff like that, is, well, it's going to be pretty tight up there. You have, let's say we bolt this to this part of the wall.
So like a top-down view.
Yeah.
So if you had this, oh crap, I got a poopy marker. So if this is a top-down view of the engine, just looking straight down on it, and you say that this is 2 inches in OD, well, fittings for certain sizes that you're looking for or wanting to use only come in certain sizes and certain geometries. A lot of them have hexes on them so that you can actually get a wrench on it, and they're usually oversized so that you can get that they can handle high pressure. The fittings we're purchasing are able to handle over 1,000 psi. We don't need 1,000 psi, but it's just what we can really get. So those fittings usually have hexes that are anywhere from the hex itself, the flats between the hexes. So if you do the hex, the flats between the hexes could be like 7/16 of an inch, or 0.4375 inches, or higher, depending on what the tube size, the tube diameter you're looking for. So if you think about this, you have 2 inches in OD, and now you have this almost half-inch wide part, but that's between the flats. Between the points is even wider. I would say it's almost about 0.5. Mm-hmm. So at your max, because you're going to have to spin this thing, you're going to have to spin this fitting into there. So you have to take into account the bolts on the top that are going to bolt in to the chamber to hold the injector down. You're going to have to take into account all of these like bolts that are sitting around here. Let's just say there's 6 of them. And now you have to fit these hexes in here somehow so that they can spin on their own and also not interfere with each other or these bolts. And the space management becomes really vital and tight. So you're doing these little hexes and stuff, and these are like your fittings for your fuel and your oxidizer. And now you want to add a pressure transducer tap. So you have to add another one of these fittings possibly, depending on what fitting you're looking for, which ones you can find. So now you're adding even a third hex in here that has to clear all these things. And then finally you're adding an igniter, which in our case is going to probably be a glow plug, which has a smaller hex, but is a hex nonetheless, and that's got to fit in there as well. So we'll just say this is the glow plug. Pressure transducer, or PT. And then you have, it doesn't matter, this is just arbitrary, but then you have fuel and oxidizer. So now you have 4 things up there, and these are all cap screws.
Yeah.
These are all the bolts. Bolts times 6 that you have to fit in this 2-inch space. And it becomes really, really tight, and it's a space management issue, and it's really hard to get it all to work properly.
Yeah, and some context too on what exactly these fittings are. So like, you have, so the fittings we're referencing look something along the lines of this. You have a thread here, a hex here, and then you have some kind of flared end fitting. So this part is called an AN fitting. It just stands for Army Navy, and these come in like dash sizes. So like a dash 4 AN fitting, a dash 8 AN fitting, stuff like that. And in order to find like what size that actually is, you actually just divide that by 16. So a dash 4 AN fitting is just a 1/4 inch. Now this bottom part here is an MPT fitting. That's a National Pipe thread, and essentially it's like any other thread you would find anywhere, but it's got like like a very slight angle towards it. I guess a taper. That's the word. I guess it more accurately looks something like this. And as you thread it in, it gets that resistance between the walls gets tighter and tighter.
And it's meant as it was designed originally as a method of sealing, because you put those together, and if you think of two cones that go along each other, like this, like just exaggerated cones. You have these two cones, and when you mate these, you have this, theoretically, you have this entire sealing surface here and here that seats with here and here. And that makes up the sealing part of it. But then you also mix in a little bit of other fun stuff like NPT tape, which is actually a lubricant. It's not really. It kind of acts as a sealant in some cases, but excuse me, it's meant as a lubricant to get the threads to not gall and do weird things. Mm-hmm. So that is its own issue in itself, just because those require a lot of. Can I use your marking? Actually, no. Here, I got it. There we go. Usually NPT requires a really, really deep thread. Mm-hmm. So for 1/4 NPT, the minimum thread engagement is, I think, 0.26 inches. So you need at least a plate 2.6 inches thick, so that you don't run the risk of. I mean, these are standards. You could do it undersized. You can, because this is so close to a 1/4 inch. You're like, I'll just remove 0.10 of an inch, and it'll be 0.25, and it'll be fine. Like, it will work. But these are just like some of the standards that they come up with. But in our case, we were really looking at this, and we kind of deemed there was a little bit too much. It was too dense. There wasn't really space to do this properly. Like all these hexes with the cap screws, it was almost. I think it was basically physically impossible. I think it was physically impossible to put all those fittings on top. So we came up with a different concept.
Some ideas we bounced around is the concept of a top hat engine. I won't go too deep into this because it was more of a joke. But one idea that we had thrown around was just a very large plate up top to store all these fittings and stuff, and having some kind of channel to bring it down to where the orifices would be, the pressure transducer channel, stuff like that. But we decided that it would actually be a better idea. I'm actually going to erase some of that, and we add, say, like a thicker plate up here. I think that's about 1/2 inch, and then that's 1/4. And then we have the fittings come in from the side. So that is not.
Oh, that is not a fitting.
No. All right, sweet. Fittings. All right.
Oh no, we've done a freeze.
Is it?
No.
Oh no, it's still there. I'm just very bad at drawing fittings.
So I thought it froze on here. Okay.
We decided that we would have these two fittings that stuck out from the side, from this thicker plate. So we have our oxidizer and fuel coming up from the top there. And then we have, say, our pressure transducer channel on the top there. And then our glow plug somewhere around here. That way we have plenty of room to actually torque these fittings. And then at the same time, this is definitely not to scale, but if, say, alright, so there's our glow plug. And the way that we're actually securing all of these down to the chamber bodies, we're going to have these screws that come in through both of the plates and then actually into the chamber body, or the chamber wall, and we actually plan on tapping those holes and screwing them all the way through. But essentially what we did to size these screws is we basically went as big as we could. So these are going to be a 1/4 20. And then that's, I think these are going to be an 8 MPT. Yeah.
Were these 1/4 MPT then, I think? Or were they 8?
Those were 8 as well. Those look like 1/4 though.
We'll figure it out.
Yeah.
Yeah, so it's just, like, again, a space management issue. So when you do this, if we, like, I'll draw another picture down here. We'll do, like, a cross-section of that top piece. I already screwed up. And, like, this is not to scale at all, but okay. So, oh my goodness, it's all over the place. So. So this is like a cross-section view of this top piece here. And this is where you have your NPT fittings that thread into this space, and then it has the corresponding thread on there for this is where the pipe interfaces. And then you're going to have, and you'll have another one over here. And then this is where, I'm going to contaminate one of these markers. So you have your, like, fuel that's flowing like this, coming in here, and then that's when it gets into the engine. So you have these fittings that basically for your flow path. So that's kind of what the flow path would look like for injecting fuel into the engine or oxidizer. And we'll have the same situation over here, and it's pink, but whatever. We'll have your fuel coming in, and combusting and reacting and burning and doing its thing. So that's kind of like the cross section of this top area. Cross section.
Yeah. And the nice part about this too is it leaves us more room for. We kind of mentioned, like, we would have 6 screws up top securing these caps to the actual chamber, but the good thing about this design is it kind of allows us to have screws that are rated for pressures far higher than what we're actually achieving, so we're well within a
factor of safety with this one.
Right.
Yeah. And then, I don't know if you highlighted this, but down here, there's going to be another retaining plate that's going to come in a little bit, and it's going to catch that nozzle so that it doesn't come out. It's going to kind of look like that. There'll be another plate, and then you'll have the same cap screw guy going in there, and there as well. So you'll have screws going on there, and that retains the nozzle from keeping it from coming out. And then right here in this corner is going to be an O-ring. Yeah. And that O-ring will just keep hot combustion gases from going from around the nozzle and out the sides and causing all sorts of havoc. So then we're also going to load this area up with RTV sealant to really, like a high temperature sealant, to really keep it from doing a thing. So,
and now, I guess one of the first thoughts that one might have about this design is that there's a ton of leak paths. So especially like right here, there's an opportunity, out the sides, up where the screws are, stuff like that. And in a more traditional rocket engine design, there would be an upper manifold. Well, essentially, you try to minimize the surfaces you have, like, contacting each other as much as you can. You'd have an O-ring gland with, like, a very, very fine surface finish, or something that you can get your O-ring to seat properly and actually create that seal. But in this case, since we're firing our engine for 2 seconds max, it would we're not too concerned about the leak paths there, and there was also, let's see, I think one of the other ways that, in addition to this O-ring here, that we were going to minimize this leaking issue was, what was that paste called?
RTV seal?
RTV seal.
Oh no, this or is the graphoil seal?
No, okay, we forgot both of those actually. So, in order to minimize some of this, we have essentially it's called graphoil, which, if you can imagine, it's like, I want to say it's like tin foil, but made out of
Graphite.
graphite. Yeah.
Carbon. So it's really compressible. It
Yeah.
can be like squeezed, and it works really good as a gasket. You make a gasket out of it.
Yeah.
It's really easy to cut and really easy to mold and work with.
Yeah. So if you can imagine, like, we're probably gonna have one of those here, and then probably, I want to say,
We'll have two. Yeah, we'll have there and
we'll
there.
have them there. So, and this, in addition to the RTV sealant, should take care of our sealing issue for the 2 seconds that we'd be hot firing, or less than 2 seconds. So, yeah, let's see. In regards to the pressure transducer, so since, again, we're working with such a small space, it's kind of tricky to get a good positioning for this. So we have the two fittings coming in from the side for each of our orifices here. Now, ideally, we would put the pressure transducer channel here, which we still can. Just the tricky thing here is we're going to do something like drilling a hole down here and making some kind of flow path here. And this is where that that mill down,
The little, the little tiny mill. We're gonna essentially, if you look at this plate from, we keep doing this. If you look at it from like bottom up, like now you're looking up this way at it. You'll have this hole coming in from the top, and then we're gonna mill a notch like this over towards wherever the center or wherever the port is that comes through the injector plate into the chamber, and that'll allow the flow path to come up through this hole and then go over and then up again through the pressure. So that's just, it's not necessarily a flow path for hot combustion gases. You'll probably have we'll have a little bit of that happening, but mostly that's, the pressure transducer is going to be it's going to be off of a line that's really long, probably about 1 foot long, and that line will have air in it, and that air acts as a buffer for the sensitive pressure transducer being exposed to hot combustion gases. It won't be because there's that air buffer in there, and the engine will only be running for a second or two, so there's not going to be a ton of heat transfer up this tube towards the pressure transducer.
Yeah.
So, but we have to make this little notch in there so that we can get the flow path to come over, like come down, over, and then down again into the engine through the injector.
And then, in regards to the igniter, just kind of sitting farther back, it's kind of hard to get a sense of location, I guess, but we just have another hole coming straight down here. And essentially what a glow plug is, it's like a spark plug, but for like RC cars.
It's not a spark plug.
Well, it's not, but it works similarly.
Yeah, well, in the case of RC cars, the glow plug, we'll energize the glow plug with like 1.5 volts, and there's like a little tiny coil in there, I forget what the coil is made out of, which will glow. And in our case, with this massive hydrogen and oxygen rich mixture, it is going to ignite.
Yeah.
And it might detonate, and we might, I don't know if we can avoid a hard start. It might be hard to avoid a hard start with this engine, but it's going to, that coil gets hot enough that it'll ignite the mixture. But in the case of an RC engine, when you keep running, there's a reaction that happens that even though there's no electricity being run through the plug continues to glow. It's like a diesel glow plug, and when a diesel engine, when you compress that air to fuel mixture, it gets really hot. Your compression ratio in gas or diesel engines is really high, higher than internal other gas-powered vehicles. And it's kind of the same principle, but a little bit different.
Yeah, that's true. Yeah. All right. Let's see. I think that's it. Yeah.
Yeah, I think that's pretty good. We'll probably, do you want to do the CAD design on my computer, right? Because you have to show it, so you'll have to do it.
Well, it's like we can just kind of I guess a further note on this as well. you don't have to design like your entire engine like this. This is just a way you can do it. You can, I've seen it done like with much smaller engines too. Well, I guess just in general, you can actually just weld tubes onto this surface here and then just kind of bend them out. So let's say like if one way to avoid some of the costs here, like if you already have experience with welding or have access to welding resources, I would definitely consider the possibility of just welding some tubes onto there and maybe try something other than aluminum. But given the fact that we don't have any welding resources and just our budget and the way that this turned out, we think fittings is the best course of action. But yeah, I think.
Yeah, so I guess before, let's erase this. Or you want to take another picture of it quick? Or do you think it's useful?
I might as well.
Just keep taking pictures of things.
Yeah.
We're going to quickly do like a little mini P&ID. We'll just do a P&ID really quick just to show you what it's going to do, because I think we'll just stick with, we'll put it down here, because it's going to be the same thing as in the software, which is we're going to be using Lucidchart. And I'll show you, like, maybe we'll start doing the CAD, and then I'll flip over for a few minutes and maybe do a little demo, just a couple parts into the Lucidchart to show you how it's done, but then I'll do it separate than what you're doing.
Yeah.
So we'll erase this, and we'll kind of do a little quick P&ID for this guy. So it's not going to be like, is that the, there's a good marker here. Yes. Nice. So we're not going to be doing like anything, like it's going to just be very, very rough. So the engine, I think we're going to be hot firing in the horizontal configuration. So we'll just show it horizontally. So we'll just do it like this. We got our little engine here. We got engine. This is going to be a little, this is going to be a special P&ID. We're going to add a little bit of colors to it, but there's the engine. Even though the flame will be kind of like blue. Well, actually no, because all the stuff burning, it'll be kind of red. Yeah. So, ooh, all right, let's get smart here. Okay, we're gonna have two high pressure cylinders. I'm gonna have one up here. Oh boy. Speed up. One there. Like that, and we'll do fuel is red, oxidizer is dark blue, because I like dark blue. So we'll do the oxidizer first. So O2, and we'll come out of the O2 cylinder, and we'll have this little regulator. This will just be like a nitrogen regulator. And then there's a little that comes out the bottom. So it's kind of like, it's a P&ID that is a little like, a little bit more spicy in terms of the drawings. So we'll come out of this as regulated fuel in terms of pressure, regulated fuel pressure. We'll come this way, and then we're going to go through a solenoid valve, and then what was the image for? What was the P&ID picture for a check valve? Oh, you actually kind of.
I think it's like two lines and then a diagonal line in between it and an arrow, I think.
This is how I would do a check valve, but I'm going to get yellow. So it's like a ball seating on a thing. I think it's been done like this before. That's what we're going with. So that is literally how simple this is going to be. Same concept over here. We got regulator. These are just the gauges on the regulator. And then we got fuel line coming over. little symbol for a solenoid. And then another check valve symbol. Oh. Drew it too low. Another symbol for a check valve.
Nice.
A big check valve. And coming out of the check valve and into the engine. That is literally the PNID. There it is. That is the PNID. I probably should have drawn it down here a little bit. But that's the basics of it. And then we're going to have pressure transducer to measure the chamber pressure. And then the glow plug will just be something else. It'll just it's electrical, so it's not going to go on the fluid PNID. Yep. That's literally it. That is how simple this engine is going to be. So we just have the check valves in case something bad happens. We don't want that propagating back up the line and destroying upstream fluid components. We don't want the solenoids getting nuked. Because if the solenoids break, then they're just gas. There's just gas leaking out and going everywhere. So there's going to be 2 check valves, and then we have 2 solenoid valves, and then it's just regulated pressure from the bottles. And that's it.
Yeah. A good thing to note too is it might be tempting just to have like a traditional ball valve there, one that you would move with your hand or something like that. And one of the reasons why solenoid valves are so important in a system like this is if something were to go wrong, you can literally just pull the plug. Those solenoid valves, you can buy them such that without electrical power, they're closed.
Normally closed.
Normally closed, yeah. So you can literally just pull the plug and you stop all the propellants from going into the engine, and you don't have something that say like, oh, well, this all of a sudden caught on fire. It's probably not a good idea for you to run up there and close the valve when something could explode. You can do it all remotely.
Yeah, and there's always so much risk. There's a certain amount of risk you have to take, because you could say, well, what if these like fail? Well, now you're propagating fuel or some sort of high pressure wave, propagating a high pressure wave up here, and you might destroy these. These might break, and then they don't shut down, and you're still. But like in that case or that scenario, there's not really much you could do. It's more, it's like it was a failure on our part in some way, shape, or form in the engine, that it either hard started and caused that pressure wave, or something else happened and things started failing. Or there was a materials incompatibility for some reason.
Yeah.
So all those things could happen, but there's always a little bit of risk you have to take on, and also you can only put so many safety features into the system before because you'll never be able to account for everything. It'd be like saying, oh, we have to have a safety feature because if I walk up to the test stand in this way, shape, or form, I could trip over this exact crack here and fall, and my hand could land on this, and this could cause this to happen, and you just can't do that. It's just not feasible. It's not financially feasible. It's not procedurally feasible. You can eliminate as much as you possibly can. There's like stupid, easy things like making sure that the bottles are standing upright on the ground, and making sure that they're just not laying around, that things are constrained and restrained properly. But in terms of like, it's like, oh, well, maybe I'll add like 40 check valves here so that in case one fails, the next one picks up. No. Yeah. Then you have a huge pressure drop across your system, and you need to have this at like 1,000 psi to get the flow rate through the system. Yeah. Like, there's only so many things you can do before it's just wasteful.
With any system, there's going to be some kind of risk involved, and I guess the point is, while it may not be the safest thing in the world, it's safe enough, you could say.
Little glow plug. Yeah.
So
yeah, that's basically the PNID, and that's what I'm going to make in Lucidchart. So there isn't really a huge reason to show you making it in Lucidchart. I might show you the beginning of one. I'll be like, here's the engine, here's these couple of valves. They're like, this is how you draw a line between the two things, and then kind of then I'll switch back over and let the CAD let you continue CADing the heck out of it, and then I'll maybe come up with some other stuff to work on. But
cool. Yeah, and then I guess after that, so once we have our PNID and our CAD for this as well, do we want to go into test stand design now, or just get a general kind of sketch for it? I think it'll be fairly simple though. We're really just making a table.
Yeah, you can do it.
But So I guess another important part about this as well is like, all right, well the engine's got to sit somewhere. So if you can, I'll do something down here. So, but all right, so we have our engine, and we have to. We're gonna put it on some kind of table, something like that, and there's multiple ways in which you could secure this. They make things like, so you could do things like U-bolts over the top. There's, I believe they're called like conduit clamps. There's these little things like that that have a bolt through them, or you can do like a U-bolt, like something like that, to actually secure it to the table. One thing you want to be careful of, though, is that the force of your engine isn't actually going to shear off those bolts as they're sitting into the wood. Now, with our low-thrust engine, I believe it's like 8 pounds.
It's going to be 8 or 9 pounds of
Yeah,
thrust.
so not too much of a concern.
We should be able to achieve much more clamping force with these than, and also be well under, we're going to be leagues under the bolt shear force for those bolts. But it's always better to oversize everything. You never know. Because, like, for example, there's a hard start. I said that weird. A hard start.
Yeah.
And this thing blows up. Well, that's a lot of force.
Yeah.
And though the engine's exploding, and you can't really do anything about that, and at the end of the day, it's like, well, the engine blew up.
Yeah.
But if you have everything constrained properly, well, if you have a hard start and you don't want the engine to pop out.
Yeah.
Like, you might end up accidentally, you might blow out the nozzle or blow out something else, but everything else stays in constrained, and that's super important, is making sure that it's all constrained. You don't want loose things. You don't want things that move and shake and vibrate, because you just run into more issues. Some things need to be unconstrained so they operate properly, like dynamic systems that are spinning or rotating. You can't constrain them, they'll break.
Right.
But this is a static system. We want to make sure that it stays static and that it doesn't move. So.
Yeah, and one important note as well is, in order to keep everything a little bit more secured, maybe that looks like building some kind of securing feature into the engine itself. So maybe we have, maybe one solution with that would be slightly oversizing the retaining cap for where the nozzle is going to sit. That way, when we clamp it down, it's got some kind of force that it can act against.
There's a lip there. So if it slipped or something, or even it just, that is the retaining feature. That oversized ring. There's a lip there and there where it mates with something on this table, and that's the physical feature that prevents it from moving.
Yeah. So then we have something like those clamps there, and then kind of, I guess, off to the side we have our oxidizer and our fuel lines. We have our pressure transducer over here, and then let's see, I guess I drew those a little bit too long, but one thing we could do is we have some kind of, say, like piece of plywood there. We have this secured to like some 2x4s or something. We could have a panel we secure to the back there, and this kind of goes into kind of making your test stand safe. So if we're going to have like a bunch of, we're going to have bottles behind here, that looks like a person.
That's a person bottle.
So if we have our bottles back over here, we want to make sure that whatever goes on over here doesn't damage those bottles and cause them to explode. So that could look like, all right, well, we have a piece of maybe plywood right here that we secure our solenoids to, our pressure transducer to, something like that, and then maybe we reinforce that with like an aluminum or steel plate on the back of it as well, something like that.
Yeah, and then pass the lines through the plate and bring them out over to the two bottles.
Yeah.
And that way, thing goes boom, things go wrong.
Yeah.
It's contained to there.
Yeah.
Any sort of objects that go this way are going to get hit, or going to stop because they're going to get absorbed by this plate. And I'm not expecting, like, this thing is small, so if something goes wrong, it's going to be high energy, but not high energy enough that it's going to be catastrophic, where you, like, blow a crater in the ground. No, that's not going to happen. But you still might have parts that are going to go this way, this way, this way, all over the place. So you want to kind of contain it. Some other ideas and things is I've seen people put sheets or make a box of acrylic or plywood around the engine, and then fill it with sand. They made like a box and put sand around it as like a little bunker thing. So if the engine blew up, all the sand would absorb all of that, all those parts flying
Sure,
around.
it's not a bad idea. Do something like a moving blanket, maybe something. Well, I don't know. Yeah, it might catch on fire.
Yeah, that might burn up.
But yeah, definitely something we'll brainstorm a little bit here in a sec after we get the PNID and the CAD a little bit more finalized. But yeah, now a lot of you are going to be wanting something like a thrust measurement, or we mount a load cell to the test stand and get a thrust from that sort of method. Now, it sounds, I guess most of the cost didn't actually come from the load cell, surprisingly. If the main issue is the fact that all of the other testing infrastructure
Static.
is static, right?
And
so
also hard lined.
yeah,
So,
if you were to turn like these connections into something like a metal flex hose you'd find on McMaster or something like that, those can actually get expensive fairly quickly. The alternative, of course, is something like vinyl tubing, which is prone to melt.
Yeah, it would melt, but it can withstand the pressures because we're not anything crazy. Like
Yeah.
you can find tubing out there that, like flex tubing, that can handle 200 psi. It's just the next question is how much is going to cost.
Yeah.
And also, we're at such a low thrust that even those flex lines that you can buy, they enact a force on the engine. It's going to put a torque, like as you twist them and put them in there, they're going to want to twist and move around, just because they have internal stress and internal. Like they sometimes they don't want to. They're not as flexible as you think they're going to be. Like if you've ever taken a vinyl tube and bend it, and then it like kind of springs back. So that's a force that's going to push on the engine, which is going to make the load cell reading inaccurate. You can adjust for it, but it's still a force acting in some different way than you want it to be acting.
Yeah.
So, and we're such a low thrust that it's going to be. I don't think we're going to really get an accurate force reading, especially and also using really cheap load cells. It gets even worse.
Yeah.
You have more inaccuracies, more errors, and a harder time calibrating those. So
Yeah. And that kind of explains why this guy is here, this pressure transducer, because we can take the chamber pressure and kind of back calculate it out to what our thrust would be.
yeah. So kind of like we're doing in the Excel sheets over here, we can essentially make a little table off to the side that says, hey, this was the recorded pressure during the test. Put that into there, or you put it into a column that, like, we're going to have it actively taking pressure throughout the test of the chamber during the hot fire portion of it. And hopefully we'll get a couple readings. We'll get, not by a couple, I mean, hopefully we'll get more than 20. More than 20 over those 2 seconds. I'm hoping to get 10 per second at least, or even higher. I'm trying to maximize as much as I can. I want to have as much data as possible. And then essentially take all those values, put them in the table, and then literally have another cell next to it that you reorganize some of these equations that we have over here, and you should be making assumptions like such as your fuel oxidizer ratio that you can't necessarily measure. We have a designed OF ratio, but in reality it could be off a little bit. And that's when you add like things like flow meters into here, but those are really expensive, and that is like a non-starter for this project. So we're making assumptions like as saying that the OF ratio was perfect, it didn't change. The like gamma was this gamma, like everything what the NASA CEA told us is what we're assuming in that calculation, and then we should be able to backtrack out what the thrust measurement was based on the chamber pressure. And we're hoping that it's pretty close. Because if we read a chamber pressure that's close to 100-ish PSIG, that's pretty good. That's going to be that we did this right. We calculated it the right. We did the right thing. Now there could be other inefficiencies and things like that, but that's the number we're shooting for. We're shooting to record a chamber pressure of 100 PSI.
Yeah. So I think we should jump over to
get going on CAD.
Yeah.
So he's the CAD man. He's the CAD master. He's gonna show you the most efficient way to do it, which is variables, right? Adding variables, parametric modeling.
Yeah, that's one of my favorite features of Onshape is it makes it very easy to do stuff like that.
Let's get going. All right. Do we want this still? Might as well take a picture of it.
Yeah, good point.
I'll flip her over here to screen share. All right.
guess if you don't use these cameras for a while, they go into sleep mode.
Oh, is
yeah.
it frozen?
Yeah, it like slept, and then I turned it back on. So, all right.
What are we going to do? This? Do we want?
You're gonna do it on my computer.
All right.
So you're gonna maybe you can see. You have. I got to turn you on.
Nice.
Good. Good. Okay. So he is in control now. We have like a little setup going here with a USB dongle that has buttons on it that you can activate certain USB lines. So he's going to be in control, and we're going to kind of sit here. And so this is on-shape. This is what we'll be using. Like my computer might start spooling through this entire thing. It's going to be in some serious demand, running a stream and also doing CAD.
All right.
So
So
let's create a brand new thing. Let's create a new folder or document. Bi-Prop live. We'll do it live.
Indeed. All right. So, I'm sure as most of y'all are watching this are pretty familiar with kind of the basics of how CAD works, but essentially it's pretty similar to Inventor in that you have your, I guess the interface is somewhat similar, but let's say one of the features that I want to focus on is this idea of parametric modeling. So actually, I'm going to come over here to this X thing and say like variable. So let's say I'm modeling let's say I'm modeling the chamber, right? Just a real simple like hollow tube. So you come over here, you make your variable, and you call it like say outer diameter, and I want to make that like 6.25 millimeters. So I make that variable. Come over here, let's say ID, and then I don't know, maybe I want to do something like yeah, something like that, just for the sake of demonstration. So then come over here, make your sketch on this plane, and then I draw my circle there, and then I draw my second circle there. So the way that you assign these is pretty straightforward. You just type in OD, and then there's your outer diameter. And then for the second, where to go? Second part here, you have your ID. All right.
Yeah. So essentially, you're just typing in the variable names.
Yeah.
For you're using the not just the constraining feature. What is that? The dimensioning.
Yeah.
Like you're dimensioning that part, but when you hit dimension, instead of typing in a value there, you're typing in the name of the variable that you already created, and then it essentially pop. And then it's like, hey, I know you want OD, and I know OD is equal to 6.25, so it makes the OD 6.25.
Exactly.
And that's really nice for changing things. So like if you end up saying, hey, wait, I didn't want 6.2. Instead of going into the exact sketch where you typed in 6.25, you can just click on that variable, say, hey, I want to make the variable 8 millimeters now.
Yeah.
And then it'll automatically fix the sketch. The sketch will change.
So like, let's say, let's name this part L-star. I know this isn't exactly accurate, but let's just say, all right, so you have your sketch here. I'm going to go ahead and extrude that, and then so it works with extrusions as well. Just about anything you can dimension, you can have these parameters. So let's say I wanted to change my ID to something a little bit larger. Change it to 4 millimeters. Your sketch goes away, but as soon as you change that parameter, you come back, and now it's a little bit longer than it was before. Important thing to note with parameters, it can kind of be a little bit finicky. So let's say I don't know, just be careful with your naming, like you can't have any spaces there, or special symbols it usually doesn't like. But it's essentially pretty straightforward. And once you have a very complicated model that you want to make a lot of changes to, say like I have a model of the nozzle that we had gotten off of the rocket system. This one, yeah, I forget what that company is called.
Yeah, it's that.
Rocket motor components, yeah. So if I had a sketch like this, and maybe we decided, well, we don't exactly want this motor, I could set literally all of those dimensions to a variable and just go in and change all those variables instead of remodeling the entire thing. But Yeah, a couple other notes with what did it freeze again?
Should be back.
Okay. Yeah, so a couple other notes with Onshape. You have a lot of your extrusion features here, kind of other ways you can manipulate the 3D model there. Let's see. When you're making an assembly, the way that it kind of does it, it's a little bit unorthodox in terms of the way everything is set up. So the way that this works is you have a part studio and then you have an assembly. So let's say I'm just going to go ahead and make like I don't know, just a regular cube. I'm going to demonstrate. Let's see. Let's do this. All right. I'll do up to next. That's not what I wanted. All right. So let's say I wanted to. So if I'm making an assembly, I'll you just insert your parts there. Not exactly. Yeah, actually, I guess this is a good chance to demonstrate the fact that your variables don't span across different part studios as well. Yeah. So, kind of getting back to an assembly, the way that these works is you have like mate connectors. This is essentially a way for you to mate specific parts of geometry to other specific parts of geometry. So I could put a mate connector here on this part. Actually, I kind of want to do those in part studios rather than in assemblies. It's just this little circle here. So I want to mate this part to that face of that hole. So I put a mate connector there. And then I want, let's see, I want to have the middle of this tube go where that mate connector is. So I put that there in the part studio, come over here to the assembly, and then you can just click this fasten mate here. You select the mate connector, and then you select the other one, and it'll put it exactly where you want it to. There's a bunch of different other features here, or I guess types of mates that you can mess around with, but that's essentially the most important things that I'll be using. Nothing too complex. I mean, I guess one thing that I should go into as well is the most complicated thing about these models is the hardware, actually. So you might be wondering, all right, well, where do I get my fittings from? So instead of spending the time modeling those, let's say I wanted like a flared fitting for the side of our engine. So I go, I go to a website like McMaster. I choose the exact part that I wanted to get. You see this little symbol here, and you can actually just download. Let's see, Onshape likes step files, so I would download those rather than the SolidWorks file. But let's say I wanted that part, so I download that. I come back over to here. I import the part into my. Let's see. I'd import the part into basically just the main workspace. Okay, and then once that's done, you go back to insert and then
Wait for it to come up.
yeah, there it is. All right, so then there's your fitting, and it's about pretty straightforward. Let's see. One last thing is if you're modeling hardware, come over here to standard content. Let's see. So like here you can select your, so let's say I wanted a screw or a bolt. You can select your screw or bolt size. We'll probably be going with something like 1/4 20. And it'll probably be about 1 inch long, I want to say. And you can select the different head types. So like, let's see, I don't know, let's just go with round head bolts. And you can insert those. And it, not exactly. Oh man. Yeah, so I forgot. Yeah. Anyway, so you can insert those, and I don't know, let's say I wanted to mate this screw. Oh man. Mate the screw to that tube there. So don't know why you would want to do something like that, but you can. And another important note is that you don't necessarily have to add mate connectors to all of your parts either. But yeah, that's essentially the basics of what I'll be doing with this engine CAD. Nothing too incredibly complicated. It's just that's pretty much it. But
Yeah, indeed. Sounds good. Alrighty.
but yeah, do you want to dive into the PNID?
Oh yeah, I guess we'll look at that a little bit.
Yeah.
Put another tab here. Lucid Motors. So this is not our PNID. This is actually mine for a different engine I was working on, and involving LOX and IPA. This is okay. Oops. Yeah, there we go. So this is the free trial version of it. This is as many components you can actually fit during the free trial version of Lucidchart, but it's really nice for doing what we're going to be doing. So essentially, I'm going to just make the basic fluid system that I showed you on the whiteboard back there, and we're going to make it in here so that we can print it out and have it. It's just one of those things where, as engineers and as programs and things are being made and parts are being done, you make fluid systems and stuff. So, or make it PIDs for fluid systems, so that other engineers can see them and other engineers can use that information for whatever they need. So we're going to make a new one, blank document. Oh boy, over my document anyway. Oh, actually here. I'll just do this. There's probably some extras in here that are just not good. Oh no. That should allow us to keep. There we go. Bang. So. We are kind of going to be looking for some like you got process engineering stuff here. Yeah, let me try to find what I'm looking for. Is it process engineering? I don't think it was process engineering. I forget. It's been a little while since I set this up. No, nothing there. Don't want. Maybe we do want a template. They start from a template somewhere. But yeah, so there is a ton of different things you can do with this stuff. I totally forget how to do this. Maybe it is process engineering, I'm not sure. But we'll figure it out. Learn more. Yes, it is. Oh, my bad. I'll go back in there. We don't need equipment. We probably... We're going to want vessels. We're going to want instrumentation, and we're going to want valves. Use selected shapes. Bang! Now they're over here. So we can get rid of stuff like this. We don't need these guys. So, essentially, we're going to start with a... They have a nice engine shape somewhere. Let me see if I can grab one more thing. I don't know if it was in there with what I wanted. I guess not. I guess maybe they got rid of it. There used to be another. Oh no, it's in pumps. I mean, we'll add pumps to this. It is not. They call it a ejector, so it's literally a rocket engine. It looks like a little rocket engine.
Actually, yeah.
So we're gonna use it as a rocket engine. Yep. And now we'll get into adding fun stuff. So we got gas cylinder here. And basically make what we made before. Got one gas cylinder. We'll rename this guy H2. Yeah, my computer is doing a spool.
I can take off.
It's gonna take off. Basically. Yeah, Lucid Chart's pretty smart, honestly. Unless I do that. Now it's not smart. And we'll do O2 for oxygen. So we'll use this little this back pressure thing. I'm going to assume that's like we're going to use it as a regulator today. So we'll have a little regulator guy going here. Oh gosh. Yeah, sometimes it's a little finicky to work with, but it'll work. So then I can do this, or not. Come on. Click there. And it brings it, okay. Sorry about that. We're gonna go from there to there. Boom! There we go. So this is our regulator. And we'll do the same thing. We're gonna control V that. Drop him up there. So we got two regulators, and then we're going to go to, excuse me, our solenoid valves. And then we're going to add a check valve. That's the symbol. It's a different, I mean, there's multiple symbols for everything, but let's just pin some symbols. All right. Yep. So I'm just drawing lines, and it's super easy. And just like that, P&ID for the engine is basically done. We will toss in, so they have transmitters here, we'll pressure indicator. We'll just call it, this will be our pressure transducer. I keep clicking too many times. Come on. Call hit PT for pressure transducer, and we'll come off that like that, and that gets reported back to our Arduino. So yeah, so this is basically the P&ID for our project. We're going to be going from high pressure cylinder regulator pressure down to about 200 psi through the solenoid, through the check valve, and into the engine. And that's basically it. So cool. Nice. Alrighty. Do you want to flip back over to you then?
Yeah, sure.
Yeah, so let's, you can finish the sketch on there, and then we'll bring it up on here.
All right.
Yeah, and also this thing saves it automatically. So, and then you can just click File, and you want to go print it, hit print, and that's what it'll look like. And you can kind of just use that for some sort of diagram or whatever you want to do for it. But it's just like a basic, like this is not supposed to be professional P&ID. It's literally, it's good enough for what we're working on. But it's another free resource. You have limited use. The other thing is drawl.io. You could use drawl.io, which gives you, I think, unlimited capability for drawing, right? Drawl.io.
I think it does, yeah.
Yeah. So you could use drawl.io, but I just like this because I used it once and it had a lot of the variables I was looking for. So yeah. And yeah, do you want to flip over to here?
Yes. Something is not right.
The engine's breaking over there.
Yeah. All right. Yeah, you can go ahead and actually flip back. It might. Here, let me hop up there. So then.
Oh, hold on here.
Oh.
He's not himself. Sorry. Cool.
Nice.
Alrighty.
All right. So. Let's go over here. So. I guess what y'all are kind of looking at right now is me modeling the nozzle. So let me bring that over here. So I'm taking these dimensions and I'm basically taking the center line down through that throat as like a point where I would revolve this sketch across. And you can see over here on the left all my different variables, and I can just go into here. If I wanted to change the length of the nozzle, I could go over here and change length, or let's say I wanted to change the throat diameter. I could come over here and change, actually, let me go ahead and do that now.
Well, that's a diameter. You want to divide that by 2.
Yeah, that's a good note as well. So when you're modeling these things, and especially doing like a revolve, you want to make sure that these parameters reflect what's actually going on in your sketch. So like this value, it's everything here you see is in millimeters, but this is actually half 0.291 inches. But it's doing a little funky things right now. Because
Wait, is that half?
I believe it is.
You just have throat. You want to do throat divided by 2.
Well, no, throat is already divided by 2. Like this is 0.291.
I would just say do 0.291 as the throat diameter.
Well,
Oh, I see.
yeah. So the issue with these parameters is they don't really like. Well, Onshape doesn't really like combining text and numbers. So if I wanted to do throat divided by 2, it wouldn't like that. Like it has to just be like when you dimension something, it can only be the
I didn't realize that.
Yeah, it's not exactly the most fun thing, but let's see. So length converging. Let's see throat.
Did you do the angle yet for the Xing?
Yeah, so
Oh,
the
yeah, it's
angles are
right
correct. I'm trying to figure out why it's still being sticky.
Pretty sure
Oh.
that's...
So that's not all. Okay, which diameter was it? Flange step. That's what it was. Alright, actually, let me do this. Yeah, okay.
It's getting better. It's getting less bad.
Yeah. Yep. Alright, let's see. Now let's...
OD, right?
Yeah.
Pod.
Pod. Alright, and then...
I would try to, slide it
So
over
let's
here,
see.
just so that it's not up in that corner.
Oh, right.
I think you're still, this should be up there.
Should. So...
No, that's the OD. There's a step, right? There's a step right here, and then it comes up again.
Yeah, that's right.
Yeah, yeah, you have a step OD and then you have an OD.
Yeah. So there's so many dimensions here. It's
It's breaking.
yeah. Well, my naming scheme wasn't exactly the best in the world.
Yeah. Here, try to drag that line up a little bit. No,
So,
let's just drag this line up. Can you? Yeah. Well, just yeah. So now put it there like it would be, and now dimension it.
Yeah.
Don't dimension from the point. That's the problem. Dimension the whole line. Go click on the whole line,
Oh, I
and
see.
then click on
Yeah.
yeah.
Okay.
And do the step.
Right. So, yeah, failure on my part was not actually remembering what I named everything. That is one thing. Sorry, the screen is like way off to the side. It's like it's not exactly the easiest thing to control. All right, so
Step OD.
is there? Yeah, there is. All right. Let's see.
I think you're good. Pretty sure you're good. Oh, there's not. Okay, it's not all constrained. My bad. Well, you know why? Because you're not. You can move it like this way. I think you're not constrained in your wrong.
Yeah, that would be text. You know,
Like you were dragging the whole sketch this
no,
way.
yeah, that's not too much of an issue. I'm wondering, just making sure I have like. I believe that's good. Now I'm just going to revolve this. And there's our nozzle. Oh, that's good.
I just want to do something quick.
Right, yeah. Alright.
Oh, there is a. Wow, they have phenolic in here. That's amazing.
That is pretty cool.
But we have to. Can you? Wow,
Yeah.
I'm blown away that they can do that. Okay, well that they have it in there. Sorry, I want to do one last thing.
Okay.
It's gonna be like black,
Yeah.
or like super dark gray.
Right.
We'll do that. That looks good. All right.
Alright, so do you, let's see, I'm trying to think what we can knock out. Well, we have our PNID, what else? Do we want to like start catting up the test stand as well while we do the engine?
I think you just crank out the engine. I think it would be nice to just see the whole engine build process.
Alright. Do you want to go through, I feel like we should start going through the bomb too then?
Yeah, we'll do it after.
Or do we want to, like, do we want to CAD the whole thing first and then do the bomb? Or, so I feel like we can knock some of that stuff, like we can start pricing out what the test stand materials are. I feel like it's very inefficient if we just sit here and watch me CAD. That's not getting much done. We can. It's not gonna.
Well, yeah, I'm just saying, is like people are here for the engine design part. I think they would want to see that, and if we're just like, here's the budget, they're gonna be like, okay, but how did you do the engine?
Right.
So, well, I would okay.
Well, we can swap back and forth.
I would say do the other parts, and then once you get to the injector and the injector cap,
Yeah. No, I
show
can,
that, because that's going to be important to show how we did that.
Yeah.
That's a complicated component.
Yeah.
The chamber is just a tube.
No, right, yeah. I think, yeah. So let's start, Dylan's going to start showing you all the process for the bomb. I'm going to get some of these basic components knocked out, and then we'll check back in the CAD when we get to stuff like the injector plate. But, yeah.
All right. So, okay. gonna rename this. It's real cheese. We're gonna call it the Budge Bomb again. Budge Bomb. Now, okay. So this is our current Budge Bomb for this this project. Essentially, we are going to. This is what we're. Almost everything is accounted for in here. We're going to probably go through and check a couple things, make sure that some stuff's fixed. Some things are going to change, such as like this drill bit size. It just depends on what the engine ends up being in terms of like the orifices are going to be different. So we got to make sure that those are correct. Once we do that, then we'll put that into the budget. Find the links to those exact drill bit sizes, and that'll be fine. So, the schnoz, name it the nozzle. So for the nozzle, we are just using, like we've been showing you numerous times. Where did it go? You stole it from me. So here's the that's the drawing for it. So we're using those, and they are actually only $3.65 a piece, and we are going to purchase probably 3 of them, two. Sorry, we're going to purchase 2 of them just so that there's just in case one breaks for some stupid reason, you have another one, and also if you end up buying enough materials to build 2 engines. Then here's the Garolite. The Garolite is a McMaster part. So that's what it kind of looks like. It's this like glass phenolic tube. So it's actually a linen fabric, and the resin is phenolic. So it's this linen fabric that's like inside of resin, and it's kind of, and you can see it's like texture is smooth, it's brown, and it's like opaque. And so we have a 1-inch OD, 3/4 of an inch ID. You have this drawing here. So this is the Garolite that we plan on purchasing. And we also have this like percent of budget thing going here, just to kind of look at where things are really eating into our budget. And then we start getting into regulators. So these are probably not the best regulators on the planet, but they will do the job. These are high pressure regulators from Amazon. These can deliver 0 to 800 psi, and they're $27, which is crazy that you can get a regulator like this for $27. But I don't care how cheap it is. We were able to get it, and that's good with me. Yep. So that's probably the regulator we'd be using, and that we made that full determination based off of the regulator. We have one here available to us that we tested. So we kind of like looked at that. We did some tests to make sure it would achieve the flow rates we wanted to achieve, and here's the. We'll go over this a little quickly again. All right, we'll go over this quickly one more time. But this is just flowing a set pressure of air into a cylinder and measuring the, basically finding the maximum volumetric flow rate. And the first one was set at 1,000 psi bottle pressure, and 750 psi bottle pressure was the second one. You can see the difference in slopes is because of the. I attribute it to the delta difference between the bottle pressure and the set pressure. Like here, that's 700, almost a 700 psi delta, and this is only a 300 psi delta. So the bottle is taking, there's a little bit more back pressure, and there's also less pressure in the bottle to force that air into the cylinder. So there's a little bit of a difference in time. As you can see, we start here at about 4 seconds, and it takes all the way to 20, so it's like almost a 16-second time versus this, which was about 9 seconds. Oops, wrong way. Yes. Just look. Somebody walking. And we have the pressure transducer we plan on using. This is just another Amazon purchase. It's really basic, 0 to 500 PSI pressure transducer. It might be fine to get something like get this 300 PSI one just because we're at lower pressures, but we chose the 500 PSI one just because in case we originally wanted to maybe use this for other projects where we'd have a little bit higher pressures and things. So we're still going to have it as 500 PSI. We might change it to 300. I'm not sure yet. And that's just the pressure transducer for measuring the chamber pressure. And then we have these adapters. Here's the sketchy part. This is the CGA 350 to 580 cylinder adapters. And this is essentially how we are adapting a, like, literally a hydrogen bottle to an argon/helium/nitrogen regulator. I am very surprised these exist because it's a little scary, but you can buy them, so that's what we're going to do. I highly recommend not doing this, but if you, like, we're on super budget, so we kind of have to work with what we got. In the same case here with the oxygen one, oxygen is 540, so this will adapt oxygen to nitrogen. And then we have our aluminum chamber for McMaster. It's really pretty simple thing. 2-inch OD, 1-inch ID. So 1 foot long, and it's a pretty expensive part. $52 for one of those. And then all of like the retaining hardware, like the aluminum discs that we're going to be using, are from just McMaster again, and they are a 1/4 inch thick and 2-inch in OD. So we're going to probably use one of these for the nozzle, or sorry, one of these for the injector, and then one of them for the other for the retaining the entire nozzle assembly. So this isn't completely filled out yet. There's some adjustments that need to be made. We have a 12-volt battery here that we're going to use for actually running the entire stand. This 12-volt battery will power the Arduino and the solenoids, and then also supply. We have a drop-down 12 to 5-volt regulator for the pressure transducer, so we can run the pressure transducer off this too. And it's just a 12-volt, 1.3 amp hour battery. And pretty cheap too, $12.50. And then we just have so here's the Grafoil gasket sheet material. It's a little bit pricey, but it comes in this. It's 5 pieces. It's a 0.5 millimeter thick, and the flexible foil gasket sheet, $16.49. There's probably other ones on here we can maybe get that are cheaper. I just haven't looked around super hard. And we got some more. We got some fittings here, and then this isn't been populated yet. And then we're going to use 2x4s from Home Depot to make the frame of the test stand. These also may have to be repopulated right now. We tested a different solenoid 2 days ago, but this is basically the same solenoid. This is the one that we'll be using for the test. This one says it can go from 0 to 1.2 megapascals right down here. But we tested the one we have to 200 psi, and it didn't leak, and it was good. So we think they're good, and the ones we tested were these $9.75 valves, so we could save basically $10 total for 2 valves here. Yeah, and then we got a 50-foot USB for testing. We're going to stay far away. That might become a 25-foot USB depending if we can save a little bit of money and maybe put some shielding around the engine. That way we can be a little bit closer and save some money on the 25-foot USB is half the price of this one. So here are the check valves. These are McMaster parts. Really simple. 1/4 MPT, 400 thou thread engagement, and these are good up to 500 psi, well above where we are going to be at. And they have a flow coefficient of 1.2, so lots of flow. And then here's the RTV sealant. This is the high temperature sealant we're going to use to sure up the cracks inside the engine and make sure nothing's going wrong. Or if something's, make sure that nothing does go wrong. And these come in little tubes, and it says it's only rated to 750 degrees Fahrenheit, but intermittently, we're going to be very intermittent. We're going to be fire and then done, and I fully expect some of this stuff to melt, boil off, burn off, do whatever it's going to do, but it should be okay. Then we have copper tubing from Home Depot. We're just going to get a roll of it at Home Depot. It comes in a 10-foot roll, and it has a 35 thousandths of an inch wall thickness, I believe. Yeah, 0.19 minus 2.25 minus 1.9 is 35. 30 thou. 30 thou. Whew. Then we are going to get some Amazon relays to fire the solenoids, and also possibly the igniter loop for the glow plug. We'll run the glow plug igniter off of one of these. $7 for these 2 boards. Not too bad. And then like I said, we're going to power this all. We're going to run it all off an Uno. So this is a knockoff Arduino Uno for just under $11 on Amazon, and this will be able to run the solenoids for the test and record data from the pressure transducer, and hopefully report it back to us on a MATLAB window that we are going to like a command interface, a GUI for testing the engine. And then we have some wood screws from Home Depot to put things together, a 12-volt to 5-volt converter for the pressure transducers. Then we have like drill bits. We have some money associated here for drill bits, the air gas stuff. Then here's all the MPT to flare fittings. The amount of these will probably change a little bit, but this is essentially the same fitting we showed you earlier with the CAD stuff. We're working on CAD. There's some more tubings, and then we had a pack of 10 of these 45-degree flare nuts so that we can actually put it all together. Put all the tubing together. And then there's these nipples for the hex nipple for the solenoid to check valve interface. We want to keep that short run length. Then we got an O-ring for the engine, and it comes in a pack of 10, so it's a little bit pricey, but we'll have a bunch of them in case we screw up. Glow plugs from Amazon, a 1/4x32 tap for the glow plug, and then we also plan on getting a fire extinguisher from Home Depot, just a little one so that we can put out any gas fires. It's rated for gas, it's B and C, so it's rated for gas, liquid gas, and energized electrical fires. So this should be good enough for our little stand, and we should be able to keep ourselves safe. So yeah, so that's the budget bombs as of now. We're at 485. There we go. We got 500 budget, 485. We got $15 worth of stuff. There's probably going to be things getting moved around here. A couple things will get changed. Things will get either knocked off the list or a smaller amount of them, but I think we're going to be able to stick with the under $500 budget. Yeah, I think it's going to be good. So yeah, that's the budget bomb for this project. And then we're going to do some test and design stuff in a little bit. It's going to be mostly, we're going to maybe do a couple of just like pressure drop calculations and some things just to make sure everything's good. Yeah. But for now, I think I might do some stuff with the sheet here, make sure that we're finishing up some of these values. And yeah, we're cranking along here. Zach's over here cranking out parts.
Yeah, so this is kind of the part of the design phase where it gets probably a little bit tedious to watch, but a lot of what we're doing now is just let's see, let me check something. So a lot of what we're doing now is just kind of finalizing the design process, getting some CAD out, making sure all of the parts fit together properly or behave the way that we expect them to, have the right stats. And the way that we kind of checked those earlier, how we mentioned, was characterizing the flow out of that regulator. And then we did a pressure test on that solenoid valve earlier as well. So a lot of these things are just important for making sure that your system is safe, but also that it's going to perform how you expect it to. Yeah, this process is, this is, I don't know what the right word is. It's tedious, yes. But yeah. Let's see. Let's see. Yeah, so if anybody watching currently has like a question about what we're doing, feel free to put it in the chat.
Are you doing the injector without everyone?
No, I haven't started.
Oh, okay.
Yeah, if we want, we can hop over to that now.
Yeah, watch him do the injector because the injector is a complicated part. Yeah. All right, I'm going to turn you on.
Alrighty, so kind of since we last showed this, so I've added. We have the ablative part of the chamber, then we have the chamber itself, the injector plate, which I'm about to go in detail here. We have the retaining plate, the fitting plate. We have our glow plug, and then our fitting, and then of course our O-ring, and then a little circle for our gasket there. So, but yeah, so I guess getting into the injector. So one of the trickier things, let's see if I can, so I guess we kind of have a whiteboard for this, but I'm going to go ahead and just, it doesn't even, no. Well, actually.
Yeah, let's pop over the whiteboard then.
Yeah.
Do you want to go over there?
Yeah, that's it. Because
some of this geometry can get tricky. I'm gonna, I took a picture of that. Alright. So,
We got it bad.
So the trickiest thing, or one of the trickiest things about designing an engine is what's known as just the upper manifold, or the area in which the fuel interfaces with the engine for the first time and actually goes into the orifices. So I'm just going to go ahead and draw, it's going to, so I'm going to make it nice large. So I'm going to go ahead and draw kind of what my initial thoughts were to do. So that's going to be the chamber wall. This is going to be our ablative wall. That's already a little. Let's do this. Be our ablative wall. Okay. Alright, so for starters, let's go ahead and talk about how we're going to retain this. So we're going to have quarter 20 bolts on the top here. These are going to, I guess, they're going to come down through here, and they're actually going to sit into tapped holes we drill inside the chamber wall. Now this is one of the reasons why the chamber had such a large wall thickness, but so these are going to come all the way down. They're going to have to be pretty long screws, but those are going to interface there. And we have the same thing over here.
That's an interesting cap screw.
Yeah. Alright. So that's going to look like that. Clean that up a little bit. Alright, so we have our cap screws, and then as kind of like a top view, we have our screws here. Now, an important thing to keep in mind here is that we can't put any screws here because we have our fittings coming in from the side. Now, given the low pressure of our engine, it's not too much of a concern that we don't have a fastener here, and given how large these screws are, it's not going to be too much of an issue. But yeah, okay. And then to kind of save space, rather than putting the pressure transducer fitting and the glow plug kind of let's see, kind of like competing for space in the middle, they're both going to be offset, right? So we're going to have our pressure transducer fitting sitting here, and our glow plug sitting over here. Now this is not to scale. Obviously the hex features on both of these fittings are a lot larger, and you'll notice that once we get into the CAD, but that's kind of the idea behind the placement for where those are going to go. So kind of down here to, I guess, this is going to be what I'm calling the fitting plate, and then this is going to be the injector plate. Oh man.
Words.
And the retaining plate is going to be fairly simple. It's just going to be, we're going to have a cutout for the nozzle, and then cutouts for, we're actually going to have 8 screws down there.
8?
Yes.
8 of them? Oh,
we're going to go all the way. Yeah. So, all right. So we have our fasteners there. All right. So then we have our orifices, which are, let's see. So the way that those are positioned, you have to keep in mind that this is where our chamber is going to be somewhere around here. And which means our injector is going to have some kind of path directly towards where the chamber is. Or injector, sorry, igniter. That's going to come about down halfway. Have some kind of hex feature there, or whatever that is. So, this is the part that's going to glow.
This is on the glow plug.
Yes. That's going to face there, and then that's just going to be a hole straight down.
Into the chamber.
Yes. Okay. Oh man. It's not the day for nice lines. So, kind of, let's see. So this is kind of what's going to be in front. So if you can imagine kind of like a section view where instead of going straight down the middle, it's like going down through the side rather.
It's offset.
Yeah.
Offset plane.
Yeah. So then on the center line itself, that's where we're going to have our injector orifices. This is going to be on the side here. So then we have our impingement there. And then on that same plane, on that same midpoint, we're going to have our pressure transducer channel, I guess. So that's going to be there. And then this is where it kind of gets a little bit tricky, because we have our fittings coming in from the side. Okay, so then we have some kind of hole here that our fitting sits into. It's going to get really messy, just bear with me here. And we're going to just drill straight down. So we're going to have a place for our fitting to go, and then there's going to be a little bit of space afterwards, and then a hole.
A little pocket of space.
Yeah, a pocket, yeah. So that's going to be there for our orifice over here, and we're going to have the same thing over here. It's going to be not exactly to scale, but alright, so then now we have the stream for gases to flow to our injector. We have a place for our igniter to go and actually ignite the gases that we're mixing. And the last thing we need is a spot for our pressure transducer channel. So this is actually, we want this to be right in the middle, right behind the impingement plane. And the way that we're actually going to do that, since this can't sit in the middle because of where the injector is, you can kind of see over here, we're going to have to make some kind of like channel, if you will, on the side there. So we have like a port here. That's the channel that goes into the chamber, and then it's going to come up into this plate, kind of off to the side, and then up where that pressure transducer is. So, I know that probably sounded slightly confusing. No, it probably sounded very confusing.
Big confused.
Yes. So,
Oh my gosh, that's amazing. What a fitting.
yeah.
Here, try it for a second.
Oh, go for it.
I just want to show that there's threads.
The threads, yeah. So, yeah, one of the most challenging things about this engine is the fact that it is so small, and you have to, when you're using conventional fittings like these, I'm sure you can get them smaller somewhere, but it's going to be expensive.
Yeah.
So
You can get 16th MPT,
Yeah.
and those are pricey.
oh man,
A little bit pricey. Pricier than these.
yeah,
1/8 inch MPT is really the bottom.
yeah, that's crazy.
So you're going to have like
Yeah.
basically a straight hole drilled down to here.
Exactly. So it's going to come all the way down here. Those lines are going to get a little wonky, but it's like everything drawn on top of each other. So this isn't all in the midplane anymore. So this pressure transducer is actually going to be somewhere back here. This is where the glow plug is going to be, and then we have our orifice, and then pressure transducer channel, and that's going to come over here through a notch that we're going to make in the face of either this plate or this plate.
It'd probably be the fitting plate, the top plate,
Yeah.
because you want to keep this as thick as possible, the injector plate.
That's true. Well,
Yeah, you want as much meat there as possible for heat absorption.
Well,
or would you rather? I mean, honestly, it doesn't matter. You
Yeah.
could do either one. That only needs to be a 1/16 of an inch thick or deep. That channel only needs to be like an 1/8 of an inch wide, 1/16 of an inch deep. That'll
Yeah.
be enough to take the pressure up that way.
yeah. See, the reason why this has to be so thick is because of the fittings. This can be a little bit more thin, and it's kind of a balance there because we don't want to drill through too much material sideways, or I guess diagonally. Yeah, so I guess keeping that in mind, we'll probably go into the injector plate so that we don't mess with, there's a lot going on in that plate already. So this is behind that, and then it's going to go into a hole that we have here. Something along the lines of that. See the hole that's going straight down, a channel that's cut into the injector plate, and then that hole there.
A little hole drilled down to go into the chamber.
Yeah.
And that way, you can, when the engine's running, you have a pressure inside this volume, and you'll be able to record that pressure because that gas pressure is pushing on already atmospheric air that is just present, and it pushes on this flow path, and it goes up to here, and then it'll continue onward and go up to a pressure transducer, and it compresses that gas, and we should be able to measure the chamber pressure with a pressure transducer all the way off up here, all based off of that little tiny hole down there. Yeah, it's not going to be super small. It'll probably be, I'm thinking like a 3/32 of an inch, so like 0.18, or sorry, 0.09375, between a 1/16 and an 1/8 of an inch.
It'll be very small.
It'll be pretty small.
All right, yeah, so kind of clarify some of that. Let's go ahead and jump into CAD.
CAD time.
Alright, so one of the variables, oh that's over there. One of the variables I neglected to add was the, let's see, PT, the pressure transducer hole. So we'll go ahead and make that 3/32 of an inch. Nice. So we'll go ahead and move that up there. The placement of your variables actually does matter. If you say if I were to move this above the sketch, then it would be invisible, right?
You couldn't use it in Sketch.
Exactly. All right. So let's go ahead and in order to get
I have an idea. While you're talking, do you want me to make us some tea?
yes.
A little cup of tea? Alright. That sounds like a good idea. Cool.
All right. So in order to, let's see, I think the first thing that I'm going to do is go ahead and make the orifices. So let's see, actually, now that I'm thinking about it, we might want to do, I think we want to do the fitting plate first, actually, because well, actually no, that's fine. I don't think it. matters too much. But yeah, all right, let's go ahead and do the orifices first. This is kind of what I'm thinking of out loud, is that the placement of where these orifices are is going to be impacted heavily by where basically that pocket we had drawn earlier is placed, because that hole is going to go straight down and we're going to match that where the orifice hole is. So let's go ahead, throw those there. And then, so that's our oxidizer orifice. And then we have our fuel orifice there. Okay. And then, let's see, let's go ahead and make that a variable. I'll do fuel orifice. Yeah, something along those lines. So maybe make that 10 for now. Let's do that. Okay. And then ox orifice location. Let's do, yeah, actually that one better. Not 120, we want to do 10. Alright. Okay, so then go ahead and jump into that sketch. Ox. Let's see. Ox. Yeah. And let's see, they're probably going to be the same location from the center, but I do want to give myself the opportunity to change that if I want. So, alright, let's see, so I think I'm going to go ahead and, yeah, okay. So now I'm going to go ahead and add the pressure transducer hole. Let's see. Nice. Alright. So the way I'm going to add the orifices is I'm just going to make a section view there. And let's see. I'm going to make a accept that section view, make a sketch on the plane that runs directly through the center of the circle. And then grab that center point of that circle and then just drag it down to the plane there. Yeah, that looks good. So I think we want the angle of that to change a little bit. Let's go ahead, actually. So what I like to do is kind of, let's go ahead. Yeah, alright. So what I like to do is I like to define as much variables as I can before I actually start a sketch, and that usually, but of course sometimes that isn't always the case. Sometimes you'll be, halfway through modeling and realize it might be useful to add something, or, but it gives you a lot of flexibility in what you're actually modeling. So I'm going to go ahead and we're going to accept that sketch, and our pressure transducer hole can just go all the way through. That doesn't need any fancy angles there, but we might want to do something a little bit different. We'll just do a sweep for our orifice holes. Let's see. Yeah, so we want to do alright, so I'm just selecting those faces there. I select the sweep path that I made that runs directly through the that's not correct. Hold on. I'll have to do them separately. Give me one sec. Yeah, so we want to move that. Alright. I'm going to select the face of the other orifice and then just do the other sweep path there. It seems to, yeah, so this can get a little bit tricky if you just got to make sure that your sketch is visible. Sometimes it likes to select the entire face, and that can mess with a few things. So we have our orifice holes now. We might want that angle to change. Right now I've got it at 45 degrees, but maybe we want something a little less aggressive. But because we have our variables, I'm going to leave it at that now, just because it will be easier to change in the future. Alright, so we have the pretty simple part of our injector plate done. I'm going to go ahead and hop over to the fitting plate now, just because a lot of the geometry here is going to kind of change a lot of how the injector plate geometry looks. So let's see here. I'm going to go ahead. Give me 1 second. Let's see. All right. So I'm going to go ahead and start the. Let's see. I'm going to go ahead and start the bolting pattern for this. So it's important to keep in mind the fact that we have to have 2 spaces. Actually, here, sorry, my thoughts are a little bit disorganized. Since we have those fittings coming in from the side, we got to be mindful of the pockets that we have to make, like in the side of the plate. So I'm going to actually go ahead and model those first. That way, the feature that is kind of constraining how this looks, we can kind of have a more accurate idea of where it is. So I'm just making a plane that's tangent to the edge of this circle here. I'm going to make a sketch on that plane and make a circle for the fitting. Let's see. Alright, let's see. I'm going to leave that like that for now because I accidentally left. Let's see. Well, alright. Let me go ahead and make a variable for our fitting hole. Which I think I'm going to want to make that. Let me check real quick. Yeah, so that's going to be a 1/4 of an inch. Alright. So I'm going to go ahead and go back to that sketch, change that to fitting hole, and then we're going to put that about halfway up, I'd say. Yeah. Alright. And then just like I just like black these five down. Alright, so I'm going to go ahead and make another variable for, we'll call it fitting pocket depth. And let's see, I'm going to throw an arbitrary number in there for right now. I always just like 6.35, it's a nice number. Okay. Go ahead and make that hole. Fitting pocket depth. Nice. Alright, so the way, I'm going to do it here in a sec, but the way that I would determine more accurately what exactly that depth is going to be, I guess we'll do it now. So you kind of have to keep in mind, I'll go ahead and draw a sketch here just so we can kind of get an idea of what it looks like. So you have a, let's see, oh no, hold on. So I just drew the circle here to kind of get an idea of where exactly I guess the thickness, or I guess what's the word I'm looking for? Like the chamber, I guess the volume of the chamber actually starts, the empty space through which the gases combust. So we're going to want this channel to, let's see, it's going to come in. We want it, actually, just trying to think here, because maybe we don't need to do mess with some of this geometry after all. Let's see. All right. All right, 4.3. All right, so I'm going to go ahead, actually. I'll do that in a sec. I kind of want to get a more established.
Bros.
Thank you. Oh, did it?
Yeah. Thank you. I was afraid this was gonna happen.
Yeah.
Here, let me see the mouse. May I have mouse?
Oh, yeah.
It's probably been frozen for a while. Hope not.
Well, it's still going there.
Well, at least the text was, or sorry, at least the screen was going right.
Yeah. Looks like.
Crud. Yeah, we have some issues with these Logitech cameras. There we go. I don't know what it is.
Nice.
They like go into standby mode, and then we lose our video. So
Yeah.
maybe not the best things to live stream with.
No. All right. So I kind of simplify the process for. Let me go ahead and get out of the sketch here. So I'm just going to go ahead and mirror. Let's see. So a good way to kind of look for, I guess, like different features of the CAD software as you're modeling is if you can't find something, you can select something like Alt-C is a good keyboard shortcut for finding different parts of, like, you know, maybe you can't find Revolve or something like that. You can just Alt-C and search for it. Let's see. So this is no. All right.
He won't let you.
All right.
What? You just refresh the page. Anything broke. Oh, select a mirror line. You don't have any, like, draw a line down that. Oh, maybe can you select the plane?
Should be able to. Ideally, I would just be able to select the geometry.
Oh wait, do it now. Do the mirror now.
Yeah, that's what it was.
Yeah, you don't have to mirror that circle. What is going on? Is it like broken?
Alright, let's see. I want to do this plane.
No.
Can I not?
It's considering it a part of it, I think.
Alright, well, the good news is it's not like anything too complex. I can just do it over here.
Making planes everywhere.
All the planes. Alright, yeah, so let's see. Just doing the same thing on this side. Alright.
The fitting holes are wrong, but I don't know why. It seems really small to me.
It does seem a little bit small.
Where'd you get that number from?
That's a good question. No. those two holes there. Let's see. Alright. So now we want to go ahead and do our bolting pattern. And the reason why I did that first is just because the positioning of those pockets is pretty vital to actually where we're going to put these bolts. So let's see, we want to actually start our first hole there right on top of where the pocket is, which sounds counterintuitive at first, but it's actually one way of guaranteeing that your pattern actually doesn't overlap where that pocket is, because that's actually the only one place you have the most control of. So actually we'll want to do,
Yeah, I don't think you made
what
it
I
there.
call it, did I make it?
Didn't make it yet.
I did not. I'll do the screw.
No screw holes. It's a bolt hole. If you'd make it a screw hole, I mean, it's all done.
Alright. Good times.
Make me angry now. See, you're calling it
Alright, let's see. So I think we want to do that 18. 19 was a little more comfortable. Okay.
Wait, wouldn't you want to do it right down the middle of, you have a half-inch landing for that tube. That's not good.
What do you mean?
Wait, what? This is your bolting hole, right?
Yeah. So, alright, so
Am I just not thinking correctly?
I guess what's your question?
My question was, why are you doing this? Like doing a linear dimension when you could just put it on a circle and then say, hey, the circle's at this diameter, or I guess.
Well, I guess
Right.
the circular pattern does it.
Oh, it does. It's special. Oh, that's an oof.
Yeah. All right. So, since I did the circular pattern
So you have to make them all
right on top of the pocket, now I can get rid of these two.
Why didn't you do
And
the
now they
problem
don't
with the
interfere
problem with
the
this
pocket.
is that you don't constrain anything. The way I'm not just like a
Oh.
small critique. Like when you do that, now there's no reference for this, and you could just drag any one of these. And so, but if you do that, yeah, now they're all on that circle,
Yeah.
and then you dimension that circle. So like slap a dimensiono boyo on that thing. Oh man, I need to stop. And name it 38. Oh, it's still not dimensioned properly because
Yeah,
you don't have the
near
angle.
feature, not part. Oh, it's Sean. Hello, Sean. Yeah.
He's got bad CAD practices. No.
Yeah, no. I'm quite sloppy with my CAD. All right.
What did he say?
He said, there's an option
Oh.
in the mirror feature thing to change it to the mirror feature not part. Aha! That's good to know. Alright.
Oh my
Get
goodness.
outta here.
What happened there? I guess you're just not good enough. I think that's.
No, I think that's the answer there.
And then I made you do this instead of you just like the halves.
Yeah. No, it's fine. Alright. So we have our bolting pattern. Nice. The next thing we have to do is so now we have to determine how deep we actually want to make these fitting holes, and then after we know that, we can actually determine, let's see. So actually, one thing that I'm going to go ahead and do is make an assembly. One nice thing about Onshape is there's this feature where you can edit in context. So it's like you can kind of put everything together and then edit apart with like some of the other ones kind of blurred out, so then you can get an idea of where to place things. So I'm going to go ahead and do that actually to simplify some of this process here. It's just a cylinder.
Engine.
Engine.
We have made engine.
Yes. Alright. Let's just...
Two gaskets.
Two gaskets. We don't want... Alright. Let's go ahead and get everything in there. fitting plate. Let's go ahead and bring our glow plug, and then we'll inject your plate as well. Nice. All right, so I'm gonna go ahead and mate that to this here. Yep. And then this part is going to go. Yeah. Nice. And then, okay. So then just kind of to make sure this is how I want it to look, you can, yeah, alright, cool.
Yeah, you like you should probably put that in between the two, right? Because you have that plate. Sorry, the.
Oh, that's a good point.
Well, you didn't even make it yet, so I wouldn't even.
No, yeah, we'll get to that in a sec.
This is just good for now.
Yeah.
We're doing some estimates.
Yeah. All right. So I'm gonna go ahead and.
No. It like didn't even detect it.
Not exactly conventional, but it works. So yeah, that's definitely not correct.
It wouldn't go that deep, but it's fine.
I suppose be a little more something like that.
Yeah, probably.
Yeah. All right. So what exactly? Yeah, I might want to change that to something a little bit bigger.
That whole.
Yeah. Yeah.
You're just throwing random numbers at it. It's also not like really deep. That's fine.
Yeah, so that's kind of where the editing and context comes in. So now that I have this, you can right click, you go to edit and context, and then you can still see, it's like you're in the assembly, but you're only making changes to the part. So now I can do a section view here, and
That's pretty nice.
I think am I still on fitting plate? I think I am. Yeah, alright, sweet. So now I can actually gauge how deep I actually need to make this pocket. So let's see, fitting pocket depth. Maybe we want something closer to 8. Wow, that didn't seem like it did anything. Okay, it did. Nice. So, yeah. So I guess the more professional way of doing this would be actually doing some fun geometry to
Actually calculating.
yes.
I would put them back because we're going to drill just straight holes up into the pockets.
Right. Yeah.
So make those deeper.
Yeah, they're gonna need to be a little bit deeper.
That's a big thing.
They're gonna need to be a little bit deeper.
170.
Alright, so now that I have that, I can come over here. Let's see, I'm gonna go to my assembly real quick and actually unfasten this. Bring it up a little bit, and then let's see, go back to editing it in context. Okay, so now I have a hole that I want here. So let's see. Do that as oh man, orifice entry.
Just make it like 1/8 of an inch.
1/8?
Yeah. It's pretty big.
It's pretty big.
Just so that if there's any misalignment, you're not like covering up the hole.
Oh, that's true. Alright. It's a bit large.
No, it's fine. That's easy to drill. You don't want to make them too small.
That's true.
Because then you run into issues where plug the hole or accidentally do something else.
Yeah. So let me go to this real quick, and I'd like to know the center distance. 10. Nice.
Nice. Nice. We just CAD it. You did a CAD.
Yeah, yeah. Alright, that looks good. I guess we'll just do up to next. Yes. Alright. So there's our
That
first
was
thing.
perfect.
Ooh, now we have 5 people watching. Whoa. Alright. So now, let's see.
Yeah. You can get pretty in depth with the design. So like, there's some stuff that's a little bit different. For example, you didn't take into account that drill bits have 100 usually standard drill bits that you can get in a set of drill bits has a 118 degree point at the end.
That's a good point.
So they'll sneak in like this. The end of the drill, the end of the hole of this blind hole will be a point. Yeah. So I mean, it's fine for like what we're doing here is like we're not doing anything crazy high tolerance like crazy parts. We'll take that into account when we make the drawings and stuff. We might edit a couple of these features to show those
Yeah.
kind of dimensions so that they're just correct.
Yeah, this is a very kind of
Super crude,
quick
quick.
thrown together, yeah. Alright, so
There you go.
now
Now you have the holes, and you have your passages from your fittings through the plate,
Yes.
down into the next plate, and into the injector.
alright. So let's go ahead and get a section view of that, make sure everything looks good.
Bang! Look at that.
Nice. That looks pretty clean. We have our oxidizer and our fuel going into these holes, and then out on the side we're playing with impingement. Yeah, so I think now we want to, I think now would be a good time to go ahead and add our pressure transducer hole.
Well, isn't it going to be off to the side?
That is true.
Hurt, brain hurt.
Yeah. Yeah, so y'all will find that the upper manifold of a rocket engine can be, well, it is the most complicated part of the engine itself, unless you have like
Turbos.
yeah.
We're pressure fed.
Yeah.
Pressure fed bi-prop.
Yeah.
Literally the junkies about pressure fed
Yeah.
pressure fed bi-prop possible.
It can get pretty complex.
We actually get pretty junky too. What we're doing is
Yeah.
probably, in my honest opinion, the bare minimum / of engines that are actually going to do something. Like I've seen people make engines online where, yeah, that's might do something, and then it usually just burns up. It's a lot of
Yeah.
not good fabrication practices. The
Yeah.
design might be sound, but the fabrication is not sound.
Yeah. It can be a difficult part. Of the process. Okay.
Whoa. I was like, whoa, whoa,
How did I
whoa.
do that? Oh, that's cool. Oh, alright.
Oh man,
That's kinda
that's neat.
yeah, that's cool. Alright. Apparently you double click and it switches the direction. Didn't know that.
Finding out on shape, new things about on shape.
You learn every day. Okay. Alright, so now we need to have a spot for let's see, yeah, so I guess we don't want this down the middle actually. Because
Be like off to the side, right?
Yeah.
Like the plane like this. Do like a top-down view. What are you working on? Or what are you trying to figure out where to create that channel? What are you doing, son?
Alright. So I'm just trying to think where we want to put our, let's see. Injector plate.
Well, we want we're gonna want the pressure. We're gonna want the igniter to be straight through. We don't want the flow path for the igniter to be any through bends. We want that glow plug to be a straight in.
Right.
So make that just drop right in somehow.
Okay, so let's go.
Oh my God, we're coming up on 8 hours on the stream.
Are we really?
It's 7.5 hours now that we've been live.
Oh man.
Keep grinding.
Yeah.
Unfortunately, we only have one computer to do. We have two computers, but we can't show you. I didn't figure out a way. I don't think it's really possible to show you two screens from two different windows. It's just not. It's not going to happen on two different computers. It's just not going to be happening. So you get to watch Zach do it.
Yes, indeed. Alright, where's Skizzers? Get out of here. Alright. So I think,
Just somewhere along that line.
yeah.
Which one is that going to be?
Oh, right, yeah. And then, let's see.
The glow plug hole could probably only be like I would say, anywhere from an eighth to a quarter, 3/16. Doesn't need to be huge.
Oh.
We don't want to make it that a huge. Whoa.
Yeah, it's gonna look stinky. Alright. Nice. There it is. Sketch 4.
Oh, okay.
It's like, where? Alright, no.
Cool.
Alright, so then I think, please tell me that's concentric. It is. So we want to do 10.
And then the other one has to be closer.
Yeah, I think.
I would say like 9 or something for now.
Yeah, looks healthy.
That might even be close.
Yeah.
Oh well. Oh, fix that extrude. Oh, what'd you just delete? Oh, okay. Oh man.
It's Pac-Man. Alright. Nice. Alright.
Oh yeah, those are the threaded parts right now.
So I think that's a little close.
I still think you're gonna have to move that way a little bit.
I kind of think so too. Don't know why that fasten is.
Just broke. It broke.
Yeah. Maybe like.
No, that's the.
I know that's still
9.5.
I feel like. Let me just see. Let me just see. What are we doing? Why are we guessing?
We have fittings. We have the fitting.
Yeah, we
and the cap
we
screws.
can put it there.
We can put the fitting and the cap screws into the model.
Jeez. All right, I imported everything like twice now. Nice. All right, so that's gonna look something like that. Okay.
That's scary.
No.
What happened? Oh, we got plenty of room there.
Yeah, we can jive with that.
You want that copper washer to see.
Hmm. Do that.
Wow. You want that to see all the way to the bottom, but it's fine. It's just for like getting this together purposes. But you also want to put those cap screws in there. Or the model, you get those cap screws from the
Yeah. No.
That's fine. Close enough.
All right. So then, let's start with the longer ones for now.
Probably. Oh, not hex bolts.
No, those are.
Socket head screws. There's a socket head. There's a screw.
Oh, but it's not.
You can change the bolt.
No.
Can you? Yeah, you can. Whoa. There you go. There you go.
Nice. All right.
What? All right, we're going with that, I guess.
Oh,
it's 080.
It's so small. I was like, that ain't right.
Do you want to do a little? Wait, so we got half, quarter. Well, that means we'd have half an inch of threads in there, right? Yeah.
Yeah.
That's fine. That's a lot. That's a good amount of thread engagement. Yeah, it's not going to blow up. Don't worry. Insert.
Won't blow up. Don't worry. Okay.
Wait, is there a more efficient way to do this? Probably not. I'm going to say, could you import one and then just like. But
I could probably.
we are
could do that.
brute forcing this.
Yeah. Efficiency is not necessarily my human. No, there's much smarter ways of doing this. It's just. Alright.
Yeah, this engine's going to be dense at the top.
Yeah,
Oh my goodness.
that's quite close to that.
Oh, that's easy. That's not. That's fouling out already. I can see that.
Yeah. That's the one thing,
That's not a bueno. Non-buenos.
though. Yeah. All right.
Well, it's actually, yeah. I would
Hmm.
try to make it so you can move it in. We got. This only comes in so far. You have all of this space.
Yeah.
You got space galore.
Alright.
No, you
No,
don't need to.
yeah.
Yeah, I was gonna say you don't need to do
Let's see how that looks. Oh man.
that. It broke.
It doesn't like that extrusion at all.
It's just taking the inner circle. Don't break. No, don't just redo it.
Yeah.
Oh my goodness. Oh my goodness. Oh my goodness. I'm surprised Sean isn't making them in the chat.
Sean's like,
Blasting your CAD practices,
I
man.
know. He's still there.
I don't think so. He hasn't commented. Mm-mm.
What do you
Oh,
need?
no. Oops.
Uh-oh.
Sneaky.
Oh man. Alright, let's see. We're gonna make it through this.
Is it better at times? Oh my god, it's 4 o'clock. Holy crap.
Is it really?
Yeah.
Okay. I need it to stop selecting that geometry. Hold on. I'm just gonna. Where's the input? Oh,
Just starts over every time. Oh my god, it's broken.
Alright, you know what? Hold on. Hold on. This is because
Cut all that stuff down.
Yeah,
Go in there, trim it.
that's what I should have done from the start.
Actually, wait. Before, yeah, trim those. No. Actually, wait. No. Stop trimming things. Control Z everything.
Why?
Just Control Z it. One more. Ready? Watch this. Actually, wait. What am I doing? I got a mouse of my own. Ready? Watch. You can select this, and then you can transfer it and make it a construction line.
Oh.
You can make all these construction lines, and they're not taken into. That's what you should. That's why I was freaking out about your CAD practices, because you make these all construction lines. You can constrain to them, but then when you do your little extrudo,
that.
you do your extrudo. Look at ready. Oh. All right, I guess that one is not good. Yeah, but you can just like do this now, or not,
Just now tell me this.
or not. You know what? You know what? What is going on
Here, you should just be able to select sketch 4. Like,
here? No, but it's.
okay, let me, I'm gonna
You gonna drive now?
I'm gonna drive.
Will it work? Oh, oops. Oh my goodness.
Okay, we're both learning here. All right.
Your constraints also don't work very well. Oh my. That hole broke. All broke.
I wonder why that happened.
Oh, because we deleted the geometry and rebuilt it.
Oh, right.
So stop doing that.
Yeah, that's probably bad. All right. This needs to not necessarily leave.
It's like this.
All right.
No, don't leave. Please don't leave.
Hold on a second.
Yeah, the way you constrain stuff is no bueno.
Yeah, not necessarily fantastic.
No, it's literally trash.
All right.
I'm pretty sure you can. What-
Yeah, honestly though. We needed that. It's your support that drives this show. I feel like we can slide that in a little bit more.
Which one?
The
It's all good. Like, well, the only thing I'm worried, like, you can all these corners will all clear this lip here. So what we'll do is these will be installed first, and then we'll just cap down the head.
Yeah.
So like it's like this is fine. Like this is great. Like these aren't gonna no matter what position this is in it's always going to clear the cap
I know.
screws.
I know that. It's just very. Well, I guess it's going to be close pretty much no matter what.
Yeah, and I would rather not get these super close to each other.
Yeah.
But
All
honestly,
right.
it doesn't matter unless you want to. I don't know.
No, that's all right. All right. Okay.
What a re.
So-
All right, you gotta make that channel. Where is the hole? Why'd you get rid of the hole for the pressure transducer?
Well, because it was right down the middle and it wasn't supposed to be.
Oh, it wasn't?
No. Because that's not.
I thought you said. I remember you saying you were gonna do that.
Yeah. Well, because I guess initially I thought we would. But
Oh, okay. It's easier to just go straight in, I think, right? Right?
Yeah.
Instead of no, we might not even need to know a notch. Wait a sec. Let me drive. We're doing some driving.
Well, hold on.
If you just drill a little hole in the injector plate for the hole there, and then like a almost full diameter for that one.
Well, because remember the problem was
What was the problem?
the ablative.
Oh, crud. You're right.
Yeah. It's like we go down, and then that was going to hit here. Like the hole's not there, so you can't see it, but yeah.
Right. Never mind. We do have to bring it in.
Yeah. Yeah.
Actually, here, can I see it for a second?
Yeah.
Oh man, there we go. Oh boy.
here. Oh. All right.
How did you just like? Other than clicking here for section view, where else can you click? Is that the only place? When you get your shortcut?
I forget the shortcut to bring up the shortcuts.
What? No. Why do this?
But yeah, I mean, you can kind of see it from there too, actually. Well, wait.
No,
Hold on. It'd be
no.
right up against it.
No. Watch this. No, gosh. Sorry. This is actually really difficult to do. Like,
Yeah.
not difficult, but if we... I think we're on that 20-degree line.
Oh no, yeah. Never mind. It's really close.
See that? We could bring it closer. Like, there's plenty of clearance here. Let's bring it in.
Bring it in.
Yeah. Bring it in. You guys, let's bring it in. And then the thing I was going to say is all you have to drill is one little hole right here. Because like I said, we don't need the full diameter.
Yeah,
so
that's
we
true.
drill one little hole here, bring this guy in, and then drill almost a full diameter. You don't need a full diameter. We just need almost like a hefty hole there. I would like to say about at least 1/8 of an inch.
Oh yeah,
So
then
that
we don't
has-
need to mill.
Yeah, no milling then. And then it's even
Yeah.
better.
Okay, sweet.
Yes.
All right, I like that. Let's bring it in.
Yeah.
Yeah, we'll try to
hit break. Yeah, because it's gonna break again. Did that move with it? Check it. I don't think it did.
Well, let's see. Moved. You know what? Let's hold on. Let's go ahead and move this sketch over to.
Don't tell me your 2 parts goes
Yeah.
on. Oh, you're gonna move. Okay, I see what you're saying.
Yeah.
Oops. I'm gonna move it over.
Oh. Hello. Yeah, alright. Oh, okay. See, look, it's only that tiny little part there. That's the only thing. What about? Oh, yeah, and we don't even.
We don't need the full diameter.
So,
So make that one.
what would you want to draw?
I would say, no, that's too big. That's
That's
too
too
much.
big?
That's too much volume. Yeah, do like 3:30 seconds
Yeah.
at the absolute max. What? Oh, 3:30 seconds.
3:30. Shape Y.
Because we have it set to inches, and then do that one. Do one, yeah, or something like that. Well, I would choose an English unit because if you make it 5 millimeters, I can't guarantee it. Like, I don't want to find a 5 millimeter drill bit. Like, do like what's 3/16?
3/16.
Yeah, do 3/16 for now. Oh man.
Oh man.
Oh my god. Oh, good.
Yeah.
Perfect.
I like that. I like that.
Where'd it go?
Alright. Okay, so it's still cutting into the.
Is it really?
Yeah, it is just a little bit. And.
That's like more than fine.
Yeah, the pressure transfer is fine. If we.
Well, I can't. You can't. I can't see what the freak's going on. You're just too fast.
You don't see that?
I'm trying to process it.
So it's like right.
Okay, yeah, now just yeah. Okay, that's all I wanted to see.
Yeah, I should have started with that.
I say move it in. Move it in. Oh well, move the other.
What
Well.
is that for? Move it in.
That one's not because. Oh my god.
Oh.
The sketches are isolated.
Hold on, yeah.
Because you did another bad CAD.
Yeah.
I'm just gonna call you bad CAD. Yo, what's up, bad CAD?
Pro Academy. Alright, there we go.
Now why is it? Okay. See now, like yeah, just can you redo the thing? Can you do the thing? Can you do it properly?
Nope, still not gonna properly do it.
Why would we do it the right way? I mean, right? Like,
No.
why not? Do your little scroll wheel. Just okay.
Oh. Uh-huh. No.
Yeah, just kidding. That's good. Good enough. Oh.
That's like right there.
Yeah, that's not going to show you anything. Just draw a circle.
No. Oh my god. Little 0.98.
Draw a circle around this. You can see.
What do you mean draw a circle around it? Draw a circle around here.
Yeah, to touch the points, because that'll show you the arc, the travel arc, and then you can figure out if they're going to hit each other. I'm just kidding.
Alright.
I refuse. I'm not doing this.
How, well, alright.
Move it
Here,
move
you know
it
what?
back a little bit.
Let's just make this hole smaller.
What if it doesn't do a combusto? No, I'm just kidding. It'll be fine.
Well,
Make it.
I
Make
mean,
it.
no,
What did I say? 3/16. Make it. An 8. It's probably not, honestly. The gas is gonna get up there. It's
That's
gonna
what I'm
go
thinking. Though. Like, because if that pocket is larger than, like, if all right, so
whiteboard. Whiteboard cam.
Yeah.
It's probably broken. Hold on. Whiteboard cam is broken.
Is it?
There you go. Now you're good.
Okay, cool. So the concern is like it's a little plug, and it goes into there. That's
That's the top plate.
Yeah.
Fitting plate.
and then something like that.
Oh my goodness.
All right, hold on. Just give me a second.
I should not do that with my hand. That's gross.
All right. So the spark, yeah. So the spark is actually happening here. Gases go up into here. We have combustion, but then that's a force that's going to want to drive those two plates apart because that hole is so small. It's not like,
It's not small. It's not big enough that it's going to separate the plates.
well, I know, but it's I don't know.
What are you worried about? It's not going to do anything. Nothing's going to happen. The only thing I'm worried about is that you just don't have enough gas flow up here, and we run it. We have this going, and you put
gas
put
was
gas.
going in there in the
Yeah,
first place.
yeah, you put gas in there, and now we have a crap ton of gas in the chamber, and then eventually it goes, then it just goes bang, and then you have a huge hard start.
Oh, I see.
That's what I was trying to maximize. But at the same time, you kind of want to minimize that volume because you don't want extra volume for combustion to happen. But then at the same time, I want this recessed back far enough so that the hot combustion gases do not go that way and cause bad things.
Proposal, we make this 1/8 of an inch. Like you said, if what you said is also true, there's a bunch of gases in here, and if it survives the hard start, we put a sparkler there and just ignite with the sparkler.
If it fails to like
Yeah.
sustainably
Yeah.
ignition,
Yeah.
but it goes boom,
Yeah, like if,
and it just nukes itself. Nozzle comes flying out.
what if we did a bunch of small holes?
Where?
Like,
Nice noise. I don't know how you mean that small. I know what you mean. What is that going to achieve other than a pain in the butt to make?
so it's easier for the gases to flow in.
How is that easy? I'm just curious. How is it easier? I don't know. I literally am not following.
Hold
this.
on, no, I lost my train of thought.
The easiest is just a big hole. Just a giant hole, full diameter.
Oh, we can't even do that though, because it's stupid. Well, I guess
think it's
before,
close.
because we were thinking of doing the channel, it was the same problem anyway. We could get rid of another bolt. I'm serious. Like,
And do what?
Because as it stands, we have that there.
Mm-hmm.
Bolt, bolt, bolt. PT. Glow plug, bolt, bolt, bolt. Okay. So these are too close right now. There's a like some kind of interference here. Well, we can't move them any closer. I guess they're basically fixed where they are. What if we just got rid of this guy? Move the PT like a little bit closer over here, and then we just have like a tiny hole here, and then we can move the injector or igniter closer over here, and then
Do the full diameter.
full diameter.
I don't think we're.
But now we have 5 bolts.
Yeah, I don't think that's a good idea. You don't have. So I think where we're at right now.
I think this is good. Like, because we can. So, you moved it in, right? So
Yeah.
we go to this assembly.
Oh, I guess I need to make that hole an 1/8 of an inch. But I didn't know how to do that.
See, like, look at. It's fine, as of right now.
Oh, it's gonna be right up against that ablative. It's gonna be gone.
Why is it gonna be gone? This is just to start the combustion.
That's where it's gonna start. Yeah.
It's not gonna just nuke the ablative instantly. It's gonna
Well-
go and then into the engine.
Yeah, but where combustion, I mean, intuition would say that where combustion starts would be where the ablative, like,
Goes bye-bye.
degrades
It goes
the
by.
fastest, yeah.
Goes away. Alright, well then we do this. That's the PT.
No, that's the,
That's the PT.
yeah.
We do 3/16 is 1875 minus a 32nd is something like stupid. But it's a common full size, like, nonetheless. Like, there's a little bit more meat there now.
Yeah. Yeah, I like that, because if we
That's
mess up-
a ton of volume though. Like, that's a big space to, like, right? Like, the gas will come in and it'll go. It'll ignite.
our chamber, our nozzle diameter is,
Why do we have this? Go away. God, on shape makes me want to scream.
cause see, I'm thinking, like, what's the diameter of that hole again, that injector hole?
This?
Or igniter hole? I don't even know.
This guy
Yeah.
is whatever. Uh, 1.1565 or 530 seconds. That's what I wanted to know. Oh my god, I couldn't think. 530 seconds of an inch.
Because my concern is that hole is smaller than the nozzle hole. So then all of the air is going to go out of the nozzle before it's going to want to go into there.
No, no.
Yeah.
That's it'll. It's not just gonna like flow and be gone.
See, that's my concern. Is it'll just it won't actually.
No, it'll ignite it. Don't worry. It will go. It will definitely go. That whole chamber, the gas will diffuse across in every nook and cranny possible. That that oxygen to fuel mixture
Well,
will
yeah,
diffuse.
that's true.
Don't worry. It will go.
That's true.
It'll definitely go. I'm just worried about a hard start because I'm hoping that it goes as soon as the gas enters there versus it filling the entire chamber and then going boom and then trying to sustain combustion. But,
Yeah. All right.
we'll design it like this, and I don't know. I might have some big scaries, and want to do. I might just buy an igniter, or like we could literally go get like a rocket engine igniter from. Ooh, that's actually a really good idea.
What?
We could go to the hobby shop and get rocket engine igniters, and then just
Oh, like those SCs?
the SC's rocket engine igniters, and maybe we can cook up some like sugar candy, like rocket fuel, and then just
Straight up, actually,
mix
yeah.
it in there, and then just cure the igniter inside the
Oh.
rocket fuel, stick it in there,
Yeah.
and then like ignite,
No,
and it starts burning
I like that. Let's do that.
instead.
No, we'll do it. Well, we'll put that
Oh.
stuff like lining the hole. No.
Just in the engine, like inside.
Yeah. All right.
Like so that like I'm just whoa. Oh, okay. I was like, what just happened there? Did you just move it over?
Air breathing rocket engine. All right. All right.
Oh, you forgot to put the hole in that plate.
Yeah. Okay. Template.
Yeah. We'll do that. We'll make some of those so that we have extra things. I don't know, because I'm gonna be scared. So what we'll do this. We'll probably do the R candy thing first, the rocket candy with the igniter to start it, because we can just shove that in.
Yeah.
We'll make like a little tiny ball of it so that it actually gets ejected out the nozzle when the engine starts and doesn't clog the nozzle and blow everything up.
Yeah.
And then it goes boom.
All right.
We'll make a little R candy thing, stick it in there, and then that'll start burning, and that'll ignite the engine, because then the gas hits that and it immediately goes.
So, are you saying like put the rocket candy like right where the injector is? And then
Yeah, we'll push it
or
all the
the
way.
igniter-
Yeah,
oh,
we'll push
God.
it all the way up towards the injector face, so that when it starts, we'll hit it. We'll start. We'll hear it burning because you'll see a little bit of smoke come out, and you'll hear it start burning.
Yeah.
And then it's like boom, and it goes, and the engine just dumps fuel and oxidizer in there. And
Yeah.
as soon as it gets in there, it's burning. And what we'll do is then we'll do this. If the engine survives and we can test it again, we'll test it again with the glow plug. If the glow plug works,
Okay, I like that.
and
I
then
think that'll work.
and then we can, because I'm afraid of a hard start and just nuking the engine immediately, and then not getting any data and being like, well, that sucked. That was a waste of time. Well, not a waste of time, but that was not a good idea.
No.
I'd rather. What's the word I'm looking for? I'd rather knowingly test it, knowing that the R candy is going to successfully ignite the engine, and then afterwards do the experimental igniter, the experimental glow plug igniter, and see if I can get that. We can get that to go.
Oh man.
Oh, you have it there. Bolt hole.
Oh yeah.
Bolt auto.
All right.
Now you can do the pattern, right?
Oh yeah. No, I'm gonna make each one.
Yeah. I was gonna say, please don't do that. Oh. Do not do 8. We do not need 8 in there.
It looks cool.
No, it doesn't. Put 6. Please put 6. I have to. That'll be
6.
2 more holes I have to drill and tap, and that'll be
Yeah.
because that's more mistakes to be made.
That is true. Nice.
You have to put the same holes in the chamber. You don't have any holes. It's just solid right now. You're bolting into a solid.
Oh boy.
And also you have to put.
Yeah.
Oh, this is gonna get spicy. We have to do a little bit of thing. Oh, so that's not the right thickness. Do 0.5 millimeter on that.
It's 0.5 millimeter?
Yeah.
Man. Okay.
We don't want it too thick.
Yeah.
But then the next thing we're going to talk about is you have to think is you have that roughly 0.5 millimeter thickness. You have to make sure that you make the little ablative slightly longer, as thick as that, or just something like, you know what I mean? It's
Oh, slightly. Okay.
yeah.
Slightly.
Like slightly oversized, so the blade
Yeah.
will stick this much further out of the chamber up towards the plate,
Right.
because you'll have that little tiny sliver of stuff that compresses very slightly.
Ah, I see.
Yeah.
Okay.
We'll have to I don't know how we're gonna cut that super accurate.
Mm.
We'll probably cut it oversized and then take it to like a belt sander and then kind of like sand it down a little bit by little bit and kind of test fit, sand it, test fit, sand it, test fit.
Yeah. I think the approach couldn't hurt.
What'd you do with that? Did you break it? Or is this the? Is this the same part when I do that? Oh, it's a gasket.
Yeah.
Is that centerpiece an inch in diameter?
Yeah. No,
What?
it's because it covers.
3/4, you mean?
It'll cover the 3/4.
Oh, okay. Okay. Sorry, I misheard what you said. It's like a quarter of an inch. I was like, what?
Butaining gasket.
You just name a gasket because there'll be two. Oh wait, no,
It's gonna be
two gaskets. You'll have one on the retaining side, right, and then one above.
well, yeah. I guess I can
Name it like
No,
a
I'll-
plate. Like just name it gasket.
because. So this is what you're thinking.
I'm about to scream. No, I'm kidding.
Alright.
Nope. Something happened.
Yep. So
Get rid of that. Get straight.
get out of here.
What?
Alright.
Now it should be fine.
There's another one.
There is another.
Okay.
Don't you have that? No, you don't. Oh, it duplicates it. Doesn't it? Takes the variables with it.
Yeah.
That's actually really dumb.
That was dumb. We can make it.
How much do we have to do? I forgot what we have to do.
We have to order parts.
Well, we're gonna order them tomorrow.
Oh, do we?
Yeah.
Why? That's not what I wanted. Hold on, sorry. Alright. 8, that's fine.
Just kidding. Then make it a.
Yes.
Yes. Oh. select the circle and then click the other thing.
Nice. Alright. That's retaining. That one's gonna go here. Do we want one?
Yeah, we're gonna need two.
It'll be the same thing.
Slightly different because we have the holes that come through it.
Well, that's what I was thinking. Do we want to? Nah, you can just leave it. It'll be the same. Like, cause
No, you have those. Remember how?
No, yeah, but
You have to, otherwise
Oh,
it'll
I
flow.
do,
Flow.
yeah.
There's flow paths now. You'll mix fuel and
they're
oxidizer
slow to each other.
in this weird pocket, and then
You're right.
it goes nuke.
Yep.
It goes nuclear. So just duplicate the sketch, right? The whole sketch from the bottom of that one plate,
Yeah.
and then just boom, put it on there. Do. Yeah. We only have one person watching. Everybody's leaving. Everyone has left. It's probably also because it's like almost 8 p.m.
Yeah.
on a Sunday night.
No. Oh yeah. Oh my god. Yeah, it is. Wait. No, I did this wrong.
You have that name. Is that thing called Part 1? Oh, okay. I was just like, where's Part 1 at? Okay, that's fine.
No, never mind. Never mind. I thought something was wrong. It is not. Hold on. Just realized I don't want those. That's a good question. I don't know.
Somebody's here.
Yeah.
There. Oh.
Go
Go to the other one. Go back to the other one. No. Don't do
Hold
that.
on.
Don't do that. I'll scream. I will literally scream. Oh my god. Oof.
Oh man. I mean, it works.
Whatever.
Yeah.
Your cat, dude. This makes me want to cry, but it's okay. Now make
it
those
works,
sketch.
though.
Now make those sketch lines because it's gonna like break.
Yeah.
Just- Send it.
All right.
Oh, there you go. A gasket. All right, I'm getting some.
That needs to go away. Getting gasket. Alright. Alright. So, let's see, I'm just gonna reassemble it.
The engine's looking like an engine now.
There it is.
It's actually pretty neat looking.
No, that's pretty cool. Yeah, alright.
The cool thing would have been if we like welded that on there so there wasn't actually any bolts here and we just had
Yeah.
the nozzle sticking out. Boom.
Actually, I'm gonna go ahead. Yeah, hold on, let me.
Yeah, unfortunately I would like to do something else, but I think it's kind of important to show this. Like all of it. Because this is
This
the
is
design.
literally- yeah.
This is the engine design. If we don't show this, it's like, well, how did you do it? How did you get there?
Yeah, that's
We
a good
showed
point.
kind of the some of the basics.
Yeah. Every time
It just dies. It's like
well, hold on. I think that's a circular pattern.
just make it. Yeah, do a circle. We're gonna get
Not done.
we're gonna get doxed like 40 points for poor CAD.
I know.
What? What? Oh, is it because like one of these is one of them fixed in place somewhere? Just make that 19. It's a circle, but it's not on. It's not perfect though.
All right.
Why? Should do an angle. Do an angle. Just do the angle. Oh man, some screens. Okay, yeah, you'll be fine. Just. Oh no, not fine. What are you doing? Sketch 2.
That's not right.
Oh, you broke out of the.
There we go. That's definitely not right.
What did you do? What is that? Oh, my bad. You're in the part now.
Yeah.
It's like what is going
It's-
on?
Not good. What's the depth? Half, yeah. Not half a millimeter. That's incorrect. Okay. Alright. Now we're cooking.
insides of the engine. Indeed.
Oh, we forgot the O-ring.
Yeah, right there. No. You had it the first time. You could have split the difference and gotten it perfect. Please don't do this. No, please don't do this. Oh my god. You want to die.
See? That's fine.
Please don't do this. Doesn't this engine look so neat, honestly?
No, yeah, this is
Will she do it? Oh, goodness me. You know, because you don't actually...
It was just delayed.
Okay, I was going to say, you're not actually constraining things, but somehow you are. I don't know.
No, see, it's weird because you wouldn't think like, well, it's like a fastener. They're very weird how it works. I've never seen another CAD software that uses fasteners. So I don't know.
Boom, boom, bop.
That is-
You did the wrong side. It's going to... if you flip it, it's going to do it wrong. What?
It doesn't flip it. It like mirrors it.
My brain does not process.
No. Hold on.
Uh-oh. Haha, didn't do it now. What?
Wait, hold on.
That's it.
Yeah, where'd the...
There's no holes. There's
Wait.
no holes there either.
What?
You did it wrong. Dude, I'm so disappointed in you right now.
Honestly. Alright.
I can't believe how bad you are. And I'm so...
Alright.
Obviously. Do not copy that scam.
That's not
Do
right.
not do it. Don't do it. No,
That's-
don't do it.
Oh my god.
I'm just kidding. That's fine. We're fine. Kind of not. How many people watch? One. Alright, is that 3? That's a 3. Wow.
That's right. Okay.
Bi-Propellant.
Bi-Propellant?
Alright, now I'm starting to say do things. Oh, whoa. That's broken.
It's because it doesn't recognize the variables. It's like, our variables aren't here. That's not right. Alright, well, here, hold on. I really don't need any of it. I don't know why. I don't know why.
Just do it from scratch.
Yeah, honestly, it's starting to...
It keeps breaking. Everything is breaking.
So,
There's still another one.
nice.
Just never mind. Just to draw a circle. Oh, you're on the wrong side.
Hold on. Let me just...
Start over. Get out of here. Okay, it's like right there. Do you have what?
Oh, I forgot it. No, that's right. Oh man.
We're gonna start to get dying inside a little bit here. The angries are coming. Angry.
Yes.
He's gonna. Yes. You have to add the holes into the chamber. do a flippy.
Oh, is it backwards?
No, it's just you don't have holes. You didn't make them.
Oh, that's right.
It's like, there's nothing wrong here. You just didn't do it.
I just didn't do it.
Yeah, that's correct. Wait, is that right? That was 6,435.
Mm-hmm. I doubted myself earlier, but I was like, no, it's gotta be. No,
87.
maybe 87. Are you prepared to tap 87 holes?
Okay.
I think that's just the wind.
Or not.
Or not. Someone's on the roof. I mean, that could be possible too.
That's fine. I mean, it's fine.
That's happening.
I mean, it doesn't really matter. You did 0.5 millimeter again. Oh no, you didn't. Oh wow, my eyes did not process that hole.
No, it did kind of look like it for a little bit. All right. All right. Okay, that's looking better. That's looking a lot better. One thing about Inventor that I did like was the fact that it makes a little like sound when you make things.
Yeah, it's the best thing ever. It really is. Oh my gosh. Now you gotta do all those. Derp, 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 derp. Derp, derp, derp.
I feel like this would be a nice thing to time lapse if we were editing this.
Well, I'm recording the whole thing to my computer, so we can like,
Like some movie magic.
you know, do a little
video editing things, yeah.
Oh no, we froze again.
Did we? Uh-oh.
Hopefully it wasn't like an hour ago. I hate all these things. These are not meant for live streaming, obviously.
Mm-mm.
Hold on.
We're back? Alright, nice.
We're back.
Alright. We're almost done. Yeah. Nope.
We're having dinner.
Food? What?
We don't eat as engineers.
No. Alright. Okay.
Add some bolts.
Yeah.
Do you need the same length? No. You don't need a quarter. Inch and a quarter. You need probably.
Should have done that earlier.
What, told you earlier?
No, I should have like pasted the bolts in like that earlier.
Oh. except now they're facing the wrong way. Just kidding. This thing is looking nice.
It is looking pretty cool. It's got like. All right. Okay.
Can you turn off the mates, like those fasteners? Like, can you turn on hide all connectors?
All right.
It's just
Don't look at it yet. We gotta make it look cool.
It's making my eyes like explode.
No.
Well, we can assign materials, but we'll not do that. Just make it like a silver color. Do not make it green. No.
All right.
Over there, one of these. Choose one of those. It's gonna be aluminum, so choose like a nice bright color. No, that's not aluminum. That's not an aluminum color. Choose like a super. Nope. Keep going. There we go.
Nice shiny aluminum. They're all gonna look the same.
I don't care. That's what it's gonna look like in real life. No, do not make it tan.
Yeah. You gotta make it interesting.
No. Oh my god.
Literally all it's just different shades of tan.
That's disgusting. That's just
so disgusting. Alright.
You're being disabled.
Oh no. I lost my mouse. Alright.
I'm just kidding. Oh, okay. I thought I broke the computer.
Oh no.
What is
Alright. So everybody watching, this is
what is going on? I
essentially-
can't get off of this.
oh, is it stuck?
Yeah. Oh, there it goes.
Alright, so for y'all watching, it's been quite a long time since we did a lot of the design work, but to kind of recap the entire process so far, we started off with the NASA CEA. We had our propellant, hydrogen, and oxygen. We plugged that into the CEA, got out values like the OF ratio, the specific impulse, the chamber pressure, the the pressure at the throat, chamber temperature, throat temperature, our gamma, which is our ratio of specific heats, and then our area ratio, which is the ratio of the area exit to the area throat. So using those values, we used a couple equations from Rocket Lab's liquid Bi-Propellant design book, and we got a couple characteristics for our chamber design. So we got our chamber volume, chamber length, diameter, other important parameters. We calculated our L star to be 49.6, which is on the border of the 50 to 100 recommended L star. And then after that, we used some of the values from the CEA to find the mass flow across the nozzle throat. And then we used our OF ratio to find the mass flow of our, the mass flow of our fuel and our oxidizer, and then use that information, more Rocket Lab equations, to find our orifice diameter. And now we did some upper manifold brainstorming. We made a PNID. For those of you who don't know, that's a plumbing and instrumentation diagram. And which was fairly simple. It was just essentially for each line, for the fuel and oxidizer line, it was a solenoid valve, and then a check valve from the regulator, and then just right into the engine. Let's see, and then what you're looking at now on screen, or that assembly there, is the final product, where we have a main chamber. Inside the chamber is an ablative, Garlight, for the cooling. On the end we have...
Let me do it.
Yeah. So then on the end there you can see our phenolic nozzle. Everything is retained by we have a retaining cap on the end, which holds the nozzle in place, and...
All these inefficiencies.
Yeah.
There's a couple adjustments to be made.
Right.
But
yeah.
the basic concept is there.
Yeah. So we're essentially just screwing right through just an aluminum cap on the end, securing it to the aluminum chamber. And then up top for the upper manifold, we have our two orifices coming down, making one unlike doublet there, and then we have our fuel and our oxidizer coming in from the side. They go into these little pockets, which then go down into a little hole, which then goes into the orifice channel, I guess. And then kind of offset on the side, we have, let's see, if you can go ahead and click the, we have the, let's see, we have the pressure transducer. That's going to be, let's see, it's going to be on the side there, and it's just going to come through a little channel on there. And then we have a glow plug as the igniter, which is right on the edge of that phenolic, or I guess ablative lining there. So a couple of things we had discussed to help with the ignition of the engine is getting one of, I believe it's called rocket candy, just putting it right up there.
Yeah, rock candy is just a fancy fancy term for sugar, sorbitol, and potassium nitrate motors. So
Yeah,
yeah,
just something to get a stronger flame to ensure that that's actually going to ignite and not just fill up our engine with gas and we have
and then
more start.
boom, and then
Yeah.
it blows up or breaks something. Nozzle
Yeah.
would probably break.
But now I think the path forward is, I think we have a bill of materials that we priced out for this engine, and I think our total cost is, let's go ahead and go on over there. So it's,
Right now it's 45.
It's
There's
45.
There's a couple changes that are going to be made, so it's probably going to be a little bit more money. Well, we're going to decrease some things and then increase some things, so hopefully it balances out properly.
yeah, we still have the gases to price out. We still have the hydrogen and the oxygen.
Which shouldn't be too expensive. I don't
Yeah.
think. Well, we're looking at probably roughly what $30 to $40 a piece for total rental for those guys. So
yeah, I think that sounds about right. But then, of course, there's also, I think, the battery, yeah. So, the bill of materials needs some updating, but it should come in at, let's see, after updating, we'll make sure, if anything comes up in which we need to kind of, it'll be under 500. Yeah. And we'll essentially make this Google Sheet available. We'll share the link, and y'all will be able to see all the materials and the calculations we went through. But let's see. I guess before you close out, we'd like to do a little bit more design work on what exactly the test stand is going to look like. I think that might not be a bad idea.
yeah, but we might take a break for a few minutes
Yeah.
because there was a lot of CAD. So
That
all right,
was.
we will be back in a couple minutes. Thank you. All right, we're back. We got some wire here. We got some wires. All right.
All right. So the plan right now, going forward, is is essentially I'm going to kind of go into a little bit more detail on the test stand design, kind of actually designing what that's going to look like, and then Dylan's going to do a little bit of work on the GUI for cycling all the solenoid valves in the igniter. So once we finish that up, throughout the week we'll be ordering the parts off of the bill of materials, and we'll keep you guys posted on
What else was on the list?
Let's see.
Did you make a list?
I did. I made that.
Oh, okay.
But that was it.
Oh, okay.
Yeah.
Yeah, I'll see what I'm going to do right now. I might check some of the math and make sure that's all correct before we order things and do stuff, but
Yeah.
I'm just thinking I might start the GUI, or I might do like another live stream midweek sometime for like in one night, because I'm thinking I can do this in one night. It's not going to be complicated. It's going to be connecting to interfacing with an Arduino. And it might be better to do that because I can wait until we have the hardware, because I have to test the GUI, right? I can't just build the GUI without interfacing with hardware. So I don't know if I'm going to do the GUI tonight. I think I'll wait until midweek and I'll get all the hardware, and maybe we come back and on a Thursday night or something like that, or Wednesday, Thursday night before we start the build. We'll do a little mini live stream during the night to interface the Arduino with MATLAB, and that's going to be cringy as heck because I'm so rusty with MATLAB. It's going to be all over the place. But yeah, so I think we'll do that maybe during the week sometime before test day, or on the day we build everything. I would rather not, because I think it's going to take a little bit of time to make the GUI. So we'll think of it. I don't think I'm going to do it tonight though. So we'll kind of just keep working on this stuff and figure out what's missing, and then kind of fill in the gaps and make sure that we have most of the design information done today.
Yeah.
Because that's the important part. So yeah, cool.
Yeah, and if y'all have questions, please put them in the chat, and we'd be happy to answer. All right. I think I'm gonna start doing some sketches on what. Let's see. Yeah, I think I'm gonna go to whiteboard and do some sketches. Nothing too formal. Just kind of throwing around ideas.
I got the whiteboard cameras down again.
Uh-oh.
Here, I'm activating it. There you go. That's not important anymore.
Oh, that's what we forgot. I just realized we wanted to put a lip on the retain plate so that the clamps on the test stand had something to, I guess, grab. Do we still want to do that?
That's going to be an issue. If we do like some sort of, the other like what I was thinking of doing was either just getting like an angle bracket from Home Depot, cutting it, and then drilling. So we have those bottom 3 holes. Like we'll have 3 holes right there. You know, right, the 3 holes on the top of the engine, and usually just basically putting the plate in between those and the engine. So if you go to like engine CAD, like putting in like literally cutting out like getting an angle piece piece because we're not going to have that much thrust at the seal angle, and then cutting out, like drilling holes to put those in and cutting out a notch to clear that, and really bolting that down to the wood and then bolting it to that.
Oh, I see.
The other thing is we can just get big, it might be easier to get C, like it might be easier to do those big, like the clamps that, or those things that you got for the,
Yeah.
for here, right, downstairs.
Are you talking about the
The
U-bolts?
U-bolt.
Okay.
And just U-bolting it down to a piece of wood. It literally might, it will be fine. It's not gonna move. As long as there's a good climbing force on it, it might scratch it from the outside. Who really cares? Just put a little bit of rubber right there to protect it, but it's not really important. It's not gonna go anywhere. It's gonna produce 8 pounds of thrust. It's not gonna go whoosh and go flying away, so, yeah. I'm just gonna make a key for the for this. So I'm gonna make the things that are like inputs.
Oh, okay. It might not be a bad idea to clean up some of that madness.
Yeah. Do a little bit cleaner.
Let's see. Okay. Oh, nice. All right. So, I think I want to do conduit clamps actually, or
So they have more surface area.
yeah.
They're gonna look so disgusting though.
It's gonna look bad, but I.
Hey, at the end of the day, right? It doesn't matter how bad it looks. You
It
built,
just needs
you
to
built a rocket engine. It
Yeah.
just needs to work.
I like those better. Maybe we'll do 3. Like that. Have that on some kind of table hanging off the edge of it. The check valves were pretty small, right?
They had quarter MPT on it.
Oh, okay. Do you think I could fit a line of those under a foot?
What do you mean? Like, is there enough space?
No. Because, well, alright, so what I'm thinking is, as far as the fluid lines go, we have one come out, we bend some tube, we go on each side, and then we go through this panel, and then we bend it up, so then it comes out here, and then we just mount it to like a wood panel.
The problem
So
is
then they're gonna
the set. I don't know if this is like super critical, but it
Mhm.
says that I've read that you want to keep the solenoids in the vertical orientation to make sure that they don't like so they can't mount them horizontally like that or vertical like that.
I see.
The other thing you can do instead of making it like a super complicated, like you can do this.
I know, you could just make a long table.
Long table. Like the one thing I was thinking of doing to simplify it is just having it sitting on the ground, like not even having this really off the ground. Just like,
No, I was planning on these being like
like
a couple inches.
Oh, okay. I was thinking even smaller than that. Like, okay, maybe like a one stud there, like just to keep it off the ground.
Yeah.
But it's like engine, and then it was almost like this is not too scaled from like glass plate. And then check valve. Maybe coming through, and then two bottles. And then this is like the blast plate, and this is really just like a little narrow 2x4 thing. But then also maybe, because how do you want to weigh it down? The other thing I had to think of was almost like extend this and make it a frame so you can actually put the two bottles in there side by side, and then make a little plywood plate so that the weight of these is holding the whole system down. The weight of the two bottles sitting in the back is like holding everything down.
Oh, so like
So like these
What
would
if
be
you-
extended out somewhere like this, and it'd be like a plywood cradle for these guys that's laying on the ground.
maybe if you had like something like that, and that's the bottle sat on that thing. So like maybe it looks something like that. We mount the plywood to here. The engine sits off like that. Blast lines here. The bottles sit on it like that.
Yeah, like something like that, exactly.
Okay.
Just something super easy, and then that way, if we can get like more plywood, you can maybe make like a cage or something, or some way to retain it. Like we can try to keep it. We can even build like maybe a whole little house for it, just to retain it. Like if it blows up this way, if it blows up downstream, then it doesn't really matter. But just like to keep, like maybe we just keep it so it's like the plane of exposure, like just the nozzle little guy sticking out there, and the rest of it's just plywood. Even though the plywood is not really going to be like the most legendary thing on the planet to keep it, keep those parts in. If it blows out.
It's gonna be hard to secure that panel right there.
Not really. Oh, you mean like how are you going to secure it? I was going to just do this. I was going to do plywood, and then down along the sides, bracket, just cut the wood at 45. Like that. Or not all the way at the top, probably. Like midway up, and just screw, like right here, look at this. Just screw right through, like that, and then screw down and into the deck. Something like that. And that's the blast plate. So it looks like this from the side almost.
Oh, okay. That might be actually pretty easy. Oh yeah, and then we can just mount like a there. All right, yeah, that's pretty simple. A box, a luncheon box.
Literally something like that.
Yeah, if you extend those up to the top too, you can just mount like a thing of plywood on the top and just secure the two corners on that bracket. And then-
Oh yeah. Yeah, I don't know if we need. Like, I'm just saying. Like, I think we're gonna have plenty of wood. We're not gonna run out of. We're literally gonna get two
No.
8-foot 2x4s, We'll do the CAD. We'll find the lengths
Yeah.
in CAD here,
Yeah.
and we'll figure it out. I don't think we're gonna have an issue with that. We just have to see if we can get some like small 2x4, or not 2x4, some sheet that isn't expensive. Maybe
Yeah.
sheet's a little pricey, but not like crazy, but enough that it's like somewhat of a concern.
Yeah.
But yeah, I don't think we need this. We don't need the back side. We just need the front side to hold it up.
Mm-hmm.
And you're right. We can literally make the engine sits in here like this.
Yeah. All right. Like that.
I always do this wrong. Just need to taper to a point like that. There we go.
All right. Cool.
Off the end.
Almost there.
Look at this thing. Oh, let me finish this up quick.
Oh.
Almost done. How do you get the thread? Oh, there we go. There's base off, but
Yeah.
it's a thin clip. It's technical. Just mark it. Alright, there we go. Look at, so I made like inputs mid-step calcs that are like not kind of important, and then outputs and constants.
Oh, cool.
So at least for now, like this is good enough. I just didn't
Yeah.
touch this yet. So here, you can jump over into my CAD over here so that they can see what's going on.
Boom, look at that bad boy. Look at that engine. Nice looking engine there. Alright, we're gonna do this. We're gonna create a new folder called test and then we'll make a folder.
Oh wait, there's already one.
Is there really?
Yeah.
Where?
Engine right next to testing.
What do you mean?
Right here.
Oh, a folder for the engine?
Yeah.
Oh, okay. Well, I was making a folder for the testing. I was about to make an engine test folder, an engine folder. Did you put anything in here yet? No.
No.
Just the nozzle. Just this is
Well,
in there.
yeah, because I was in the process of.
Yeah, I know. And then we I broke it.
No.
I broke your process. All right. Oops, I keep clicking on the right. Ooh, are you doing something?
No.
Oh, you're moving. Okay, things are moving, and I was very confused.
It's a ghost.
It's amazing how quick it is. All right.
No, actually, it's like a Google Doc, which is part of the reason why I like it so much.
All right. Can we get rid of test?
No.
Yeah. I'm deleting it. I can't though because you're on it. Get off of the test so I can delete it.
This document is in use. Alright, cool.
Where did the test stand? Oh, we're in engine. All right, there you go. Now you take the reins over here. Man, it is really sucky to be doing that. Like have one person on doing CAD on the computer that is streaming. It is really botched.
Well, you want to do, like, because you can do some of the test and CAD, like, it's like a Google Doc, like, you can, I've actually never had it to where both people were actively editing part studios on,
Well,
like,
we'll do-
one workspace, but
Yeah, yeah. What do you want to do? How do you want to set it up? Do you want me to build the wooden frame? I'll do the wooden frame, and then you can maybe figure out the fluid system.
yeah, that works.
That's a pretty good idea.
Alright. Go
Alright.
time.
4 people watching. Cool. All right, now watch me suck. Oh my god, it froze.
Did it?
Just now, so I caught it this time.
Nice.
We're back online. All right, here we go. I'm gonna do this the right way. I'm gonna make in the test stand folder. I'm gonna make a folder called the wooden frame. And I'm gonna do it. I say I'm gonna do it better, but I'm still gonna do it crappily, and it's gonna be all over the place.
Everybody has their own CAD style.
I'm just used to Inventor, which I think is like a million times better than this. But Nobody,
Inventor's pretty nice.
nobody wants to listen to me. All right, so how do I want to do this? We'll do this. Oh. God, I wish I could make global variables
No, that would be nice.
and say like, hey, reference across all these Park Studios, reference
Yeah.
this, please. This is gonna be funs. Alright, so fun fact, 2x4s aren't actually 2x4s. They are 3.75 by 1.75, I believe. Which is really stupid. But that is how things work because we keep skimping out on wood. People don't want to... Nobody wants to make things correct anymore, so we do the old skimping for the wood. The wood skimp. I'm trying to think, how long do we want to make this? I think 2 feet's more. 2 feet's more than enough, I think.
Yeah, that should be.
Yeah, I'll do it 2 feet. We'll start at 2 feet. So they actually not have pine. What? Dune oak wood. There's no reason for me to do this, but I'm doing that. Just kidding. I just want to. No. I'm gonna edit the appearance. That looks like a good wood color.
Nice.
How wide do you... Oh, actually, how wide are those little bottles? High pressure bottles. They're like 9 inches, aren't they? They're like 9 inches in diameter.
We have a size 80 for. Hold on.
I think they're 9 inches. The other thing we have to think of, how are we going to strap not the bottles down, but kind of, really.
Yeah, actually.
Oh, I have an idea. Never mind, I keep doing this on a piece of paper. Whiteboard.
I have an idea. So this is what we'll do. We'll do this. We'll hopefully have enough wood for this, but we'll have our 2x4s chilling like this, and like this, side by side to make up like the base underneath it, and then we'll make like a cradle based off of, because we're gonna have this vertical panel here, like that, and I can probably just screw it in and make a little like wood cradle, like that. That's in like a loop around them, and then put a piece across so that they just slot in and rest on here. They rest on those bases, but then the bottle's like here, like that. So they're like in a crate, just to constrain them from moving, and they can be side by side.
What are you doing the supports, like the edge of the cradle with?
These?
Yeah.
It's just gonna be the extra 2x4s. I'll just make 2x4s. So like, looking straight down, you have like, the bottle is pretty big, so you have like 2x4, bottle, and then over here. Actually, we'll try to get them as close as possible. Actually, try to get them as close as possible. Oh boy, what's going on here? And then the cradle would be like coming off this front and go like this around them. Like that, and into this wood, that wood sheet. Something like that.
See, you're not.
Not making sense? Oh, am I not on?
No, you're not yet on the camera.
Dang it.
But I see what you mean.
Did you fix it? No.
No, it's still.
I literally thought I did this. Junk.
Oh, okay, nice.
So, like a little frame going around it. There's a high pressure bottle here, high pressure bottle there. This is the front panel right there. And then you just like screw this all in, or box it around, and then put a brace across them so the bottles can't move anywhere.
Okay. But what's the point of this crossbeam then? Why not?
Well, it's in the front.
Well,
so you
okay,
fall
I see what you
forward.
mean.
It's
No.
just meant to be a spot for them to sit.
Well, no, because I was thinking like, oh, you can just put them flat against here, but we're putting plumbing there. So. Yeah. Okay. That works.
Well, are we putting plumbing there? Remember, we want to make the valves, all that stuff as close to the engine as possible. So all the valves and stuff might be on this side of that blast plate. The blast plate
Well,
is to protect the bottles.
Originally we were thinking we would put it on this side because we wanted to protect the solenoids if it were to explode.
But remember, we want to get them as close to the engine so we don't have that onrush of air.
Well, yeah, but you can still do that by just moving the plate really close against the back of it.
Oh, yeah, I guess you're right. Yeah, you're right.
I mean,
honestly, if it explodes, I mean, solenoids, like, what are you protecting the coil? It's not really, it's going to go bang. Something's going to break.
no, actually, because if the solenoids fail, we might actually run on this side. Yeah, let's put it on that side. Yeah, because
Do, like, all this, all the,
yeah, that's fine. But then if we,
alright, this will be, oh gosh, actually, I want to keep that image. Like, this will be the 2x. This will be this, right? Engine mounted there. And then we have the other 2x4s that kind of come down, bolt there, bolt there, then there's a frame like around this. This will be probably all the way down the back. This will probably be like this, actually, right? And have that frame, and then put more pliers here and here, and then all the valves and stuff will be right. Hopefully, we'll probably have enough space this way to do a line, and a line, and then come through and go to the bottles.
what dimensions do you want to make this? So like maybe like
Well,
a foot by 2 feet?
yeah, well, this is the critical thing, right? Because like these are 9 inches in diameter, I think. I'm pretty sure they are.
Oh, well, yeah, I'm just trying to think.
So if we do right next to each other, like butt them up, this minimum is going to be 18 inches.
Oh, I see, I see.
That'll be 18. And then the total width would be, what is 1.75 times 2? 1.75 times 25.
Yeah.
Yeah, so that would be 1.5. It's 3.5.
Yeah.
Oh my goodness. I literally, it's not 3.5. It's 18 plus 3.5, 21.5.
Alright.
So that'd be
20 and a half.
Alright.
Hold on. We'll be right back.
we're back in the whiteboard. Woo! There we go. Okay, cool. So yeah, I guess we're looking at roughly 21 and a half for this. Probably like, that's if they're like butted up directly against each other. So 21 and a half.
Yeah, I think
I don't really want to cut any like, so you can get these like panels, like that plywood. You can get like a thick plywood. They usually come in nice sizes. Like they don't come in 21 and a half.
Yeah.
I don't want to cut it either. We don't have a table saw. We don't have any sort of saw. Oh wait, no.
Yeah,
We do have those corners. We have those. No, we don't have the chop saw or the miter saw is not the right tool for that. But
Well,
we do have
that's true.
we do have a circular saw that we can just. So never mind. We're fine. That we can cut it if we need to. And we also had the miters to do the 45s for all these like angles for these guys.
Yeah, that's true.
We're making a sled.
Yeah.
Rocket sled.
Yeah, actually, no.
Yeah, and then it's like almost like gonna be like a little box like this. Right?
Yeah.
Are we gonna put anything on the top? I think we should. But that's a lot of expensive stuff.
That's what I'm thinking. It's
Like
gonna
this.
get expensive.
Let's not even do these plates. Just have it all exposed. It's fine. Okay, that'll be fine. We'll just leave it. Like we'll have this back up to brace it sometime.
And we just make those supports really long. So
We could always find like scrap material. There's probably somebody in somewhere that threw out plywood
Yeah.
in a container somewhere. If we really needed to get it.
Yeah.
But
Okay.
otherwise, I think we can leave this like.
The fire extinguisher on the bottom?
Yes.
Okay. Because we might need it.
Wooden test stand.
Yeah. That'd be a bad idea to have like a bucket of water too. Alright.
Engine. Rocket sled.
Yeah.
So yeah.
Alright.
Sound like a trumpet there.
It did.
Alright,
Yeah.
so I think that'll work. I think, because then we'd only need to get one of these sheets, and we go on Home Depot's website and look it up, and then we can hopefully have enough, like if you think about it, we only have these 2 foot lengths. We have plenty of plywood for that brackety thing in the back. And then we also have to maybe do like 1 or 2 cross members, like in between, right? Like there, and there, just to make sure it doesn't like flex and do weird stuff.
Yeah.
Then the weight of the bottles will keep the sled from moving. There's no way that 8 or 9 pound thruster,
Yeah.
that pound thrust
That'll
thing
be
is going to
fine.
move this sled. There's no way.
Yeah.
Well, maybe there is a way, actually. It could do it. There's enough friction. Put it on ice, it would move.
Yeah, actually.
Remote testing. Fire. Go shooting across.
That'd actually be kind of cool.
That'd be fun.
Rocket sled. Alright.
With a bigger engine next
Yeah.
time.
We just put wheels on the bottom.
Oh my god.
Alright. Are we gonna mount this to? So, are we gonna have like a plywood floor here, or
No,
is
just-
that just gonna?
It's just going to sit on those 2.
Okay.
Yeah. So we'd have plywood laying flat like that, and then we'd have not the plywood, the 2x4 laying flat.
Mm-hmm.
Plywood there, engine, and then this guy, bracket, which is 2x4, and then back here we would have.
Wait, what? Sorry, what is that? Right there.
That's just
that's
not plywood. It is plywood.
Okay, that's
the
what I was
plywood.
wondering.
Sorry, that's plywood. That's 2x4.
Okay.
2x4, 2x4, and then we have back here just. Obviously, this is like completely wrong, but that, and then we're gonna have like a little cradle guy. That's the 2x4 on the other side of it. That's a little cradle, and maybe I'll put one piece down there so that doesn't like want to flex like a lever arm.
Yeah.
Like I'll put a 2x4 down, and then the bottles will sit in there. This will be actually a lot closer. We probably, then we gotta make sure this is pretty high, right? Because the bottles are gonna be sitting there. The engine blows up, parts are gonna maybe go this way. And we don't want it to hit the regulators. Yeah. So.
All right. So that little plywood square then is going to be 21 and a half by
What, by whatever we could honestly have the engine sticking off this, we could, but we do have to bolt it down to the plywood, right? Or bolt it, or whatever those brackets.
Because just thinking this is the first thing we need to CAD because I'm going to need to know this area so that I can basically design out the fluid lines.
Yeah, you're right.
Because it's 6 inches long plus however much the nozzle is.
I would say, can you find, I'll find it. 2-inch, we need 2-inch OD, right, for 2-inch pipe.
Yeah, I can find those.
Okay, so what we'll do is 2. We don't
need
need 3, we need just 2. 2 is fine. We'll do 2, and we'll get it move it as far forward this way so that the nozzle is actually sticking out over the end, so that we can get as much room here. Because I want to try to stick it max 24 inches here. So.
Probably a foot. Probably need a foot. Yeah, we'll need a foot.
Of what? Space behind it?
Well, yeah, I'd say around a foot, maybe a little less than a foot for the plumbing.
Okay. Do you have models of?
Yeah.
No,
that's not a problem. I can model that. It's just
No, yeah,
I
yeah.
need to know. I'm just trying to gauge
what
that's going to be. So maybe 16 inches. I'm thinking a 16 by 21 and a half.
The other thing is we might change. We might change the valves that are on, or not the valves, the fittings that are on the engine. We can just make those elbows. We don't have to do tubing. We can make it an elbow fitting.
Okay.
And we can get elbow NPTs to.
All right. I don't know if we keep.
We make a list. Yeah. Use this guy. We're good. You could do the list over here. We have some space over here.
Elbow. It's gonna look crap because I'm thinking. About 21 and a half, and then. Clamps. Split screws there. Once the lines actually get, nipple.
We'll just drill a hole in the plate or in the thing for the diameter of that tube. In that sheet.
We'll find out what kind of tubing we need.
It's all gonna be 1/4-inch copper tubing. Oh, the lengths.
Well,
my bad. Yeah, you're right. I forgot. Forgot what you actually need.
And
you don't need my. Actually, that would be this. If we can judge this correctly, we can make it. It'll be really nice to drop the line right in, like that.
do those regulators attach from the bottom?
Yep, all of them are
Okay.
bottom fitting, so we can get it so that it's as close
They
as
are?
possible. Yeah, the hose barbs on the bottom, or the hose barb, the fittings on the bottom of the regulators. Yeah, do you want to see?
Yeah. I thought they were. Most of them I've seen on the site, so I was just curious.
Outlet fittings on the bottom.
Okay, nice. That makes it easy. Oh, that's what you do.
Oh, cylinders.
That's what I was going to add too. They're
You-
probably stuff
They're on grab
grab
CAD.
CAD,
Yeah.
Alright, let's do it.
Cool.
CAD speed run.
Test and speed run.
Yeah.
We are speed. I am speed. Assembly, boom, boom, boom. We're gonna insert Base wood. Insert another base wood. Restore! Broke it. Planer mate. Please no, don't do that. How do you make them that they're in the same plane? Parallel, probably. That's probably it.
That'll do that. You can still pull them apart here.
Dude, it literally did not do it that one. Broke it. I don't like the stuff here. I really don't. The assembly stuff in this is not good. I'm not a fan.
Yeah, it's not exactly.
I need to like.
Well, I wouldn't say it's yeah.
I'm gonna flip back over the whiteboard to do this.
Whiteboard's working. I can't do it. I can do it in Inventor, but auto like this is gonna go forever. Like I'll just be all over the place. I need to just literally just draw it. I need to do this.
How thick do you want to make that plywood? 8?
No, like get 1/4 inch at least.
Yeah.
I think I have a better idea.
I'm gonna call them stretcher pieces. Dang gummit. A little 6-inch piece of 2x4. That's oh god, how expensive? Oh my goodness.
$100.
Never mind then. Oh, that's 37 degree flare.
Yeah.
Do 45. You don't want 37 because it requires these sleeves. Do 45. That's what I spec'd out. I changed it because 45 is cheaper.
Wait, why don't you need a sleeve for a 45?
You don't because I don't know how to explain it right now. You just don't. I did it at home. You flare it to 45 and you put a nut over it.
Huh.
I think I don't know. I really don't know. I don't know how to explain it to you, other than just look up a 45 fitting. I guarantee you it'll be cheaper. Let's see.
Oh wow, that's a lot cheaper. $4. Dang. Okay.
That's what I mean. I don't know why, but it is.
Kidding.
Is this the assembly for the whole test stand?
Yeah.
Did you just CAD this, or did you find it?
No, I found it.
Okay, I was like, holy crap.
Yeah, I can.
Yeah, I definitely CAD it. Nope. I think we made the engine 4 too. Maybe? I don't know.
16. Do you want to make it?
Why is that box?
We can always make it shorter.
Oh, restore, please.
That's pretty cool.
What's cool?
Just
That is pretty neat. She gonna be awesome. It's gonna be great.
Oh yeah. Wait, what's the core PT there?
What? Oh, the 45 degree flare? That was our original.
Is that something we need to update?
Yeah, something was being updated there. Like I said, that the whole bomb isn't like good yet.
Yeah.
I hate this. I literally hate this. My god, look at this. I make parallel mates and it doesn't do it. What a piece of junk. Seriously, this is the crappiest software ever. I don't want it to be there. Is it gonna do it? What the crap? No sense has been made today. Does he make any sense? No. No. I gotta move this, thank God. Alright, I'm making this, I'm fastening this in place. I'm fixing it down so that this is now, what time is it?
6.
Oh my goodness.
Yep.
That's not good.
Nope. Yes. Not. Yes, indeed.
But no, I mean, yes. It'll be fine.
Yeah.
Good thing we're both doing separate things now. Oh my goodness, that hurt a little bit.
Sounded like it hurt.
Sounded like bad. My arm was hurting.
No, actually, yeah.
What are you doing? My arm hurts.
Yeah.
The sled. This thing is gonna be heckin' speed. Wait, is this the blast plate? Or is it the base?
No, that's the floor. The base plate.
Oh, okay.
How are you gonna screw this in?
What, here?
Yeah.
Long screws.
You know how much those are?
$1 a piece, probably.
Yeah, but where can you buy one?
What do you mean? You buy a whole box.
Yeah, but how much is a box now?
I spec'd out a box. Well, maybe I'll flip them around. Maybe I'll flip it.
What I'm saying is, like, you could just stack it on top. And then we
Stack
can...
what on top? Wait, hold on, what?
No, like... Alright.
It's
Alright.
big brain time.
You do, like... this. Okay. Something like that. And then you just put it on the bottom. And then you do... like that. Oh my gosh, my 3D drawing just went down the drain.
Oh my gosh.
No, that's what I wanted to do. Yeah, like that. And then ignore that line. So it's like this. That's how you do the...
Oh, I was doing it something different. I was just laying these on the ground, but I might flip them like this to make it so we can actually screw things. I did price out a box of screws.
I'm just saying it would be cheaper, but how much?
Like wood screws was for one box was $5.97, and they're 3 inches long. Yeah, I wasn't paying attention. I'm gonna flip them up like I. Well, actually, no, I was paying attention. I wanted it to be like this so that the things could sit on it. Oh, well, you can also just screw
probably
things.
Yeah, that's more structurally secure. Actually.
This is.
Yeah.
Yeah, we'll just screw.
I just don't want to buy like more than one box.
How much is in the box? There's a lot. Okay, I was like, what is going on? It's £1 per pack. That tells me nothing. 75. We have more than enough screws with that box, I'm pretty sure.
That's fine. I just don't, well, I don't want to buy multiple boxes because we have multiple different screw sizes. I want to do like, I want to do it with all one screw.
Oh yeah, definitely. Yeah. Oh, I've done it before with multiple things, and it becomes expensive quickly.
Yeah.
Yeah. So I wanted it like this, so you could put, because the bottles would sit like centered right here. Another one would be centered right there, or somewhere in this range.
Nice.
That was kind of the concept work there.
These clamps are kind of stingy.
Could you? Never mind. I can do it.
No.
There's the plug.
No.
A library.
We could undersize it.
Size 80 bottle. No.
No, that's not a size 80 bottle.
I hate GrabCat. Never finds what I want. Gas bottle.
Search is terrible.
And the gas bottles are huge. Look at this. They're huge. Like that's not that. What?
That person with the extra mile on there.
Oh, this?
Yeah.
Is that it? Are you kidding me?
onto the strap. See, it's like the name of the beer.
No, never mind. I'm just gonna size 80.
More saving, more doing. That's the power of the Home Depot. Alright. The clamp in the CAD is going to be, or the no, that's right. The CAD in the clamp in the CAD is going to be slightly larger than what it's supposed to be, just because the sizing in the master is weird. But the one in the bottom is correct.
Why does nobody have a size 80 gas bottle CAD model?
That's less than ideal.
It's just it's look at this 80 liter. That doesn't sound right.
No.
That sounds way too big. And it's from India, I think. So I'm
not
gonna
getting that anytime soon.
yeah, I'm going somewhere else. So everyone get a full size gas bottle. Give me a small one. Somebody made a burnt Berzomatic Fat Boy Max CAD model. Rip around. Oh wait a second. Oh. Poop. Type 20. Oh, it's a little big.
Oh my gosh, that pipe clamp. Holy crap.
What?
No,
How big it
no,
is?
that's fine.
Oh.
No, it's not fine, but it's
Why is it
fine.
not
I'll
fine?
find it out.
Oh my god, why is it not fine? Ah.
Oh man. Alright.
What's going on?
That was fine. Don't worry about it.
What's going on? I don't know. I have no idea. Alright, they do not have what I want, as always. Time to model it myself. Size 80. Bottle. Dimensions. Oh, they're only 7 inches in diameter, actually.
Oh, really?
Yeah. The big ones are 9 inches in diameter.
That's not bad. Alright.
Oh, they're also 32 inches tall.
Actually. Oh, so they're really tall and thin.
Which means it's gonna stick. Oh, dude, that clamp is a little big.
No, I know, that's what I was saying. Like, McMaster...
They didn't have a
I just did
stick.
it for the CAD. It's not actually like... So, the Home Depot has what we want. It's 2 inch.
The Home Depot has what I want.
Yeah. Which is in the bottom. But this is
They
not,
didn't have what
this
you
is-
wanted?
Yeah.
You really couldn't find?
No, McMaster had like very weird like. It was like, well, okay, well, 2 3/8, but that's not what I want. So then I either like grossly undersized it or oversized it.
I see
So
what you're saying. Yeah.
it's just in there for the CAD, but that's what we should buy.
Yeah.
Which is that's in the bottom.
Rotate that engine.
Yeah.
Oh gosh.
Oh man.
Oh heck. Heck and shoot. Dude. Whoa. Okay, never mind. Whoa.
That's gonna need
Whoa, bro. Look at that engine, dude. Oh my goodness. It looks like it's such a beefy thing, and it's literally gonna produce 8 pounds of thrust.
It's gonna be so tiny too.
It's gonna be like, psst.
You know.
No, it'll be a little bit more than psst. Like, probably break something. Something will break.
Yeah, it's possible.
Anything's possible with a popsicle.
Yeah, actually.
I like it.
Alright, so that's gonna go there. Channel drive, please.
Also, look at the plate. That's the actual orientation of the model. I'm gonna just do this. I'm gonna do a thing quick. I'm gonna break it. Oh my goodness. Dude, well you didn't buy, nothing was done correctly. Something was wrong, because look at it, it's broken.
Yeah, I know you exposed me.
Exposed.
Yeah.
He's been exposed.
Alright, improper CAD practices. That's also slightly. You might want to widen that that panel there, or that
bottom?
support. Yeah.
No, it's fine. You can have it. No. I have the idea in my head. I know what's going on.
Well, I know what's going on.
What's going on, you know? I was calculating, and I was calculating incorrectly, so that should be 7 inches between these guys. So there's actually, this piece should only be like 4 inches? 7 inches, and then...
Alright, each bottle's 9 inches in diameter, right?
No, they're 7 inches in diameter now.
So make it 14 plus.
No, I'm worried about just the center. Never mind. I don't know what I'm worried about. I'm just not doing it. It's not happening for me today, folks. Dylan cannot CAD. I failed.
Oh my god. Alright. Frame.
I'm going to pause it for a second. We'll be right back. And we're back. You are right, though. He probably could have done it. 2-day build.
That would have been, oh man.
Well, the thing is, you'd have to already have had all the parts,
Yeah.
which is stupid. We could have maybe done something if we had like a massive supply of parts somewhere.
Yeah.
And we've been like literally just, Harbor Freighted the entire thing.
Home Depot ending.
Home Depot Bi-Propellant. That's actually an awesome idea. I might do that one day.
That's what my hybrid was. It was a Home Depot hybrid. It wasn't, I don't know.
Can you get oxygen gas at Home Depot? No. Not like a high pressure bottle, but like a little thing of oxygen.
Yeah, you can get like the I forget what they're called. What do they call them? Forget. Bronzomatic.
Oh yeah. I know you can get propane.
Yeah.
Dude, this thing is gonna be so nice looking. If we make it correctly.
Yeah. Watch it.
Let's try. At 6:30, do you want to take a couple minutes to eat our food?
Yeah, I'm not gonna get out of here.
Before we forget and it ends up being 8 o'clock. Oh, I know how I want to do this.
Just front these metal wires.
It's just modeling a stupid bottle. I'm really just gonna wing it. We're gonna wing
Let's
the
make
bottle.
a cylinder.
I'm going to. That's what I'm gonna do right now. It's going to be winged. What is Part Studio 1? There's like a Part Studio 1 and 2 that have absolutely nothing in them.
Those are important, alright?
I'm renaming this to High Pressure Bottle. You ready to watch this? Wow. Wow. What am I? Okay, never mind. That failed so badly. Delete. Go away. Please leave.
Oh, come on.
There we
I
go.
can't believe that.
Go. Absolute masterpiece inbound. Unbelievable work by Dylan.
Nice.
This is going to be the most disgusting cylinder you've ever seen, ever. Just, you know.
Hey, as long as it captures roughly what the geometry looks like, that's all we need.
It'll be fun, yeah. It'll look pretty decent. Control Z that. Ooh, whoa! Oh man, this thing's gonna do a break.
Don't break it.
Bonk. It's gonna do it. It's done. I've done it.
You've done it. Nice.
Oh my god, dude, that looks actually really nice. Wait a second, what is this? Is that a fitting interface? You did this so backwards.
No, I know. I'm just slider making it so it'll all be straight.
Okay. Well, I'm just saying it's like you want check valve after valve before engine.
Oh, you're right. Well, no, it doesn't matter. Hold on. No, I know what I'm doing. Do I? No.
I don't think you do. Just kidding.
I just don't think it's not working like it should. All the planers are dying. Hold on.
We could make. Can you get a fitting?
Oh, an NPT to an NPT. Oh.
And just have it just ultra dense right there.
Actually,
so 1/8 inch NPT elbow to 1/8 inch NPT to the. Oh no, those are quarter NPT. Can you find an 1/8 to? I'll find it. Or maybe not. You'll find it first, probably. Speed run. Speed run. Elbow. Already failed. I'm too many elbows to look at.
all the elbow. I think I'm on the same page. I'm on the same. Yeah.
He's done it. He's done it. I have done it.
Done it? Ah.
Well, kind of.
Wait, no. It needs to be.
So you're right. Big sad. This,
Oh,
but there's.
yeah, you found it.
Well, there isn't really an adapter. It's quarter to quarter. We want a reducing elbow, right? It's quarter to quarter MPT. We can always. Well, no, we can't.
Wait, right there, adapter.
I know, but it's got a female. I want eighth to. I want male to male.
That's right. Yeah. Fitting madness. No, can't find it. Okay, not finding an adapter either. Wait, we control what size that fitting is. Well, maybe we don't have. Wait, hold on. What's the concern? The check valve has a different. Quarter. Wait, no, it works. We don't need an adapter.
What?
These are all quarters. That's
an
or
eighth.
is that an eighth?
That's 8.
Is it? Sure.
I mean,
Plus, if it's MPT, we can't control the orientation of the solenoid.
we could still get this, and then just get another. We could just get because female to female. We can just get another 8. We can get a quarter to quarter MPT nipple, and just put it between them.
Yeah, but you still... I think that actually might be more expensive than just using the tubing.
Making a short tube stub length. Also, how are we going to guarantee that those things stick out the back like that with an FPT fitting? Oh, you're right. Then very well it might not.
They might actually face the other way, yeah.
Well, we could just keep tightening, but then we risk breaking something. We could just keep cranking it, just be like a little bit more. A little bit more.
Yeah, alright, let's... Okay.
I'm sorry, I led you on the wrong path.
Darn.
It'll probably be easier to leave them like that, and then we can just bend a 1/4-inch tube at a short length.
Yeah,
you're right.
you know,
That was a little bit too much work for. We got excited. I got excited.
Yeah.
I'm sorry about that.
Well, it could have worked.
Now you gotta fix the bomb. Did
Yeah.
you adjust the bomb already?
No.
Good.
Yes. Well, I did, but... Hold on.
Thebomb.com.
Yeah.
Testing. Oh my god, dude. Dude. Look.
That's substantial.
That's an 80. That's a size 80.
Is it really?
Yeah. We might have to ask for, like, see if we can get 2 small ones. Because we don't need a lot of gas. See if we can get two 20s. Like those ones downstairs.
Yeah.
I know what you're saying. Like, well, what if we lose all the gas? Like, what if the valves get stuck open and we dump it?
If we want
But
to
that's
do
just
multiple hot
huge.
fires too.
That's huge, though. Like, how do we protect the bottle? Like, we'd have to have a really tall plate here. A really tall thing. I also didn't think about the plywood starting on fire right down the engine from the heat.
Nope.
But that's huge.
Well, but think about it. That's 2 inches.
I know. All I'm just saying is I know exactly what you're talking about. All I'm saying is I don't know what we're doing. Like, this guy, let's just say, is chilling here. Are you kidding me?
Well, it doesn't need to come all the way up. I don't think it's too bad. The bottle, get out of here.
Really? You don't think that's bad?
No.
Look how tall that is.
Yeah, but look how small. I mean, the engine's super small.
No, that's just like a lot of bottle.
I mean,
I think we could go with like a 40. Why do you fight me? I think we could do 40s.
well, we might have to with as expensive as everything is getting.
Big expense.
Yeah.
Air gain. What? Air gas. Popular gases. Nope.
Alright, we're gonna have to do some fun tube bending because these aren't going to be on the same plane as where that fitting is. This cat takes forever.
There it is, size 40. God, air gas, come on. Right there, look at. Get a size 40.
Yeah, do it 40, that's fine. Air gas
Well-
is like, well, they'll be closed though.
What, tomorrow?
When we test.
Oh,
So
yeah.
I'm saying,
Well,
like,
if we start testing, if we get any data or if things go south, what do you do? You need a nipple there. You can't do.
No, I know.
Female to female.
No.
It will weld it together. It'll be fine.
Okay, it'll be fine.
It'll be fine. It'll be fine. All right, 17 inches.
Whoa, where'd my thing go?
It's gone.
No, actually. Why did... Where did he go? Oh.
See, that's a lot better. That's more what I'm looking at. Look at that.
Yeah, alright.
That's still a lot of gas. A 40? That's double the... What's that little bottle downstairs that we were testing?
Yeah, alright. I yield.
He has yielded. Oh yeah, we were going to stop it 5 minutes ago to eat.
Yeah.
You can figure out the placement.
I'm not even...
We could eat on stream, but that's impolite.
Yeah. That's stinky.
How many people are watching this? 2.
2?
Oof.
It's us.
I think, yeah. I think we've just oofed. Doesn't matter. Get a good day. Still cranking.
No, that's what we want. We want this. I don't know what I was doing. The solenoids go above the check valves.
Yes.
Aha. Could me go. I don't know why my planar constraints aren't working on that. Fix it later. Alright. Is there? That's literally it. I don't think we need to model the tubing. Oh, we need a pressure transfer.
We need to model the tubing. We need to model everything. Let's do it. We'll do it later. If you don't model the tubing, I'm going to scream.
I mean, I can. It's just gross.
Then I'll model it. Not tonight. Maybe later.
No.
I kind of want to model everything because I want to have a nice...
No, yeah, I know.
Yeah,
Do we have the pressure? The pressure transducer is not in the bomb.
it is.
Mm.
Guaranteed in the model.
No.
You're looking at...
That's not it. That's a deucer. That's not a pressure transducer.
the deucer.
Oh, look at it. Alright. Let's eat food.
Take a little break ski. Alright. We'll be back in a little bit after we eat. We should be good to keep grinding and finish this up. Have a good stopping point. See you soon. What's going on? We're back. Got stuff? Got some jerky? This is gonna be good.
Mm-hmm.
Got an engine.
Oh. You don't even need an attention V2. We can use this one.
What do you mean? This one bomb.
We're gonna need a 45 to female and 2 for. It doesn't matter what size the pressure transfer springs, right?
I mean, the pressure transducer I picked out, which is yeah, it's 18 right? They're all 18.
All the 500 sounds.
All the cheaper ones.
Alright.
Heck and shoot. Ow. Alright, take this away from me. A deucer.
See this one. so small. Is that it?
Oh, look at this. Experimental flight board for 54mm rocketry.
That's pretty cool, actually.
This will be the next flight computer. Build another one that's like plug and play modules.
Yeah,
That'd be fun.
that's pretty cool. Alright, actually that is an 8. Nice. One part, okay.
I can't find something that has model regulator.
I couldn't find it.
The one
Yeah, there were some that were close.
like this,
Oh yeah,
but it has it out the side.
yeah. Honestly, I don't know. I think that's a minor detail that I think will be fine.
No, it must be perfect. There's so much stuff. Yeah, the search is really bad. Like, why is it giving me like engines, rotary engine?
Yeah, it's not. Yeah, that's not not exactly the thing we're looking for.
Wow, look at this fancy one.
Oh wow.
Unfortunately, the nut's on backwards. So he was close. He thought.
No, wait. What's wrong with that? Just use that one.
Using.
Yeah. Look at that model.
The nut is backwards. No, I'm just nice work. I'm gonna comment and say the nut is backwards. That's probably fine. I'm probably. The controller of gas.
Oh. Fittings that this is going to be.
Oh man, look at that bad boy. What it would be male to male, like nipple.
No, I know. It's just going to be expensive.
Oh well. Isn't it? I already had priced in the fittings for those valves.
Well, just think that's a quarter dash 4 to quarter MPT
How expensive?
times 2. So that's probably going to be like $6.
Have you looked?
No. But fittings aren't cheap.
I know, but the brass ones are really cheap.
That's true.
Don't worry, I believe. We have a Spanish casket. Oh. how did you had to go, how did you, like, I have it here, but how did you get the control, like, how did you get an import to be a
So it
bar?
has to be a step file, and then you go to the plus sign, and then just import, and then
Oh, it wasn't a step, it was like a special thing.
if it's a solid part, you have to make it. You have to check the little box that says composite, like make a composite. It's weird. Okay, now moving.
What if there is no step file?
Can you make it a solid part?
If I went here, import, it's in the zip file, right? Hit open. Oh, should I combine, import into the document or combine into, create a composite part?
Yeah, if it's a solid part, you want that.
This is zip. Like, how do I?
Oh, if it's a zip file, you need to unpack it first,
Really?
or unzip it.
Oh, failed to translate.
Yeah.
It like worked the first time because I did something stupid, but then.
Oh man, you pressed that. You got all the fitting going already.
Yeah.
Nice.
Look at it. Looks like you want to import an assembly. OnShape needs a zip file containing the assembly and all of its references to process the import.
What?
So, it's like, here's the zip file for it. I unzipped it. Something like, let me. No, it's like
Yeah, do that.
this one.
Mm-hmm.
Translation failed. Oh well.
Do the unzipped one. Yeah, try. Well, just where it says regulator.
No, it's the handle.
Oh,
This is the whole thing.
yeah, do that one. Is that an image or a? What the heck? I hate when people don't upload step files.
Big sad.
Yeah.
We're doing this one.
Honestly, just any regulator, really. We just need to show that one's there. That's the point, right?
Yeah. How do you normally rotate a part?
If you click on it, there should be like a... Oh, you have to place it first, so you have to check the green.
Oh,
Yeah.
oops. Yeah, never mind. I was being stupid there.
Just taping off. What's the... On the actual regulator, is it... You can choose what fitting goes into it, right? Well, what fitting is on it? Hello, regulator.
It's making me very angry.
Is it just not moving right?
It's not. Alright, well, it's gonna die. It has chosen death. If why? Oh my god. It has chosen death. Lay Deucer.
I agree with this dude.
Lame Deucer.
I'm gonna need a.
Grab those nuts, Fred.
PG thing.
What's going on? Nothing's constrained. Why is it making a full rotation? That's so dumb. Goodness.
What are you trying to do?
I'm trying to just stop being stupid.
Wait, why are you rotating it with the cube?
To get it straight on.
you just click the face.
No, I know. I was just playing with it because
No.
on Inventor. If you click this, it
It
just
goes all the way,
Yeah,
yeah.
and I'm like, what is going on here? I was like,
No.
oh my god. Watch this. I'm gonna go nuclear. Oh my god.
That was funny because that's what I was doing when I first was using this too. I was like, why isn't it going all the way? It's deceivingly like Inventor, but definitely not.
This thing just sucks, man. It just is this terrible software. I hate this software.
Oh man. All
I
right.
hate it because I can't use it. What do we just do? Like, obviously, if it wants to play games, if it wants to play some stupid games, play stupid games, win stupid prizes. That's what it wants to do today. And we're gonna play those games, you know? You know, bro? Watch this, ready? I played the game and I won. I tricked it and I won.
There you go.
There you go, Leto. Want 3 more years. Good. Yeah, definitely not a fan of this thing. Freaking dumb. It's only dumb because I can't use it. What a crap software. Crapware, that's what this is.
Oh, Sean's back. Hello, Sean. Yeah, we're still out. We're trying to finish this test and
We don't quit.
No. But once the test stand is done, we're probably going to spend some time making the MATLAB GUI like during the week, and then ordering the parts and stuff like that. Dylan's having a great time with Onshape.
This makes me deceased. Oh, now it did it. Okay.
Yeah. Yeah.
Not a fan of this.
Doesn't look like McMaster has a
See, this is going to be a problem to set the regulators. Maybe not.
except one upside down.
Oh man. No, I'll just tilt them like this.
Yeah. Alright, so this is an 1/8 inch MPT. What I want is an 1/8 inch female MPT to 45 flare. They don't have that.
Are you serious?
Yeah. So what I could do is get an NPT adapter and step it up to something that,
Makes sense.
yeah,
Mm-hmm.
which, I don't know. I just don't want to spend the extra like $4 to do it. No, I'm gonna do it.
Hey, there's no other way to do it.
Yeah. Ah, heck.
Alright, these are not constrained properly at all, but it doesn't matter. There is no such thing as constraints.
No constraints. Brass.
You went reducing adapters over there. A to B, that A to B thing.
Yeah.
Yeah. You went B to B1. Oh.
Of course, they don't have A as an 1/8.
Like, just click on the reducing adapter, see what else pops up there to the left. The box, reducing adapter. Reducing. There you go. The other way around. Maybe not. What?
That might work.
What? Oh
Eight
yeah,
to
because
the
then
quarter.
you can find a quarter female,
And
right?
then, yeah, here it is. There we go.
How much is that though?
That's $1, so it's like $3.50.
To fix this? Total? Ah, you're fine. That'll be good. Oh, this brass. Oh my god.
Yeah.
What's our price at? Whoa, $4.90.
Yeah, actually. What is it? Wait. Doesn't matter what degree it is. It's just how much we flare it, right? At the bottom.
What do you mean what degree? The 45? Wait, were those 37?
That's 45. No, never mind. We're good. Never mind.
It's like, dude, what?
Yeah.
It's like, what's going on?
It's 1/4.
Man, this one file, once I stop recording on this, is going to save it as a 1080p 11
Are you serious?
hour video. It's going to break my computer probably.
Oh man. Oh man.
Maybe we'll make the sled a little bit longer. We're kind of running out of room here. Ah, dumb. Why doesn't it work? Oh.
It's backwards.
It's Is it?
Yeah, because
No, it's not.
the 8th part needs to be male.
No, it doesn't.
No, it doesn't. Sorry, I'm thinking of the solenoids. I was like, oh, I done goofed.
He's done goofed it.
Yeah.
Done goofing. Alright, I'm trying to like mentally just process this thing right now.
Just absorb.
Oh my god. I'm just trying to figure out how to do this. Okay, I gotta do some other research here.
Yes.
1/4 inch plywood. I need very small sheet of it. I don't need big sheet. I need small sheet. No 4x8 sheet. Look at that. I don't need that. It's expensive. 2x4. Oh boy, look at 2x4 fiberboard. Oh no. 2x4. No.
All right. How bad do you want to use?
This one's $12.
$12. No, not enough. 1/4 inch. What's the ID? Doesn't matter. Yeah, it does. Whatever,
what?
whatever works. The tube. The copper.
It's 1/4 inch OD.
Yeah.
Why? What are you looking? What are you doing?
I'm just done making the tube now. We have 197.97. So we have 197. I'm not gonna. So the way that you're supposed to do it is you're supposed to edit in context and be all fancy. I'm not gonna do that because that takes a long time.
Oh, for the tubes.
Yeah.
So we can get this 2 foot by 4 foot actual plywood, and just I would say we get just this. We
Yeah.
cut it into two pieces, just two 2 by 2 feet, and then
Nice.
just do 2 feet, 2 feet. Or actually, no, sorry. That's a tight tube bend right there.
Yeah.
That's really tight. I don't know if that's gonna work.
What, that?
Yeah, that's tight for 1/4 inch tubing. Maybe not. Maybe it'll be okay.
We're not bolting this. Like we're not securing the lines to anything. I'm like literally we'll just drill holes and zip tie it if we want to secure it. So if it
It'll work.
we'll just bend it until it's fine.
We just you don't want it to kink. That's what I'm saying. We have two bending tools.
Right.
We have 2 bending tools though to prevent it from kinking. So
Yeah.
we'll be fine. That's probably good enough radius.
All right.
Yeah, 2 bend.
Oh man, this is so disorganized, but we don't have time to organize it. We should have organized it as well. That takes a while. Whatever. That's fine.
That'll be fine. All right.
Jeez. All right.
Look at this.
Did we?
Comment so they give you the plywood. It's like it is 2 foot by 4 foot, but it's actually 0.205 inches thick by 23 3/4 and 47 3/4. Why? Just make it. They always want to skimp out on money.
Well, maybe I was thinking maybe that's how it always is.
No, it's not.
And they just round it up so it's easier to say.
No, it's never been like
Even a piece of plywood from like the.
that. No, they just want to. They want to. They used to actually cut things like to size back then because
Yeah.
they weren't like pieces of poop.
All right.
I'm just trying to mentally think. Oh God. What is the secret?
Let's see. Maximum pressure. 1400.
What do you do? I have the copper tubing already.
I just searched tube. Oh, no tube in there.
You're not even.
Bruh.
It's the same stuff.
Mm-hmm. All right. Is that rated like?
Yeah. Look. Go. Do a look. Go down and go down and look.
No.
Pressure of 1,195 psi.
It's not enough.
It can't do it. limit 90 per order for this wood. All right.
What's the ID?
By proops, by props. Proopy prop.
Feel that.
I feel. You got me in the feels right there. Wooden frame. Yes, please. We're going to extrude this, like, I think a little bit longer. I think we're going to do 3-foot sled. All right.
All right.
That makes me feel better. Maybe 3 feet. Is that too much? I think that's too long. Maybe. Yeah.
A little bit.
A little bit too much length.
Yeah.
You have so many things just called part studio. It's like,
Oh, actually, I should probably fix that. That's important.
do 30 inches instead.
So
The engine floor.
yeah, engine floor. That's what it is. It's the engine floor. Floor is gone.
I see what you did there. Botched it. Oh my goodness, I botched it.
Can't believe you've done this.
12 by 12, yeah, boy. You are not gonna be happy with me.
Oh my god. That's fine. You could. I think there's planers. I think there's a planar constraint there, so you might.
Well, yeah.
If you just delete that.
Things have been broken though. We're gonna unbreak them.
Things have been broken.
Tubes, engine tubes.
Yep.
Yeah, make sure 10 feet is enough too. It should be, but you never know.
Yeah.
PT tubes, PT dubs. What? What did I just say? We're gonna make this thing. How wide? Probably 14 inches. Make it a little plate. I can't do this. 6 plus
6 plus 1.
6 plus
No.
6 plus 1, 13 and a half. No. Half an inch. No, offset this. 0.5 inches. No. Sorry. Are you?
What happened?
Oh, that's right. Look at that. I mean, should I just make it exactly the width? Like there's.
Yeah, that might as well. Make it really nice.
Maybe we do things. I don't know why I was like even considering making it. I ain't doing it.
Why? Just not. I just canceled my fasten. How would I do that?
Oh. Lace lid.
Alrighty.
Basically,
Look at that.
look at that mad well.
Do we need? You already have the B-nuts on there, right?
In there? Yeah.
Yeah.
They're not on
Oh, they're-
McMaster. They're not McMaster B-nuts because they were way expensive on McMaster.
That's fine. I'll just steal the CAD from there.
Yeah, that's fine. But the McMaster B-nuts were like, whoa! Each one of them was $2 or $3 something. Oh, they're not. They weren't B-nuts.
Huh.
Or they were 3. No. No.
No. No?
No.
Why not?
I said something. It's not. That's not it. It's-
Sure
look
about
up
that.
45-degree flare.
Oh.
Now, right there it is. Nuts for 45-degree.
Oh, those are different.
Yeah, look at each one of them was $4. See, excuse me. Wait, how much? $159? Oh, because it was for. Okay, the reason I did this because it was like it said it was for 49 tube wall thickness, and we're at 30. Ours is a 30 wall, and they said this is for 49, so I was afraid to use these. Right, because I didn't want to break something. So you can use the cat fur, it's fine, but we're gonna use the other B-nuts. Not B-nuts, just other random nuts.
Oh, I see how these work. Alright, that's kind of weird, but...
That's kind of weird.
Makes sense.
I'm gonna call this the blast plate.
Yeah, actually.
Heckin' darn shoot.
Oh.
just gonna simplify this thing. I'm gonna call it the cradle. And it's gonna be simplified big time, as in I'm not gonna do individual pieces that are gonna be mated together. I'm just gonna make it a one giant large object.
It's not a bad idea, actually.
Because I'm tired of doing that. I don't like how this software is. Unfortunately. Big unfortunate.
Big unfortunate indeed.
Oh my god, come on. There you go. Whoa!
Connector, please. Sometimes they just don't go where you want them to go.
This is gonna be so weird looking, but it's going to. Oops.
Alright, fluid's done. Unless you want me to model, a tube from the regulator.
Yeah, could you?
Yeah.
Gotta be as accurate as possible.
Yeah.
Always gonna show that. Or not like we did the test hand. We didn't do much talking for this like second piece
No.
here. We're kind of just like, yeah, and it's working. Oh, failure.
It's working. Oh.
Abort. Abort. This is how you're supposed to do it. Ready? Look at that. The whole thing is like black. Almost. Because black lines mean constrained sketch. Except for these bottom ones, because I don't know this value yet. You're just not good enough.
Man.
Just getting smoked over here.
Yeah, for real.
There, that's the frame to hold the bottle, made out of wood. It's just gonna be bolted. I'm gonna cut the wood and it'll be fine.
Nice.
Actually, yeah, these aren't numbers that we're gonna keep forever. I'm just gonna say it's gonna go over to the bottom of that, but that's not the right regulator, so it doesn't matter.
Oh, no, you're right.
I would do it to the bottom one, if you can. It'll just be more accurate, even though it's not accurate.
Nice.
You know what I mean? You picking up what I'm putting down?
Yeah, yeah. Oh, that's right. Yeah. All right. That means less bends too. I'm down with that.
Down with less pens.
Yeah.
What should I call those 45-degree, like those braces?
Yeah, I don't know. That's a good question.
You can tell it's getting late. No, I'm gonna die. Oh my god.
Almost there.
Almost there. I'm starting to get like jittery. I'm like, Yeah, there's a way to change the entire thing here to be not metric units so that you can actually like do all these things and not metric, but I didn't do that. And I'm not going to.
Yeah. It's actually really helpful to change that.
Because there was just so much, dude, oh my god, where are those landing? Look at this. Oh my goodness.
Oh, I didn't account for the bend radius.
Just winging it.
Yeah.
It's fine. Sometimes it has to be done. Oh, wait a second. 1, 2, 3, 4, 5, 6, 7, 8. Oh my gosh. If we get that pack of 10.
Actually.
1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7. Oh my god, we're going to use all 10 for this thing.
Are we really?
Yeah, every single one of them is going to be used. We'll eat biscuits.
Nice.
Nice. Not nice.
Not nice.
Pachoo, 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 pachoo. Ah, bun muffins. Okay, I gotta stop. That was weird. What did I just say? Oh my god.
Alright. Not exactly,
Not exactly a good thing, but
let me see.
alright, we're gonna have to put in some holes. No, no, I won't do it. I refuse, I won't do it. Oh, dude, oh, dude, look. The plywood we get, look at that. That's with the amount of plywood.
Oh,
we
that's
can-
nice. That's
we can-
perfect.
Yeah.
Alright. I like that.
Good stuff.
Yes, indeed.
Money. Cash money. That's some cash money right there. Alright, insert some more stuff. Braces. Oh, these are large. Is that good? Look at those.
Actually, I'm gonna oversize it.
Actually, hold on. Before you do it, I think you have to change the tube. I gotta move these bottles forward. No.
No.
No. I'm sorry, but no.
No, it's fine. No, actually, yeah.
Well, okay, this doesn't need to be absolutely perfect.
I'm gonna oversize them by a decent amount. That way we still have some room to work with. So if they're cutting into the regulator, that's why. I wonder if it's been the same 4 people that's been watching this most of the time.
It'd be kind of interesting.
It must be. 12 hours.
Cry. Small cry inside.
Alright, it's a little off, but let me see actually. Now that should work. Give us some room to mess around with the things there.
The cradle is very small, actually. Oh no, that's not good.
What? Oh, not exactly. That's an easy fix though. You just
No, it's not. It's not. Poop. Jeez, you saw what I'm trying to do there, though. Just make a little cradle for the bottles to sit in.
well. Here, what you can do.
What? I can just put another piece of wood on the front, and then bolt it, screw it into the 1/4-inch plywood sheet.
Yeah, you could just extend it so that, like, you have a 2x4 this face raised.
I know how I know how I want to fix it. I think. Freaking play around here. This is just a botch.
I think I'm gonna put a small hole for the PT and yeah, for all the wires. That way we can run it up, run them up like this back panel.
Yeah, because that's where all the electronics are gonna be in the back there.
Yeah, okay.
Make a big hole so we can run all the wires through it.
Yeah.
Wow, that's a stink. Look at this. What is even the...
Quite interesting.
Oh, now guess what? When we run the 1 and the 3-inch long screws, they're gonna go through the 1/4-inch plate and all the way through this.
Well, that's not good.
Screw it. It'll be fine. I can't do this. I just can't do it in my head. Oh, nice even numbers. That's what I like to see. there we go. Look at this.
Oh, okay.
I
I mean,
just screw it into the back there.
that's better.
The problem is though, watch this. I'm gonna botch. You're gonna have to redo these tubes. They gotta move these bottles. Should have made the cradle. Should have made the cradle first.
That's fine.
I want to do this to here. Big brick like that. Oh, that's not good. Look where the tube's gonna go most likely. Right down the.
Well, why do you need that support there in the first place, though?
That was to hold the bottles in there from falling over.
Oh, that's like the. Oh.
Yeah, you know, so that we don't have a stupid. This is doing something about it, right? Could have sat them down on there and never did anything about it, and then we would have had a major issue if they all fell or something. Like not constraining bottles. What did you just do? Did you just break it? Look at the bottle.
No.
Okay.
I'll move in a circle around. Alright, what happened? What happened? That was pretty scary.
What happened is this thing is making me. Watch, as soon as I bound it to here, it goes like this and sends the bottles off on their own. When I flip it around, they're just nuked.
Yeah.
See?
Are you able to move the bottles independently? Like,
All I want is that bottle to be right there.
I was gonna have to use. Unless you want to drill a hole through that 2x4. We're gonna have to.
No, that's fine. It'll be fine. We'll drill a hole through it. It's not gonna hurt.
But yeah, but that to think about it though, that pipe is going to have to like. We're gonna have to flare it.
The other thing is we also
there.
have to think is I kind of just chose a random height, so I could do this. I didn't even choose a height. Get like. You gotta be kidding me. What? Oh my god, I hate this software. Do you not understand? Why? Why does it do that? I hate this thing. I hate this software.
What are you trying to do? Just move the. What's it constrained to? Just,
I want to move it down. It's going up, and then I hit reverse, and then it flips the lid.
Alright, wait, hold
Oh
on.
wait, there we go. Dylan's on my iPhone.
Trying to do this?
Whee!
Trying to do that?
Yeah.
You just drag it down.
I want it to be bound by some number so it doesn't just all move when we touch it. You know?
You know, here, look, here's a fun
No, I
hack.
think I figured it out. I think I got it.
I was going to show you a fun hack.
Fun hack is to just quit. Oh my god. Major broke. Yeah, just undo that.
Yeah, alright.
Show me the hack.
Look,
Where the hack's at.
you bring it down, okay?
Mm-hmm.
Why is it not? Why not? No, it's not going down. Look, you just highlight everything, make it a group.
Bullying it all together in one mass. That way it never breaks, right?
Yeah.
Dude, look at your lines. They're inside my bottles here.
No, honestly, that's a serious problem though, because, like, how else? Where else are we gonna route those? Unless you want to do some kind of like.
Yeah. Well, we can. That's not too bad. That's just the two. We have the two bender. We should do it. Oh, it's 8 o'clock. Oh my god. We gotta shut her down. Are we missing anything we're supposed to be doing?
In terms of
Today's live stream. Oh, my eyes are like so freaking done. 11 hours and 32 minutes of live stream. Crazy.
we're watching.
Oh, look at all these planar mates. They're just broken. Because mine. We're gonna delete it because I think mine broke it all. Yeah, mine broke it all. That thing broke it all.
Nice.
So here, now it moves. No, it doesn't.
Yeah, there you go.
Why can you move it? I can't. Move it down. There we go. Just leave it there. Don't touch it. Yeah, so we could do something like that and then go like this. Two bend, right? Up through here. And then just like do a little elbow thing. Like a little kink dog leg.
Zigzag it through there.
Well, remember also, this isn't accurate to what we're going to have, right? The bottom bars, actually, they're going to be this way, though, I think. Yeah, because the valve and the regulation
Are
actually.
they going to be poking into that middle?
That's why we'll just twist them like this, and then bring the tubes in one.
Yeah, alright. It ain't going to be pretty. That's. Alright, let me. Alright. Did the sketch. Alright, yeah. Did it. Wait, let me just watch yours. Let's try one more. Nice. I'll take that. We'll just do some weird fun bending.
I like how that's like almost exactly in the middle of that 2x4. Yeah.
Nice. Well, alright. I could.
No.
I could get all fancy. I could. Hold on. I kind of want to now. Let me just.
You're gonna do the dog-like thing?
I kind of want to now, yeah. When you show people that CAD, they're gonna be like, "Oh, well, your tube's going through this," and I'm gonna be like, "Well, you see," I'm gonna have to explain it like every single time. So I'm going to
Fix it?
yeah.
I mean, there's probably a different way to do this thing. We did it very hastily. You know, there's probably, oh man, there's a simpler way to do this. You could just like screw in wood into these corners. Just stick them up and like, no, probably not. Big brain time.
Big brain time. Hold on. This arc tool is just not my forte. Oh my gosh. Hold on.
So, for everybody still watching, if you're even there, somebody's even there, maybe. This is our test stand. So it's probably gonna look like. It's gonna be pretty cool.
You know, I'm gonna do a spline.
You got the engine here. You got fluid lines to go to the check valves and into the valves. You get the pressure transducer. You get the deucer. You get the lines going out to the regulators. And then to the bottles. And then you got a little blast shield thing here. Even though it's only 1/4 inch thick plywood, it's probably better than nothing. So that's there. And then we got a little holder for the bottles so they don't tip over or move. And then, yeah. Looking good. Things might start on fire because it's all wood.
That's entirely possible. Maybe I don't want to do a spline. Alright, let's see
Huh. I have so many tabs, oh my goodness. I think I'm going to change the USB to 25 feet.
Oh, yeah. Yeah, that's probably...
It'll be fine. It'll be fine. Boom!
Yeah, we say that now.
Why did I highlight that?
Self-intercept. Where? Oh. Oh, I overshot a little bit.
Oh my goodness. You didn't need to... Why did you do it like that? It'll be fine. I was just saying... Oh, okay. So you could just...
No.
Why'd you do that? Hold on, no.
Why is my B-nut all the way down there?
Don't click away. What's going on there, buddy?
It looks cool, alright?
It looks cool, but it's not... You could have just did a rowdy route right there.
It was fun. It was fun. It was
It was
all
an
fun
experiment.
games,
It was
yeah.
an experiment. We were just testing stuff. I saved us a little bit of money with that cord. Less safety, more money. No, that's not. That's
Not exactly the best motto, but
No, that's not what's happening. We have some more safety procedures and cautions now. We can always just. Never mind. We could though, but we can't.
yeah.
Oh, I'm an idiot. Oh, maybe we can try. Oh, I don't think it'll work. I was gonna say we could do the 25 USB 20 foot and bring it to this. Bring it to a dongle, one to power,
Oh man.
one for the Raspberry, or not the Raspberry Pi, the Arduino Uno, and then see if we can get a webcam to hook up to it.
I mean that's kind of cool.
Maybe we'll test it.
No, yeah.
It probably won't work. There's not enough bandwidth on the serial probably for that USB.
All right, what is going on with these?
All right, it's 8:11. We're almost there. I think we'll probably close it up at 9. I think that's a good time.
Yeah, I would agree with that statement. Look at that.
The bee nut though did not do it.
No, the bee nut's not having it.
Oh, we were gonna do this too. Remember, I was gonna like, oh, we'll do some pressure drop calculations. I think we're gonna be fine with that.
I think so too.
I don't. The system isn't gonna have many restrictions. The engine ended up being a lot smaller and less hungry for fuel and oxidizer than we initially thought. So I don't think we're gonna run into some flow issues here. That was kind of what this tab was for. We might throw a couple things on there. I'll get rid of this number punching thing with this sheet anymore. Yeah, here's this. Here's the sheet. I feel like I'm missing something, but I don't know what.
I kind of get that feeling too. Like, what did we overlook? Oh, yeah. Yeah.
I don't know when that one came in.
Now, if you're still there, yes. It is pretty much the... Yeah. Not much of that is going to change, but it looks pretty good.
Yeah.
It's not bad. It doesn't look like garbage. Ah, alright. It's happening. Nice. There it is.
Here is the adjusted bi-prop. These obviously are not perfect because this is all fudged up here anyway.
Yeah.
Because the actual outlets here, these are just regulators we found online. Ours are different than these, but we couldn't find them. We were not about to cat the regulators. I was not going to do that, so... I don't know if I want to make these small.
I mean, I think that's if something explodes, it's easier for...
He's got some
something to hit it, yeah.
We could also put we could put a shield, like, right along here.
No, honestly.
So, oh. Oh, goodness.
But all of that plywood, all that wood stuff, that's already in the bomb.
Yeah, the 2x4s
Alright.
are in the bottom. I got 2 8-foot lengths of 2x4s, which is probably more than enough.
Oh, nice. So we still have some money for gas.
I don't know. Let's take a look at this.
Yeah.
What are we missing? Oh, did we do the plates correctly? Did you do the injector? We have 2 half-inch plates or 2 quarter-inch plates and then 1 half-inch plate, right? I don't think those are accurately depicted in the budge bomb.
What? Sorry.
I don't think you ever you have here these.
Oh, we still need to have the hardware.
No, not the hardware. Where the heck is it? You have these aluminum discs, and you have 3 of them, but we aren't using. We don't need. We're going to have 2 of these quarter-inch ones and 1 half-inch one. And the quarter ones are already that much money.
What's there right now?
3 of them. So let me do some searching.
Yeah.
Hey, here we go. Look at 1/2 inch. Here. You got a multi-purpose 2 inches in diameter, 1/2 inch long is $4.21. So we're good.
Nice.
We're okay. Almost had a botch there.
Yeah, that could.
What the heck? Plus or minus 34 thousandths of an inch on the diameter tolerance? What? How? How do you? What? It makes no sense. That's a crazy diameter tolerance. All right, we're gonna add that to it. Control C. We're gonna do. We're gonna call this guy fitting part. So what? Fitting plate.
Yeah, that would be fitting plate. And then just
Oh, you already put it there? Did you just do that?
no.
Oh, we already had it there.
Oh yeah, I guess I did put it there.
Never mind. But we have to reduce it. We don't need 3 of these now. We need only 2. So that saved us a couple dollars. We're at $4.78. The price is going down.
It's not bad. we still the hardware. All right, let's do that now. Actually,
What hardware?
let's get the bolts, the screws. Yeah,
Which screws?
These.
For the engine? The
Yeah.
bolts. They're bolts.
bolts,
Do,
bolts.
do
screws,
not. Do not.
washers.
No, no washers. No washers on this project.
Yeah,
Those bolts are pretty expensive. They're quarter 20
20.
by inch. Well, actually, yeah. Let's do some actual thinking though. Do you want to make them all the same?
yeah.
Like just buy one? That's not.
Let's do some thinking.
Let's do. You want to make all? Yeah. To make all the same? Yeah. Oh no.
We just get the zinc plated. No, not even.
What's cheaper?
Alloy steel. That's cheaper.
I
Yeah.
like it. How much is in that box though? Is it one of them? I'll tell you, it's one.
No, it's not. Is it? No, they don't.
Yeah, it is. It's one.
Is it really?
We order that and a one shows up. Yeah, it's one. There's only one of them. Oh, sorry. I'm just excited, you know? When you do 18/8 stainless, yeah, because military spec.
Oh, hold on. Wait, go back.
You have military spec link on.
Oh, yeah, there was no quantity.
No, don't choose temperature. I think
Let's get plastic.
How to blow your engine up 101.
Yeah.
We're gonna have to bite the bullet. 25 of them isn't
No.
bad.
Yeah, okay. 25 for $7 bucks. 757.
676. Words.
Words. Yeah, alright.
Yeah, put it up to yeah. Where it says retaining plate hardware. Just say like hardware. I'll rename it bolt hardware.
Read it. Did you know?
Hold on, I'm gonna go. Let's go and stand by for a second.
$6.36. Oh, you did the dollar sign thing. That's a nice little trick there.
That's a nice little trick. engine bottles. I can't type.
Yeah, you know. Alrighty.
Hold on, are these extras that you put in? Do we need all of these?
I think so.
We need.
Hold on.
Why do you have? We have quarter MPT to 45 flare again. You have another one there. It's 2, and it's a different price. Oh, is that the? That's the female adapter, right? That's
I
the
think
one.
so. Yeah.
All right. I'm gonna do female NPT to flare. We're almost there. Bottle tube. I thought it said bottle time. Bottle time. Leducer. Why are these like? Why did all of these ones up here like go the double width?
Would you call it a that part? What did you say it was?
A bottle? Oh, cradle.
Cradle. I was like, casket? No.
Casket.
Ooh, no.
Oh.
What's that one? That's
The casket.
the... Yeah, don't exactly want to be leaving the test site and going into one of those.
That's the opposite of success.
Yeah.
That is a failure. That is a test failure.
Yeah. What is that? What is that?
That's the adapter.
No.
Quarter, eighth MPT to quarter MPT. Alright, I'm gonna go grab some more water.
Alright.
Be right back. I still haven't finished my tea. Oh crap. You know, it'd be a fun project.
Sure.
Like a 72-hour liquid bi-prop where
Man.
in 72 hours you have to go. So you take how would this work? This would be hard because of valves and fittings and all this other stuff, but
Duplicate.
I'm trying to think, is there a way to do one of these projects, but like over the weekend with absolutely none of the supplies?
I know, it's
Like getting the fittings and the valves from somewhere that's open on the weekend. And being able to get it on a like hour notice. That's like the hard part.
Yeah. Hold on. Oh no. Okay. That's...
Probably not. It's probably not feasible.
I mean, depends on where you are. If you're in like Mojave Airport,
They probably have something.
you get enough people that was just like, yeah, let's do this, and then
They find things.
yeah. Alright, hold on. It's that part that I think, yeah. Okay. That's the myth. Alright.
Oh, crud.
What?
We have to get drill bits.
Yeah, that's true.